Тест 1, 2, 3, тест 1, 2, 3, тест.
Good morning.
I speak freely, like you will take a speech. So
Oh, like yeah, I usually take speeches. Good morning, everyone. Welcome to the 9th edition of the Eastern European Machine Learning Summer School.
it is.
It is 9th, yes.
Next year is 10.
Yeah. You can. Test. 1, 2, 3. Test.
Yes. A.W3.
Your Excellency, Mr. Jakov Milatovic, President of Montenegro, Honorable Mr. Mirko Stanic, Vice President of the Assembly of the Old Royal Capital Cetinje, distinguished lecturers and organizers, ladies and gentlemen, dear participants, good morning and welcome. My name is Tamara Pavlovic, and this is my great pleasure to welcome you to the opening of the Eastern European Machine Learning Summer School. For the first time in the history of this school, EEML is being held in Montenegro, and it is being held here in Cetinje, our old royal capital and the historic heart of this country. Over the coming days, participants from across Europe and beyond will work side by side with some of the world's leading researchers in machine learning and artificial intelligence. Lectures, tutorials, poster sessions, and a great deal of conversation. It is a privilege for Montenegro to host this school, and it is a privilege for me to open this morning. We will begin with a short opening ceremony. 5 speakers will address you, and then we will go directly into the first lecture of the program. Our first speaker is Dr. Viorica Patruchan. Dr. Viorica is a research scientist at Google DeepMind. Since the school began, she has carried it through several countries across our part of Europe, and this year to Montenegro. Everything you will experience this week exists because of her work and the work of the team around her. Ladies and gentlemen, please welcome Dr. Viorica Patruchan.
Your Excellency, Mr. President, distinguished guests, ladies and gentlemen, dear participants, good morning. We won't start every morning this formal, but I hope you're all excited, as I am, to be embarking on the 9th edition of the Eastern European Machine Learning Summer School. And I'd like to start off by saying that for us, this is so much more than a summer school. Here at EML, we are on a mission. We want to bring the top-tier conferencing experience in AI to Eastern Europe. There are so many talented researchers here and so much potential, but there are very few top-tier events. So we want to change that. And ultimately, our objectives are to improve access to AI education, to support and connect the community, improve diversity in AI, and raise awareness for policymakers. And we work towards this mission by organizing various events like this summer school, but we are also organizing various workshops like smaller events. All these are non-profit events hosted in different Eastern European countries, and we bring the best of the best in AI experts from all over the world. The participants are as well from all over the world, and we give priority to Eastern European students and participants. And we make sure that the events are very accessible with low registration fees and scholarships where needed. And we do this through donations and sponsorships. These are all volunteer-driven events. We have about 100 people involved each year in the organization. Organizers, speakers, reviewers, panelists, teaching assistants, local volunteers. Lots and lots of people are involved in making this event possible. And we started this initiative back in 2018, together with Razvan and Doina. Razvan is here with us. And we started in Romania because we're originally from Romania. And after that, we toured different Eastern European countries. And then in 2024, we got fresh energy from Petar and Matko that are also here with us. All along this journey, Gabi has always been with us for moral and technical support. So you will get to know all the organizers this week. In a few pictures, this has been the journey so far. 2018 in Cluj, 2019 Bucharest, 2020, 2021, pandemic hit, so we were online. 2022, back in person in Vilnius. 2023, Košice, Slovakia. 2024, we started touring Petar's home countries. So Serbia to start with, then Bosnia and Herzegovina in Sarajevo 2025. And this year we are in Montenegro. And during this journey, the field of AI has progressed so much. Like the pace has been amazing, and we are seeing transformational impact in sciences with the winners of Nobel Prize recognized in 2024. AI is driving our cars, and I'm happy about that because I'm not a good driver. It's also writing our code nowadays. I don't know, do you remember when we used to write code by hand? Well, now AI is writing our code. So there has been a lot of amazing progress. However, there are also some negative points to this development. And very recently, there has been a study from MIT outlining the main risks from AI and the pace at which things are going. So among these risks, we have the risk of AI being used for mass harm and weapons, centralization of power, unfair distribution of benefits, misinformation, false spread of information, and others. So we believe that in this context, our mission is more important than ever. We really need to make sure that everyone's voice is heard in shaping this technology that is impacting everyone's life. So I'm really happy to welcome you here, and thank you for being together with us in our mission. Thank you.
Thank you very much, Dr. Viorica. Our next speaker this morning needs very little introduction to the EML community. Dr. Petar Veličković is a research scientist at Google DeepMind and fellow of Clare Hall at University of Cambridge. His work in graph neural networks and geometric deep learning is among the most cited in this field, and he is one of the reasons this school has come to our country. He will also take you through the practical side of the week ahead. Ladies and gentlemen, please welcome Dr. Petar Veličković.
Your Excellency, Mr. President, distinguished guests, ladies and gentlemen, thank you all so much for joining us today. Dobro jutro, bună dimineața, good morning. So, it is absolutely amazing to be able to speak to you all today from the old royal capital of Montenegro, Cetinje, and as Viorica hinted, to bring our little summer school event to a country where I draw a lot of my roots from. I want to start by giving you a little bit of a personal motivation for why I pushed so hard to join the EEML community and why I supported the initiative through giving talks, reviewing applications, and so on for many years in the past. And to do that, I'd like to raise the question of what it looks like to work in artificial intelligence research or development today. If you take an off-the-shelf image generation model and you ask it to visualize an Eastern European scientist working on artificial intelligence, you actually typically get a picture like this of a scientist submitting a paper to a journal. Unfortunately, this is all too common today in the way AI research is done all across Eastern Europe. You do your work, you submit to a journal, and you just continue. And you're kind of mostly hanging around with your local community, and you don't get as much chances to go beyond. But realistically, the real conversations, the real work, and the strongest ideas are not shared in this way. To truly see how ideas are shared at the highest level, let me show you my first conference experience in AI in 2017, my first NeurIPS conference in Long Beach, California. So I got a chance to present my work in a live poster session. This is how most of the big research ideas are shared today. It wasn't particularly visited. It was one of my first papers, but still the experience of talking to people from all around the world and people who are top experts in this field was highly invaluable. Then I got to hear some really prestigious people talk about their areas of expertise. I still very fondly remember UiT's tutorial on Bayesian deep learning, still one of the most crisp introductions to that area I've ever heard. And it was in a huge room with, I think, tens of thousands of people listening. Many of you might know this architecture here in the corner, the transformer, the cornerstone of modern large language model technology. That was presented in NeurIPS 2017, a very interestingly high bar for my first AI conference. And also, maybe one of the main ways in which information flows and friendships are formed and networks are expanded, there were lots and lots of parties, okay? This is really the way in which new bonds are formed most easily. Not through poster sessions, not even so much through talks, but just by partying with like-minded people. And you also get to meet and interact with some of the people who have shaped your development. 2017 also happened to be the first year anniversary of the Deep Learning book. And we had a chance to catch up with Ian Goodfellow, Aaron Corville, and Joshua Bengio, who were all there promoting the book for the one-year anniversary. So this was a truly amazing experience, and one that I couldn't have gotten if I just sat in my office back in Cambridge. So the real point of EML is to take these experiences and bring it closer to home, because even if you work in a research group where the importance of these events is recognized, there's often not as much budget to easily travel to the United States, not even to mention if you need to get visas and things like that. It's not easy. So let's try to bring that top-tier experience back home in our own countries. These are snapshots from EML in Novi Sad in Serbia a couple of years ago, where actually we brought Yiwai, that same speaker I showed you last time, to give one of the keynote talks. You got to present your posters, and if you're lucky, you can get some really top-tier people attending your poster. Actually, Sander, who's going to be our diffusion model speaker later today, very commonly frequents these poster sessions. So if you see him, stop him and chat with him. He's super friendly. There were lots of parties, and we will actually have parties this week as well, where people got to exchange ideas. And some of the conversations I had with the people presenting their work led to research papers. This is a snapshot from a paper that I co-published with a student from Croatia who was attending this EML, and that's where we first met. So now we're bringing it to Montenegro. This is Viorica while we were setting up for the event in the hotel. So, I leave it to you to fill the gaps as to what we will make happen this week, but I'm sure it's going to be really amazing, and I'm really looking forward to it. So why am I so passionate about bringing this school to Montenegro? Let me introduce you to the old house where I used to come every single summer back when I was little. This is the very charming rural community of Njegnjevo in the north of Montenegro. And this is roughly where it is, near Bijelopolje. And this is where 50% of my family is from. I always held a very close bond to Montenegro, and I always wanted to take many of the things that I have developed and bring it back to the region in any way possible. But you cannot do it alone, okay? And I must stress, we had a really amazing team of folks from the Montenegrin AI Association, along with our other partners, that have helped us make this event as great as it is, and to bring you everything you will enjoy throughout the week. I'm just quickly flashing everybody's names. You can find all of us on the website, but these people truly deserve the highest of appreciation for all the painstaking work that they've been doing throughout the past months. Okay. But also, we had a lot of local partners beyond the Montenegrin AI Association. We would like to kindly acknowledge HPC Montenegro, the University of Donja Gorica, and the Cetinje municipality, Prijestonica Cetinje, for kindly supporting our event every step of the way. But the support this year extended to an amazing broader ecosystem that we have built and helped cultivate. So we have had a lot of help this year from the ARIA, Romanian Association for AI, the ANT from Bosnia, Association for the Advancement of Science and Technology, that have helped us set up the event in Sarajevo last year. And we're also delighted to welcome AI Albania, who is one of our co-organizing partners for this year. Here is the really amazing slide. We never had even 1,000 applications. This year, 2,656 of you have applied to come to the school. The acceptance rate was only 7%. So consider yourself very, very strong applicants for being able to make it here. Together with industry representatives, there's 290 of you. As we aim to foster connections in the Eastern European region, more than half of us are from EE countries, mainly Romania, Montenegro, Serbia, Poland, Croatia, Bulgaria, Slovenia, and Turkey. But there's 70 countries represented worldwide today. And it's spread all across the world, from Peru and Mexico through Nigeria and Tunisia, all the way to Bangladesh and Australia. We are truly a global event with Eastern European backing. The distribution this year is still mainly PhD students, but I think we're starting to notice a trend that AI is getting more and more accessible, and we're having more and more master's undergraduate students participating. And also we have 6 high school students with us this week. So it's going to be a really interesting event and exchange of ideas across all levels. And I hope that we can all help each other conveying the things that we know well so that the next generation can grow in the best way possible. Our gender balance remains in line with previous years, 35 to 65. So the event's stature would obviously not be where it is without our amazing speakers: Alexander, Andrea, Claire, Dan, Dorothy, Mari, Federico, Isidora, Kyunghyun, Magnola, Maria, Mattia, Nicholas, myself, Philip, Sander, and Sarath. And also our amazing tutorial leads: Alex, Alexandra, Andrei, Larissa, Miruna, Ross, Skanda, and Seva, along with great support from several of our amazing teaching assistants. Obviously, a single first name doesn't give it justice, but let me give you a quick summary of all the things you will learn this week. We'll learn about deep and reinforcement learning, multimodal and embodied learning, LLMs, MECinterp, diffusion models, AI for mathematics, AI for biology, continual learning, efficiency, geometric deep learning, ethics and fairness. Truly a spread of all the hot topics in AI right now, including some things that we, the organizers, believe should be important parts for future developments. And we have truly managed to bring speakers and tutorial leads and teaching assistants from the best institutions in the world. From DeepMind, Anthropic, and Isomorphic Labs, representing the company space, through NYU, Cambridge, Oxford, MIT, Mila, EPFL, UCL, École Polytechnique, IST Austria, Politecnico Milano, and also our local representatives from Universitate Crne and the University Alexander Moisiu in Durrës. So that's all from me. I hope you'll have an amazing week. Thank you so much. Looking forward to meeting you all this week.
Thank you, Peter, very much. Our next speaker comes from the organization that brought this school to Montenegro as well. Mr. Milutin Pavicevic is part of the core team of MAIA, the Montenegrin Artificial Intelligence Association, the host of EEML 2026. For years, MAIA has been building an artificial intelligence community in this country, and this week in Cetinje is the result of that work. Ladies and gentlemen, please welcome Mr. Milutin Pavicevic.
Thank you. Your Excellency, Mr. President, distinguished guests, dear friends, it is my honor to welcome you to Montenegro and Cetinje. This is the old royal capital of Montenegro, known for its museums, cultural institutions, and distinctive historic architectures. Some of us who are staying in this hotel have the privilege of sleeping in this distinctive historic architecture. And this is a place where many big things in Montenegrin history started and happened, and we are trying to make a big thing for the artificial intelligence also in Montenegro. We are Montenegrin Artificial Intelligence Associations. We are the largest associations of AI professionals in Montenegro. We have 50 plus active members. We've been founded in 2022, and we've had 20 plus successful projects. Our cooperation with EEML started as a fan message on LinkedIn in 2022. It continued with a coffee in Warsaw, and then our cooperation with Petar started. We signed a memorandum of cooperation with similar organizations in the Western Balkans a couple of months ago, and it is my honor to welcome some of the people from this picture also to this hall today. I'm very glad you'll be attending the conference. So our first event with EEML was the Montenegrin Machine Learning Workshop last year in Podgorica. It was the flagship EEML event. We had 8 speakers from the best scientific institutions in the world: Google, DeepMind, Oxford, Cambridge University, Nokia Bell Labs, ETH Zurich. And it was a full day of program of lectures, tutorials, and poster sessions. We had 220 attendees. So this was and is the most popular EEML workshop to date. And we've had participants from 26 countries. We have other notable projects. the AI for Healthcare School. We've partnered with the Ministry of Education for the last couple of years to do the AI part of the Festival of Science and Innovation. We host an annual AI Excellence Award where we award the best scientific work in the field of AI from Montenegrin scientists. We had Gen AI and AWS School last year. We were partners in the SEAI Summit Novi Sad. We are members of the National AI Strategy Work Group of the Government of Montenegro, and we've signed strategic partnerships with many important institutions in the country. So as the meme would say, Maya strong, Maya smart, but also Maya pretty. So here are some of the pictures from these events. The attendance is always very good, and the interest for the artificial intelligence in Montenegro is large. Let's give a round of applause for the volunteers here. They are here to help you. During this week, you can find them by the green color of the name tags. So feel free to ask them what you need. 9 people. They also helped you get your welcome bag. So have a look at it. There is a nice bottle here, some stickers, and some tips on how to spend your time, your free time in Cetinje. This wouldn't be possible without our sponsors. So great thanks to our diamond sponsors and donors, Google DeepMind, UiPath, our platinum sponsors, our gold and silver sponsors. And that would be it. It wouldn't be possible without them. Thank you so much and enjoy the conference.
Thank you very much, Mr. Milutin. Allow me now to invite a representative of our host city. Mr. Mirko Stanic is the Vice President of the Assembly of the Old Royal Capital Cetinje. Cetinje is not only the place where this school is happening, it is our host, and the support of this city is one of the reasons this week is possible at all. Ladies and gentlemen, Mr. Mirko Stanic, Vice President of the Assembly of the Old Royal Capital Cetinje.
Yeah. So I'm the one with the paper. Mr. President, distinguished organizers, esteemed speakers, ladies and gentlemen, welcome to Cetinje, a city of rich history, culture, knowledge, and a proud tradition of freedom. It is great honor and pleasure on behalf of the royal city of Cetinje to welcome you to the official opening of the Eastern Europe Machine Learning Summer School 2026. Through its history, Cetinje has been a place where distinguished scholars, researchers, and visionaries have come together. We are therefore especially pleased that one of Europe's most important events in the fields of machine learning and artificial intelligence is being held in Montenegro and in Cetinje for the very first time this year. For centuries, our city has been a center of education, culture, and social progress. Today, we have the opportunity to continue that tradition through the fields that are shaping our future: science, technology, and artificial intelligence. For Cetinje, these events represent much more than international gathering. It is a recognition of our city commitment to knowledge, innovation, international cooperation, while also serving as an inspiration for young people to develop their ideas and talents. I would like to take this opportunity to express my sincere gratitude to the organizers, the Montenegrin Artificial Intelligence Association, as well to all partners, speakers, and volunteers whose dedication and hard work have made it possible for Cetinje to host such a prestigious international event. I wish you a productive and a successful conference, inspiring lectures, meaningful discussions, new friendships, and ideas that will contribute to the continued advancement of science and technology. I also wish you a pleasant stay in Cetinje, and I hope you will take with you fond memories of our city. Welcome and thank you.
It is a great honor for the Eastern European Machine Learning Summer School, an honor for Montenegro, that our opening this morning is addressed by the President of our country. Ladies and gentlemen, please welcome His Excellency, Mr. Jakov Milatovic, President of Montenegro.
Well, I'm together with the representative of the city of Cetinje, the only one without the presentation. That basically means that I'm a politician here. So once again, welcome to Montenegro. Welcome to the old royal capital of Cetinje. And I do hope that you're already feeling here like at home. Let me also, at the beginning, before I give you my speech, I think it was a well-written speech by my great colleagues from the cabinet, but I do want to say one thing, that when I was listening to the other speakers speaking about the conference, one thing which is immediately noticeable is that the hotel was selected, very much in line with the title of the conference. So Eastern European machine learning, and look at the setup. So I've just learned that the hotel was opened back in 1986. It was the last years of the socialist period, not only in Montenegro, former Yugoslavia, but generally in Europe. It was also the year basically when I was born. So both hotel and myself are this year celebrating 40 years since the inception, and I'm also very happy that all of you came to Montenegro this year, because it's a very important year for us. It's a year in which we celebrate 20 years since we like to say have regained our independence 20 years ago at the referendum. And this city of Cetinje that you will also be able to enjoy a bit used to be a capital of a kingdom of Montenegro. Kingdom of Montenegro was one of very few countries across the world back then which was internationally recognized, and it happened in 1878 following the Berlin Congress that Montenegro, the Kingdom of Montenegro. Back then we were a kingdom, now we are a proud republic. As you can see, I don't have a crown. And so the city is not only the old royal capital, but also a modern capital of Montenegrin culture and Montenegrin tradition. So this is, I think this is really a great choice. So well done for the organizers. One thing that I also noticed missing in great CV of the person who was probably in charge of bringing the whole event to Montenegro, in Petar's CV is Montenegrin citizenship, and this is why I have initiated the administrative procedure so that Petar actually finally gets what he deserves, and that's a Montenegrin passport. So Petar, next time we see each other, hopefully I will be holding your passport. So without any other delay, let me say that it is really a great pleasure once again, and also a privilege to be here today in Cetinje with you in this rainy morning on such an important occasion. Among some of the world's leading experts, those who are sitting in the front row, and some of the future leading experts, those behind. That's usually sort of how the setup works, unfortunately, in the area of artificial intelligence. So today we are opening the Eastern European Machine Learning Summer School. It's a great title, but we are also opening something bigger, a new door for Montenegro. A door to the European and global AI community. And at the outset, I would like to thank really the organizers once again for recognizing our country as the right host for this year's edition of the school. Our country is well known for its hospitality, and I sincerely hope that all of you will experience this in this great city of Cetinje. But we want Montenegro to become also known for more than its natural beauty and warmness of its people. We want Montenegro to be known for knowledge, for innovation, for scientific excellence, and for technological progress. And this school really brings all of that to this small, beautiful nation of Montenegro. We are living through a period in which technology and AI are transforming the world faster than ever before. And they are changing the way we work, we learn, we communicate, we create, and we make decisions. And in such a world, no country and no individual can afford to remain a passive observer. But I think that you already know this. So hosting a school of this caliber is therefore a clear sign that Montenegro is not standing on the sidelines. It is becoming a place where leading researchers gather, where some important ideas are being exchanged, and where some of the defining global questions of our time are being discussed. Artificial intelligence is for sure one of those questions, and we must approach it with courage rather than fear, with vision rather than hesitation, and with the conviction that the AI should not replace human purpose, but strengthen our ability to serve it, to serve the human purpose. AI must be developed responsibly, guided by knowledge, guided by ethics. This is very important, guided by ethics, and guided by the public interest. Its true value will not be measured only by technological advancement, but by how effectively it improves people's lives. It can help us build a healthcare system where diseases are detected earlier and treatment is more precise, and this matters. It can help us create an education system that recognizes the needs and potential of each and every student in our schools, and that matters. It can support new industries, improve public services, strengthen financial security, and make our institutions more transparent, more efficient, and more accountable to the citizens, and that matters. So technology becomes progress, as you all know, only when it benefits reach our citizens. Montenegro sees artificial intelligence as an opportunity, and our vision is clear. We want to build a country where young people do not have to leave in order to gain the most advanced knowledge. And I'm sure this is the fact for many of the Eastern European countries. I'm very happy that somebody mentioned at the beginning of the conference, Eastern Europe has for long been just a source of human capital, and we want to reverse this trend. And I think it has been a time now. A country where major technological breakthroughs are not simply read about in the news, but developed in our own universities, laboratories, and research centers. A country that gives its brightest minds meaningful, demanding, and well-paid opportunities, so they can remain here, return here, and fulfill their potential here. A country that does not merely consume innovation, but creates it. Our size does not limit our ambition. In the age of artificial intelligence, a country's strength is not measured only by its population or territory. It is measured by the quality of its knowledge, the courage of its ideas, and the speed with which it can turn those ideas into results, meaningful results for the benefits of the people. And that is where Montenegro can compete. Therefore, let this school be more than a one-week event. Let it be a genuine beginning for Montenegro as well as for all of you here today in Montenegro. Let it be a turning point that helps make Montenegro a country where world-class AI experts do not come only to teach, but also to live, to research, to invest, and to create. Let it be a country that develops its own leading experts, attracts international talent, and builds partnerships with the best institutions in Europe and beyond. And let it send a clear message. Montenegro is ready to learn. We are ready to contribute, and we are ready to take our own place on Europeans' technological map. The future will not belong to those who wait for change. It will belong to those who understand the change, who are able to shape it, and who are able to use it responsibly. And Montenegro must be among them. Thank you very much.
Thank you, Mr. President, for your inspirational words and for your support to this school. That brings our opening ceremony to a close. Thank you all for being here this morning. We now move directly into the first lecture of EML 2026. Welcome to Cetinje, welcome to Montenegro, and welcome to EML 2026.
We have an event with but I think it was
Okay, so we will be starting in a couple of minutes. So, people should slowly try to make their way back in. I'll
You've just reminded, well, it's still tomorrow the first one, right? I'm planning to the right, I'm not planning to Friday, so there's instead of anywhere. There's two papers. But I have a theoretical.
Yeah, should I? Okay, okay. Cool. So if everybody could come in the room and take a seat, we're going to be starting soon. Good morning, everyone. I'm Razvan. I'm one of the organizers of the summer school. Been organizing it with Viorica since 2018. I'm just gonna give like a short intro with some like admin slides that didn't make sense to have them in the original introduction, and then introduce Sarath, who is going to be our first speaker. So just very quickly, you can find the agenda for the summer school on the website, eeml.u/program, and you can kind of have a sense of what's going on. So today, I think actually the next, no. Today we'll have Sarath and we'll have Sander, and we're going to have the, Phil. And you can see the whole agenda over there, and sort of the kind of sessions we're going to have at the school. So a lot of the communication is going to happen over Slack. So please try to check Slack from time to time. We'll have the slides channel where we will ask the speakers to put their slides up so you have access to them. We have a memes channel where feel free to add your memes. If we usually give a prize for the best memes award during the gala dinner, so there is a reason to interact with that. And the introductions channel, and there's going to be a lot more channels. But yeah, do check Slack. I think that's. Do we have Slido set up? So Slido is not really set up yet. Hopefully it will be in a few hours, or if not tomorrow for sure. But from tomorrow onwards, we'll try to use Slido to collect questions. For the people that are here, just raise your hands and we're going to take questions live. It's sort of the easiest and simplest, but there are some folks that couldn't make it to the school, unfortunately, for visa issues and other things, and other kinds of people that are online, and we'll try to be as inclusive as we can and give them a chance to ask their questions. You can go on eeml.u/live to get sort of the live stream of the event. But hopefully you'll not do that and actually come to the room. The whole point of the school is to be here, interact with people and talk, not to be in your room and just sort of watch. You could have done that from home. We have a code of conduct, so you can go on the website to read it. It's in line with the code of conduct from NeurIPS or EEML or iClear. If you've been to any of those conferences and seen, it is very important to us. The whole point of the school is to create an inclusive environment, so yeah. please be aware of that. And if you notice anything that makes you feel uncomfortable or any violation of the code of conduct, please come talk to us. There's emails you can send to whoever you feel more comfortable to send an email to. But yeah, just to say, we're taking this thing quite seriously, and we do hope that everyone is here for the same reasons to learn, to discuss, to make to network and meet new people. So next lecture, we're going to have Sarah Chandar, and after that, Philip and Sander. I think this is my last slide, right? And with that, I'm going to also jump in introducing Sarah. Sorry, he's the next speaker. So Sarah Chandar, he finished his PhD at Université de Montréal under Yoshua Benjo and Hugo La Rochelle. And after that, he's been a professor at Polytechnique de Montréal. I don't know how the Polytechnique de Montréal, and I think you're also affiliated to them now. And also a core member of the MILA, Quebec Institute of Artificial Intelligence, which probably most of you have heard. He's been doing work in a lot of fields. He has quite a big lab, if you ask me, that spans reinforcement learning, LLMs, continual learning, and there's a fourth, science, AI for science, if I'm not wrong. With Sarah, we've been organizing a conference on lifelong learning that's been going on for 4 years, 5 years. That this year is going to be in Romania, Bucharest. So, it could be a nice place to go and see. And yeah, with that, I'm going to let Sarah start with the introduction to deep learning. It's okay like this. Check. Got something? Check. Yeah, thanks, Ross. Do you have help? Yeah. Or put it to the front side. Here it's
Just give me a second. Okay. Sure. Thank you for the introduction, Razvan. I'm really happy to be here for this edition of Eastern European Machine Learning Summer School. And this is my first time attending EEML, and I'm really excited to be here. Hello, everyone. So let's get started with the first lecture of this summer school, which is an introduction to machine learning. So I will be mostly writing for this lecture, like instead of using slides. You're going to see a lot of slides for the whole week. So I hope you can bear with me writing. And when I thought about like what should be a good introduction to deep learning, especially for a summer school where you're going to learn a lot of deep learning for the next week or so, right? I decided to do a talk that is a bit of an overview of like deep learning, but also a bit of I would say a history lesson, and probably like a better title for like what I'm going to talk today is like neural networks past, present, and future. Like I want to start with like how the field started and like where we are, and go all the way to where we are going to be in the next decade or so, right? So before I get started, so how many of you already have a good background in deep learning? Well, I would assume that it's a lot. Okay, it is a lot of people, but there are still people like who are a bit new, right? So I hope that everyone learned something new from this lecture. So that's the goal. So even if you know deep learning, like just bear with me for the first 20, 30 minutes, but you're going to learn more interesting things as we progress in the lecture. Okay, so to get started, I want to introduce the problem of prediction, right? Which is probably the fundamental problem that we deal with in machine learning, right? I'm going to start with a simple prediction task just to set the stage and have the discussions going. So the problem that I'm interested in is given some input, let's say X, which is d-dimensional, I'm interested in predicting some target, which is binary. Okay, so it's either 0 or 1. And the goal is to learn the function f or f star that generates t given x, right? So this is the classical problem setup for prediction, and you can think of many practical applications that fit into this category, right? Now, typically when you learn a function to make meaningful predictions, so you will often start with a training data, right? So let's say I have a bunch of n examples, xi, and I'm going to use these examples to learn an approximate function f that approximates f star, but as good as possible, right? So the goal of learning is often this, so given the training data, I'm interested in learning a function f such that given a new unseen x, right, f can predict the corresponding t as accurate as possible, right? So we are not just interested in fitting the data, we are interested in fitting the data in such a way that given a new x, we can predict t as accurately as possible. That's when the machine learning model is really useful, right? So it's more useful when you can predict unseen data. So here the idea is to learn any function f which can do this task of predicting y given an unseen x, and we would often call this as generalization in machine learning. Okay. So if you think about it, all of machine learning is about finding functions that are generalizable, right? Now, we often have to start with some assumptions while learning. So the most common assumption that you would see that almost all the machine learning algorithms use is called the IID assumption, which basically says that the data is independent and identically distributed. So this is necessary, if you want to learn from a training data and hope that the model actually generalizes to test data, right? So we will talk about the limitations of these assumptions towards the end of the lecture, but for now, every algorithm that we're going to develop today, so we'll make this assumption that the data is independent and identically distributed. Okay, so now how do we learn these functions from data, right? So this is what we call function approximation. So if you think about it, all of machine learning is really coming up with good function approximators, okay? So that approximates the original function f star that we care about, right? So let's start with the simplest possible function approximator possible for this particular prediction setup, right? So I have a binary prediction, right? So binary class prediction, and the simplest function approximator I could think of is what people call logistic regression model, right? So basically you take the input x, you make linear projection of this data, and because we are interested in something that is binary, like, so I'm going to put a sigmoid function on the top, which has the range of 0 to 1, right? Like, so the sigmoid function is 1 by 1 plus e power minus x, which has a range between 0 to 1, right? So this is the simplest possible function approximator you could think of. Like, so it's a linear model followed by a logistic regression function, right? So we are going to call these W0 and W as parameters of this model. And learning typically involves learning these parameters from the data. Like, so you have data and you have this model, and the goal is to learn the best possible W0 and W from the data so that you can be better in generalization, right? Like, so the W0 that you see here is the bias of this model. And for all the discussion today, I'm going to bring the bias inside the parameter. Like, you can just put a W0 times 1 and bring it inside, right? Like, so then this becomes simply y is equal to sigma of W transpose x. Okay, so what does the sigma represent, right? Like, so it's a value between 0 to 1. So I can consider this as essentially the probability that the class is 1 given x. Like, if I have class 0 and class 1, and then 1 minus y becomes the probability that class is 0, right? So we can also think about this simple logistic regression model from graphical perspective. Okay, so like, you have the input features x1, x2 to xd, right? Now, you integrate these input features by multiplying them with w1, w2, all the way to wd. You can also put a bias here, and then you apply the sigmoid activation function, and then you get the output, right? Like, so this is the graphical representation of the logistic regression model. Okay, so I want to highlight that the name logistic regression itself is a misnomer in the sense it's not a regression model, it's a classification model, but it's basically a linear regression followed by the logistic function. So hence the name, right? Like, so anyways, like, this is the simplest possible classification model that we could think of. Now, the next question is, how do I learn the parameters W0 and W for this model, right? So, which is basically this idea of training your model. So how to train your model? Like, so we start with the training data, which is a bunch of examples that someone has given. And we also have the model, which is, in this case, sigma of W transpose x plus W0, right? So how do we learn the model? So typically, to learn the parameters of the model, you should have some objective function that you're trying to minimize or maximize, right? So we will often do minimization. Okay, so if you have, even if you have a maximization problem, you could just convert it into minimization by putting a minus in the front. So what we are going to do is to minimize some loss. So how do you minimize the loss? You're going to use some optimization method to minimize this loss, right? Like, so you need an optimization method. And that's going to do argmin of the loss with respect to W, right? So even though this looks very elementary for this class, like, so like, I would still go through the idea of objective functions and minimization for logistic regression, because it's going to really set the stage for like how to extend this idea to more complex architectures like neural networks, right? So what would be a good objective function for the binary classification prediction problem that I have, right? Like, so like, given that this is a probabilistic system, like, it makes sense to say, okay, I'm interested in maximizing the probability of t given x. Okay, now you have n examples, so you're going to maximize the probability, the product of probabilities of n is equal to 1 to capital N, P of Tn given x. Okay, so this is called the likelihood or conditional likelihood, right? And what is the probability of t given n? So if I write it explicitly, so it's going to be y of n whenever Tn is 1, and it's going to be 1 minus y of n whenever Tn is 0, right? So this is just a compact way of writing the probability for all the n classes that we have seen in the training data. Now this is maximization. Like, as I said, like we would convert all these maximization problems to minimization problems. So I'm going to do my minimization of minus of whatever we had before. Okay. 1 minus y of n, 1 minus t of n. So this is called the negative likelihood. Now, when you multiply n values, which are all between 0 to 1, you will get into numerical issues. So we would often convert this into the log space so that the product becomes like sum, right? So the final form of the objective function is minus summation over n is equal to 1 to capital N, Tn ln y plus 1 minus Tn ln 1 minus y, right? So this is one of the most popular objective functions, like you might have seen several times, like so, which is basically the negative log likelihood, right? Okay, so far we have the data, we have the simplest possible model that we could think of, and we also have the objective function that we want to minimize, right? Like, so what is the next step? So the next step is to optimize this objective function, like find parameters w, which minimizes this loss function, right? Like, which is basically what the optimization method would do. And like in machine learning, the most common way to optimize functions is by using gradient descent. Okay. So in gradient descent, you'll typically start with some random initialization of the parameters. You'll compute the gradient of the loss function with respect to w. So the gradient is going to tell you the opposite direction of the minimum. So what you will do is w is equal to w minus alpha dou obj by dou w, right? So the alpha here is the step size or learning rate, and this is your gradient. So you find the gradient, you want to go in the opposite direction to the gradient so that you can reach the minimum, right? Like, for example, like with the logistic regression case, things are convex. So your objective function would look nicely. So it will look like a ball. And with a convex function, you have a unique minimum, right? So let's say you start with some random initialization, like the random initialization puts you here. When you compute the gradient is going to show you this direction. Now you want to go in the opposite direction of the gradient. You don't want to take two big steps, then you might diverge, right? Like so which is why we have the alpha. The alpha really controls the step size of the gradient, like of the gradient descent, right? Like so, with tiny steps, you're going to keep moving until you reach the place where the gradient becomes 0. So then you have reached the minimum, right? So this is the idea of gradient descent. Now, there are many, many flavors of gradient descents like that people use. Like, so like if you use the entire data set to compute the gradient, like so when you're computing the gradient with respect to the total loss, then you get full batch gradient descent, right? You could also take one example and compute the gradient. This is going to be noisy, but sometimes this noise is extremely useful. So this is called stochastic gradient descent. So for example, let's say you have a non-convex loss function, like which looks something like this, right? So if you start from here and you use the full batch gradient descent, then for sure you're gonna get stuck in this local minimum, right? On the other hand, like if you use stochastic gradient descent, because the gradients are noisy, right? So it might be the case that your first gradient points you here, so you're here, your second gradient may point you here. Well, this is just hypothetical, but the point is these stochastic gradients could help you to skip the local minimum and potentially reach a better minimum, right? Now, probably the most common version of stochastic gradient descent that we all use is called mini batch gradient descent, which is basically this idea of taking a small mini batch of examples instead of just one example so that you can also use GPUs better, right? Like, so it's not the only benefit, but there are like other benefits as well. Like, but probably the most common optimization method that people use is some form of mini batch gradient descent. right? Okay, so now let's try to do gradient descent for logistic regression, okay? So if you remember, the logistic regression function looks something like this, right? Like, so you have yn, which is sigma of some a of n, like where a of n is w transpose x of n, right? And I'm interested in minimizing this function, right? Now, how can I compute the gradient of this objective with respect to w, right? Now, if you look at it, you don't see w in the function that you're trying to minimize, right? Like, so essentially the function that you're trying to minimize is a function of y, which is the function of a, which is the function of w, right? So we are going to use the idea of chain rule. So I can write this gradient as dou obj by dou yn. I first differentiate the objective function with respect to yn. Then I differentiate this with respect to an. Then I differentiate this with respect to w, right? So this idea of applying chain rule to differentiate through a series of functions is much more general than like logistic regression. Like, so we're going to keep seeing this for even more complex architectures that we will see throughout the summer school. Okay, so the reason why I still want to do the simple logistic regression case is simply because you can learn all these foundational ideas like with much cleaner structure. Okay, so now let's try to do this chain rule quickly, right? Like, so first I want to do dou obj by dou yn. Like, so this is basically differentiating this function with respect to yn, right? Like, so I'm going to get minus tn by yn plus 1 minus tn by 1 minus yn, right? Like, I think it's minus probably. Sorry. Oh, sorry, it should be plus. Okay, so this is 1 minus tn times yn minus tn into 1 minus yn by yn into 1 minus yn, which is yn minus t of n by y into 1 minus yn. Okay, simple algebra. Similarly, I can do dou y by dou a, right? Like, so dou of dou an of sigma of an. So when you differentiate a sigmoid function, you're going to get sigma into 1 minus sigma. So it's going to be sigma of a of n minus, sorry, 1 minus sigma of a of n, which is basically y of n into 1 minus y of n. When you differentiate the activation function with respect to w, you're going to get just x of n. Okay, so you put all these three things together in the chain rule. So you will get y of n minus t of n by y of n into 1 minus y of n, y of n into 1 minus y of n into x of n, right? Like, this things cancel. So the final gradient that you would get looks something like this, right? So now we have the gradient, right? Like, so we started with logistic regression model. We have the data, we have the objective function, we know how to compute the gradient. Just apply gradient descent. And when the gradient descent converges, like, you are going to get the best possible solution that you could achieve with the logistic regression model, right? Now, the next obvious question is, what can we model with this logistic regression model? Like, so can I model all sort of prediction problems? Like, so like, what can I model with logistic regression, right? So to understand this, like, we should know how the decision function for logistic regression works, right? So if you think about it, for a simple logistic regression model, the decision boundary is at 0.5, right? So when the prediction is at 0.5, you're between class 0 and class 1, right? Like, if it is above 0.5, it's class 1. If it is below 0.5, it's class 0, right? Now, let's try to visualize this decision function geometrically, right? Like, so like sigma of w transpose x is 0.5, so which means w transpose x is sigma inverse of 0.5, right? Or in other words, w transpose x is some constant. So this is just an equation of a line, right? So this means that if I use logistic regression to fit my data, like, I will learn a decision function that looks like a line. So if your data looks something like this, right, then logistic regression is a perfect classification algorithm because you can find a line that separates the data perfectly, right? So these kind of problems are called linearly separable problems. And for linearly separable problems, something like logistic regression, which has a linear decision boundary, is enough, right? Now, what if my data looks something like this? Can I still use logistic regression? I could try using logistic regression, and logistic regression would probably attempt to draw some line that fits the data better, right? So we don't know which line it will converge to, but it's just going to converge to a line that tries to separate crosses from circles, right? Now, if you think about it, what would be the good decision boundary for this particular case, right? In this case, if I can somehow draw a circle that separates the crosses from blue, then that's the best possible decision boundary that I could have, right? Now that we know what kind of functions logistic regression can model, so we can confidently say that logistic regression basically cannot solve this kind of problem, okay? So the kind of algorithm similar to logistic regression, which basically which looks like it is nonlinear because it has a sigmoid function, but in reality, it is just doing linear decision boundary, right? So these kind of models are called generalized linear models. So they are still linear with respect to their decision boundaries, right? And they're not going to be very useful when the data is not linearly separable, okay? So this is the idea that is very clear for us now. Interestingly, this was not clear in the initial days of machine learning when people were still trying to formalize what is learning. Okay, so I want to highlight this infamous XOR problem that was popularized by Marvin and Minsky in their book called Perceptrons, which was written in 1969. For pedagogical reasons, I started this lecture with logistic regression, but perceptrons are kind of like logistic regression in the sense they are simple linear models, but they just have a different objective function to minimize. Okay, so for the purpose of our discussion, you can consider them to be similar to logistic regression. Okay, so in this book by Marvin and Minsky, so they introduced the XOR problem, if you have already done a little bit of Boolean algebra, you know what is XOR, right? So if you have not done Boolean algebra before, XOR basically means exclusive OR. So what does it mean? When both x1 and x0, x1 and x2 are 0, the XOR is 0. If one of them is 1, then you get a 1. If both are 1, you get a 0. Okay? So this is a really, really simple problem. Okay? And 60s are the time when people were hyping perceptrons too much. Just to give you the timeline, so perceptrons were introduced around 1957, and logistic regression were introduced around the same time. And people were thinking that they could solve really complex problems with perceptrons and logistic regression. Okay, Minsky and Papert, this is Minsky and Papert. So Minsky and Papert, they did a more rigorous analysis of what these kind of models can do. And they showed that logistic regression or perceptron cannot solve even this simple XOR problem. So now we can try to understand why XOR is not solvable by logistic regression, right? So if you plot the XOR function, it's going to look something like this. Okay. So now we know that this is not linearly separable, right? So if I have to solve the XOR problem, I need to come up with a decision boundary that looks something like this. However, if I use perceptron or logistic regression, the decision boundary is going to be something like this, right? So you cannot solve this problem. So their conclusion was these models are limited in capacity, in capability, right? So they cannot solve really complex problems. And we need to do better job in coming up with better architectures that would solve these problems, right? So this, however, kind of backfired in the literature, like in the history. Like so because perceptrons cannot solve XR problems, like people thought this whole idea of gradient-based learning is probably hopeless. Okay, so people stopped working on like improving perceptrons or architectures like perceptrons for solving this kind of problem, right? So just to give you the timeline, like Rosenblatt introduced perceptron in 57, and logistic regression was introduced by David Cox in 1958, and the perceptron example, like the counter example, came in 69. Okay, now we're going to see how to make this work, right? Like we're going to see how to solve the XR problem, like very soon. But before that, like I want to highlight that this idea of hype for AI is not new. So this is like a 1958 New York Times newspaper article, which was basically explaining what perceptron is doing. Okay, so I will share the slides later. Like you can read the news later. But this basically hypes perceptron by saying perceptrons can speak in the future. Perceptrons can like solve really complex problems. Like it is almost like an AGI, right? Like so, very similar kind of discussions to the kind of discussions we have now with LLMs, but people were doing this even like with perceptrons. Okay, so now how do I solve this XR problem? Okay, so if you think about it, like again from the graphical perspective, right? Like this is what is happening here. Like so, I took my x1 and x2, I multiply that with w1 and w2, and then I add a sigmoid function, which gives me the classification, right? Now, we know that logistic regression can only solve linearly separable problems. And we also know that XR introduces this representation space, which is not linear, right? So let's say I really have to use logistic regression, and that is the only algorithm that I know, right? So what can I do? Like I can try to change the representation of this XR problem into a new space such that the problem becomes linearly separable, right? So here is an example. Like so, I could construct these new functions. Like the first function is and of x1, x2 bar. The second is and of x1 bar, x2. If you don't know Boolean algebra, just don't worry about what these functions are. Like so, these are just some functions which converts the XR into okay. Okay, so, well, I should have, okay, so maybe let me draw the figure. I think my table might be wrong. So it converts the features into such a way that the zeros actually collapse. Okay, so this means that I can just draw a line and I would be able to solve the XR problem, right? So what have I done here? Like, so I took x1 and x2, I constructed phi1 and phi2, and I'm using the same perceptron or logistic regression algorithm to solve the problem, right? Now, if you think about it, like, so what I did here is I took the data and I constructed some nonlinear representation of the data, right? Like, so we're going to call these nonlinear basis functions. Then I used my plain old generalized linear model to make the prediction, right? So this is one way of making linear models nonlinear. Like what I did is I took the data, which was in some input representation space. I converted it into some nonlinear representation space in such a way that the problem becomes linearly separable, right? So now the graphical way of thinking about this is like I took x1 and x2 and I constructed phi1 and phi2, right? And then I fed phi1 and phi2 to the classifier, right? In this case, I actually spent some time to come up with these phi1 and phi2, right? So this is what people often call feature engineering. Like, so what I did here is feature engineering because, feature engineering because I carefully constructed these features phi1 and phi2 in such a way that the problem becomes linearly separable, and I can use my logistic regression function, right? So this is easy to do for XR. Now think about a complex computer vision application. So you might have a large input representation space. Like, so how do you come up with features in such a way that the problem becomes easier for generalized linear models to solve, right? So this is going to be intractable even if you have 10 variables or 20 variables. Like, think about having thousands of features and you want to come up with new features which makes the problem simpler, right? Like, so this is extremely hard, but this is exactly what people were doing in, let's say, 80s and 90s, like, so where people were coming up with like more and more like complex features like that would make the learning problem easier so that you can still use simple learning algorithms like perceptrons and logistic regression, right? However, given that we do machine learning, like, so the obvious question that anyone should ask is like, so why are we handcrafting these features? Like, so can we also learn these features directly from the data, right? So previously I said, oh, we are interested in learning some prediction task from the data, right? Now I don't have good features for this prediction task. So can I also learn the features from the data itself, right? Like, so which is basically the question of representation learning. So can we also learn the representation, right? So this is what people call representation learning, okay? So in representation learning, like, so we start with the data, we learn some representation for the data that is useful for the classification task, and then we also learn the classifier, okay? Now, if you look at this blue box, right, like, so I somehow handcrafted these features and fixed it, right? Instead, you could think about having some linear projection here with some nonlinearities on the top, which you are learning from the data, right? Like, so that is what we're going to do next. Like, so what we're going to do is we are going to start with the data, which is x1, x2, and I'm going to learn the projections, phi1 and phi2, okay? To learn the projections, we're going to use some parameters. Let's just say v1, v2, v21, v22, right? So then I have a classifier, right? So here we are going to call this our input layer, which is basically the data that you're feeding into the system, right? So then you're learning the projection, right? Like, so let's just call this the projection layer, okay? So the projection layer is simply some linear projection followed by nonlinearities, okay? So then you have your classification layer. So if you think about it, the end goal is still classification, right? Like, so in the end, I care about coming up with a system that has, let's say, 98, 99% accuracy, right? I don't really care what kind of representations that I'm learning, right? So in some sense, learning representations is only like the intermediate step that helps you with the final goal, right? Like, so for this reason, like, we are also going to call this layer as hidden layer, okay? Like, simply because, like, we don't, well, not that we don't care, like, we do care about what it learns for interpretability reasons, like, but typically we don't care what goes in the hidden layer. Like, so what we care is like how good is the final prediction, right? So this architecture looks a bit more complex than logistic regression, right? Like, so now we have multiple layers. So you have the input layer, hidden layer, and the classifier, right? Like, so this is called a multi-layer perceptron. Again, this is another like improper name in the sense this is not really a perceptron, like, so, or multiple layers of perceptron, right? Like, so it's basically some linear layers followed by a logistic regression layer, okay? So you can call this the multi-layer perceptron, like you can also call this neural network, mainly because it looks like a neural network. Like, so each of these units can be considered to be neurons, and like, so you have this architecture which looks very much like the real neural network, right? Like, so, but I don't like the analogy between artificial neural network and biological neural network, simply because even a single biological neuron is much more complex than a multi-layer perceptron, okay? So it's the inspiration, let's say, but this is not really artificial neural network in any ways. You can also call this architecture as a feed-forward neural network. It's feed-forward because the computation goes from left to right, right? So which means you can imagine recurrent architectures where the computation could flow in both directions. You also call this fully connected neural networks, which means we could design neural network architectures which are not fully connected. Okay, so now a couple of important points worth discussing here. So before that, let me draw a simpler version of the graph so that it's easy for us to keep drawing the architecture. So this is the same neural network architecture. I'm just drawing it in a different form. So I have the input layer X. You project it with W1, you get H of X. And you project it with W2, you get Y. Okay, so if I write the equation for this, it's going to be A of X is equal to W1 transpose X plus B1. Okay, so we are going to call this the pre-activation. Okay, just give me 1 second. Okay, I forgot to add my charger. Okay, so this is my pre-activation. So then I have H of X, which is G of A of X. Okay, where G is typically some nonlinear activation function. Then finally, we have Y, which is some output function of W2 transpose H of X plus B2. Okay, so this is also another activation function. Okay, now, can someone tell me why we need a nonlinear G here? So why can't I just do a simple linear projection for learning the representation and then do logistic regression on the top? Yeah? Yeah, so the composition of linear function will be another linear function, right? So there is no point in having two separate layers, right? So we will fall back to the linear models again, right? So if you have a linear projection for representation followed by logistic regression, you still have a generalized linear model. So there is no point in having this extra layer, right? However, this is completely not true, mainly because the way in which we implement things in computers, so even if you have two linear projections, it acts a little bit like nonlinearity, okay? But that's not a very useful nonlinearity. So we should add some nonlinear activation function G, okay? Now, what kind of activation functions we could use, right? So for G, so the two common activation functions that people use are sigmoid and tan H. Okay, sigmoid is basically 1 by 1 plus e power minus a. Tan H is basically e power 2a minus 1 by e power 2a plus 1. Okay, so they both look similar. It's just the range is between 0 to 1 and minus 1 to 1. Okay, now we will see many more activation functions very soon. But for now, let's say we put a sigmoid or tan H for our hidden layer. Okay, so then what about the output activation function? So what kind of activation function that I could use for output? So if you are doing simple regression task, then you can just use the identity function. Okay, if you're doing binary classification, then you could use sigmoid activation function. So this is for binary classification, right? And if you have a multi-label classification function, you could use the generalization of sigmoid, which is softmax. Okay, this is when you have multi-label classification. Okay, so now that we have our neural network architecture, so which starts with the input, has some parameters for representation learning, some with a sigmoid or tan H, then some parameters for classification, followed by a sigmoid, right? So this is how the neural network looks like. So how do I train this model? So the nice thing is we have already learned all the machineries with logistic regression. So you can just simply do gradient descent here. And we also know that you can do gradient descent by computing the gradients using the chain rule, right? So if you want to learn the gradient, if you want to compute the gradient of the loss with respect to W2, just apply chain rule from the output to W1 or so W1, W2, right? If you want to learn the gradient of the loss with respect to the V matrix, then just do the chain rule all the way to V matrix, right? Now, you can do this in a naive way, or you could also do a much more efficient dynamic programming implementation of chain rule, which is called backpropagation, okay? So the idea of backpropagation, which is basically to compute gradients in a chained function in the most efficient way, I would say has been reinvented several times in the history. So I think it's more accurate to say it was invented the final invention was by Rumelhart, Hinton, and Williams, in 1986. So this paper really popularized the idea of using backpropagation. But backpropagation was invented several times, several decades ahead of 1986 paper. One of the most notable papers is I think Verbo's PhD thesis from 1974. But I highly encourage you to read this article by Schmidover, which explains the history of gradientism. Okay, so it's backpropagation. So this is something that people have discovered many times, and for a good reason, right? This is such a fundamental algorithm that you will eventually stumble upon this, if you are trying to solve the learning problem. Okay, now for the logistic regression case, I did the gradients manually, right? So in theory, I could also try to do the gradients manually for this. That's going to take me an hour, and I'm already running behind in my schedule, right? But I want to highlight that this is what people were doing 10, 15 years back. Okay, so people will come up with a multi-layer perceptron architecture and try to compute the gradients by hand, and then implement this in C or C++, right? And this was a tedious process. Plus, it also requires a lot of effort. There's more reason for mistakes, etc. Right? The good news is you don't need to do that now. I don't think the current generation students even learn to implement gradient descent from scratch, which I strongly encourage you to do at least once. Okay, so you will learn a lot by trying to implement backpropagation. But right now we have automatic backpropagation, in the form of auto differentiation. We have a lot of frameworks. I think the most popular ones right now are probably TensorFlow, PyTorch, and JAX. But I want to highlight that this has a long history. Okay, so this starts with the basic torch implementation by Corbett and his colleagues in 2002, and followed by Tiano from Yeshua Bengio's group in 2007, 2008, which I think Razwan was also one of the main developers of this framework. Then Caffe, then TensorFlow, then PyTorch, now JAX, and probably now there are many more other frameworks that exist, right? So we kind of take these frameworks for granted, but I want to highlight that this is not what people had access to probably 10, 15 years back. Okay, so this really accelerated the research in deep learning, as we are going to see in the second half of this lecture. Okay. Okay, so now that we have a neural network, it makes sense to ask what kind of functions a neural network can model, right? So I have taken this example from Hugo's lectures. So here you see a simple neural network which has step function as the activation function. Okay, so this first neuron has this activation function, right? Which looks like this. The second neuron has this activation function, and when you combine these with another layer, you get an activation function that looks like this, right? So this is not linear anymore. So when you combine a bunch of non-linearities in a linear way, you actually get a non-linear function, which is intuitive, right? Now, here is another example. So here I have 4 sigmoid functions, right? So when I combine these 4 sigmoid functions together, I have this blob kind of activation, like decision function, right? So this is something that I could use for the circle example that I had before, right? Now, here is the most complex example. So in this case, I have a decision boundary, which is separating region 1 and region 2. And within region 1, I have another region 2. And within that, I have another region 1, etc. Right? So it looks like with a neural network, I can model any function that I'm interested in, like however complex it is, right? So it turns out to be true. So this is the universal approximation theorem, like by Harnick, 1991, which says a single hidden layer neural network with a linear output unit can approximate any continuous function arbitrarily well, given enough hidden units. Okay, so the word given, the phrase given enough hidden units is the catch here, like because it turns out that like if you want to model a complex problem, as the complexity grows, you would need an exponential number of hidden units like in your layer, like to solve this problem. Okay, so once you start having exponential number of units, then you will get into the problem of overfitting, and we don't know how to solve that efficiently. Like, okay, so for that reason, like even though this looks like a very attractive theorem, like it's in some sense useless too, because it just says that in theory neural networks can model any function like very well, right? Like, but it doesn't give you the learning algorithm to do that. Okay, so this is something that I want to highlight. So there is a difference between expressivity and learnability. Okay, so this theorem says that neural networks are expressive enough to learn whatever you want, like a single hidden layer neural network. It doesn't tell you whether you can actually learn with, for example, gradient descent, right? It might be the case that gradient descent can never find those functions. It might be the case that we need a totally new learning algorithm to find these weight configurations, right? Like, so we just know that this weight configuration exists somewhere. We don't know how to reach there, right? Now, this looks like we are kind of stuck, right? So we started from logistic regression. We progressed to a single hidden layer neural network. And even though the single hidden layer neural network is theoretically expressive enough, like it is just that we cannot learn much more complex functions using a single hidden layer neural network. So like, how do I address this issue, right? Like, so now intuitively, like one thing that we could try to do is like, right now we are doing one layer of nonlinear projections, right? Like I start with the data, I project it into some nonlinear representation, and I'm trying to do the classification, right? Like what if I do this nonlinear projection several times? Okay, so I start with the data, I project it into some nonlinear space, then I project it into another nonlinear space. Now this is a function of the previous nonlinear representation, right? Like, and I do this a few times. Hopefully I have like a super complex nonlinear representation that the problem becomes easier, right? And also the hope here is I don't need exponential number of units. Like, so I can just do this with limited number of units because like I'm kind of trading the width of the neural network with the depth, right? So this is the idea of deep neural networks, okay? So in deep neural networks, typically you will start with X and you will do a series of nonlinear projections, okay? So here is a cartoon illustration of what could happen, right? Like, so let's say I start with data that looks like this, okay? So the first nonlinear projection could separate the data a little bit. The second nonlinear projection could separate it a little bit more. And the third nonlinear projection could just separate the data enough that I can fit a logistic regression on the top, right? So this is the hope. And the beauty of machine learning is like you are actually learning all these representations in an unsupervised way. Like, so we are not teaching the machine to learn this representation here, learn this representation here, right? Like, so everything is data driven. So the hope is when you do gradient descent with a deep neural network like this, like you will see these representations emerging as the result of gradient descent. Is that clear? So this is what people thought would happen in 90s, okay? So several people tried training 3-layer networks, 4-layer networks, 5-layer networks, etc. And interestingly, they were not seeing as good results as they expected to see. Okay, so like in a lot of cases, a simple 1-layer neural network was doing better than a 3-layer or 4-layer neural network. So this is puzzling because like the hope is with more nonlinearity, like you should be able to learn better, right? But that was not happening. And this was also the time SVMs were introduced. Like SVMs came with much more nice theoretical guarantees, and like libSVM really popularized the idea of applying SVM for any application that you could think of. And somehow again people stopped thinking about neural networks. Okay, so people started focusing on algorithms like SVMs, decision trees, which were much more tractable and easy to train, right? And showing results. So, however, some people still were trying to make these deep neural networks work, right? So now let's try to understand why it is difficult to train this neural network, right? So let's take this example architecture, which has two hidden layers, right? And let's say I want to do dou E by dou W1. I want to compute the gradient of the loss or the error function with respect to the first parameter matrix, right? Now, if I apply chain rule, this is going to be dou E by dou Y by dou H2, dou H2 by dou H1, dou H1 by dou W1. Sorry, dou W1, right? So here, let's just take this dou H2 by dou H1. Dou H2 by dou H1 is simply dou H2 by dou H1, dou by dou H1 of sigma of W2 H1 plus B2, right? So when I differentiate this, when I differentiate the sigma, I will get a sigma dash. And when I differentiate the linear layer, I would get W2. Okay. Now let's try to look at the range of sigma dash and W2, right? So typically, when you have a sigmoid, the range of sigmoid is between 0 to 1. So the range of sigma dash is actually between 0 to 0.25. Okay. So this is going to be less than 0.25, right? And this is actually close to 0 because we initialize close to 0, right? Now, this whole thing is actually going to be close to 0, right? Now, this is for one dou H2 by dou H1. Now, think about having more layers, right? So when you have more layers, let's say you have 5 layers, then dou E by dou W1 is going to be dou E by dou Y by dou H5, dou H5 by dou H4, dou H4 by dou H3, dou H3 by dou H2, dou H2 by dou H1, dou H1 by dou W1, right? So you see there are many terms that are kind of close to 0 or less than 0.25, right? So essentially what happens when you stack multiple layers is the gradient that is going to the bottommost layer shrinks, and it just vanishes. Okay, so this is called the problem of vanishing gradient. Okay, somehow it took people a decade to figure out that this is what is happening. Okay, so now we learned this in 5 minutes. Somehow this optimization issue was always overlooked, and at some point people figured out, okay, so the real problem is gradients are vanishing. Okay, now that we know the problem, how can we fix this issue? Okay, so how to fix this issue? So that is the whole field of deep learning. Okay, now how to train deep neural networks? So we are going to see several fixes for this problem of vanishing gradients. Okay, I want to start with the most historical solution, which is this idea of greedy layer-wise pre-training, which was introduced by Hinton et al. 2006, and in the RBM sense, and it was brought to autoencoders by Bengio et al. Okay, so what is greedy layer-wise pre-training? This is a really simple idea. We don't use it nowadays, but I still want to start with this because this is kind of the precursor for the pre-training that we are doing with LLMs. Okay, so what is greedy layer-wise pre-training? So we are going to start with the data X. Okay, and I'm going to learn a simple autoencoder of this data. Okay, an autoencoder is like a MLP which takes the data, it projects into some hidden representation, and projects it back to the same X. Okay, so I start with X, I project it to H1, and then I just learn the same X back. I can just tie these two matrices if I want. Okay, so this is an autoencoder. Okay, so autoencoder is not learning to predict Y from X, it is just learning to predict X from some compression of X, right? So in some sense, this is like a self-supervised learning objective, right? So you have the data X, you don't need the labels. Just take the data, learn a good compressor, and try to predict from this compression, right? So this is gonna give you some features here that are hopefully useful for other tasks, right? So the idea of greedy layer-wise pre-training is to take X, first learn an autoencoder, and once you learn the autoencoder, you are going to throw away the decoder and just take the encoder. Okay? So now I'm going to continue this process by training another autoencoder with H1 as input. So this means I'm going to train another autoencoder. So W2 transpose, right? So the most important thing here is I will be freezing this part of the network, okay? So this is frozen. I already learned W1, this is frozen, and I'm going to learn this autoencoder, okay? So once I finish learning this autoencoder, again, I will throw the decoder away. Then freeze W2 and continue this. So you can do this for how many times you want. Let's say you want to train a 10-layer neural network, you do this 10 times, okay? So then in the end, you will end up with X to H1 to H2 all the way to HK, right? So these weights are all learned by using the autoencoder, right? And then you finally add the classification layer. And now you're going to train the whole thing with the classification task. Okay, so this is the idea of supervised fine-tuning. Okay, so you see the similarities with the current LLM pre-training, right? So you do some pre-training. Here, this is called greedy layer-wise pre-training, followed by supervised fine-tuning, which is kind of similar to the fine-tuning that we do for different tasks, right? This made it possible to train deeper networks, and suddenly neural networks, like with many layers, were trainable, okay? However, can you tell me if this is really solving the vanishing gradient problem? Did we solve vanishing gradient problem by doing this greedy layer-wise pre-training? So what would happen when I do supervised fine-tuning? So when I do supervised fine-tuning with 10 layers, are the gradients going to be better? No, right? So we did not change anything fundamentally in this architecture, except for the fact that we are initializing these Ws with some better initialization from the autoencoders, right? So in practice, what happens is you will still have vanishing gradient problem with supervised fine-tuning. It is just that we don't care about it anymore because we have already learned good representations, right? In some sense, this idea is indirect, like kind of separating the representation learning from the classification. So you learn representations separately, and then you just do the classification with these learned representations, right? So this is really not solving the vanishing gradient problem, okay? However, this was good enough solution to encourage the community to start looking at neural networks once again, right? So then people really started analyzing this solution, like whether this is really solving the vanishing gradient problem, et cetera, and started developing techniques that would really solve the vanishing gradient problem, okay? So we're going to see a few such techniques today. So the first idea is to just change your activation function, okay? So if you remember, we were using sigmoid and tanh activation functions, right? So if you think about it, those are the real culprits, right? So I go back here. So we have sigmoid. Similarly, if you have tanh is between -1 to 1, and tanh dash is between 0 to 1. So these activation functions are the real reason why the gradients shrink, right? How about I come up with the new activation functions that doesn't have the vanishing gradient problem, right? So one such activation function is called rectified linear unit, or ReLU. So the ReLU function looks something like this. So it's going to be 0 in the negative phase, and it's going to be a linear function in the positive phase. Okay, this is f of x. F of x is given by max of 0, x. Okay, so the gradient for ReLU is going to be 0 if x is less than 0. It's going to be 1 if x is greater than 0. Okay, so the nice thing is when things are positive, the gradient is 1. So which means you're not shrinking the incoming gradients, like you're just passing it, right? However, the problem with ReLU is like when it is in the negative side, you have 0, and there's this possibility that like it will never come back to the positive side. So these are called dead neurons. Okay, so to address this issue, well, I think there are 10 plus variants of ReLU. Like, so the simplest is leaky ReLU, like which is something like this. Okay, so leaky ReLU is f of x is equal to max of epsilon x comma x, where epsilon is a small value, and you try to have some leaky component in the left side so that like gradients can still propagate, right? So this is one of the most popular activation function that we still use. There is a rich literature on activation functions. Like there are many activation functions, like, and some of the popular ones being swish, which is basically x times sigma x. Okay, so we know sigma of x is shrinking gradients, so we try to pass information by multiplying that with x, right? And you have things like swiglu, which is basically a swish function with a linear gating. Okay, so there are other forms of activation functions as well. Like, so this is one way to solve the vanishing gradient problem. Like, you just make sure that gradients like can flow better, right? So what are the other ways, right? So the third method to solve vanishing gradient problem is to do better initialization to begin with. So activation function helps with the sigma dash part of the vanishing gradient problem, right? Like, but then you also have the W part, right? Like, so like how to initialize better. I think there is a lot of theory now on better initialization for neural networks. Like, so like typically people do things like savior initialization for things like tanh, sigmoid, linear layers. Okay, so this was introduced in 2010, and you can do Hay initialization or K-mean initialization for ReLU. This was introduced in 2015. Okay, so better initialization puts your neural network in a region where learning is possible. Okay, so I highly encourage you to read this paper called The Goldilocks Zone of Initialization by Fort and list 2018 AAA, I guess, which explains the benefit of initializing neural networks in a specific region, which really helps with the learning process. Okay, so so far we talked about changing the activation function, having better initialization, right? So another popular way to address this kind of vanishing gradient issue is called normalization, where the idea is to normalize things in such a way that there is better gradient flow, right? Let's take tanh as an example. So when you do tanh, the range is between -1 to 1, right? And the gradient is between 0 to 1. And the function looks something like this, right? Now, when you are in both the tail ends of the function, when the tanh function is close to 0 or close to 1, the gradient is going to be close to 0, okay? So this, in some sense, is the bad region for optimization. If you are in between, like this is, or maybe I'll change the color. So if you're in between, let's say this is a good region, right? So the idea of normalization is to take your pre-activations and normalize them in such a way that you pull back the activation to the good region. Okay, so this is helpful for vanishing gradient. This is also helpful when you have exploding gradients. For example, when you use ReLU, with ReLU, there's a chance that the gradients explode. Okay, so even in such situations, like idea of normalization is extremely useful. Okay, so when you normalize, you're really controlling the norm, and this is going to help you with better gradient flow. So the most popular normalization method, which really started this idea of normalization, is batch norm by AF and D 2014. Okay, But now we have many layer normalization methods like layer norm, RMS norm, etc. Like probably layer norm and RMS norm are the most popular normalization methods that people use. Okay, so the next idea is the idea of skip connections. So what is skip connection? So let's take the same deep architecture that we started with, right? Like, so you have H2, H3, H4, and Y, right? So we know we have trouble in passing gradients across depth. Like, so gradients vanish, right? So one trick that people use to help with gradient flow is to just add skip connections like this. Okay? So the benefit is now when you want to pass gradient from Y to X, instead of doing this linear path, you can also use the skip connections, right? Like, so this is going to reduce the depth between the input and the output when you want to pass gradients. Okay, so there are many instantiations of this idea. The most popular ones being highway network from Schmidt-Huber's group, which was followed by residual networks, which is this idea of ResNets that people use in computer vision, and even the modern gated linear units can be considered as some sort of skip connections. Is that clear? Okay, so we talked about a lot of architectural changes to enable deep learning, right? Like, so there are also a lot of optimization advances that happened in the last decade, which enable deep learning. Like, so this is the sixth solution that I want to highlight, like, which is this idea of adaptive gradient methods. Okay, so remember, stochastic gradient descent is basically some theta is equal to theta minus alpha times gradient, right? Now, when you have gradients which are really tiny and you still want to make progress in optimization, right? There are a couple of major ideas that people started incorporating in training deep neural networks. Like, one is the idea of momentum, okay? So for example, like the most popular one is SGDM, which is SGD with momentum, like where you start integrating your gradients, the past gradients in a vector, and you use this vector to do your steps, update steps, okay? So now you're not just updating with the current gradient, you're also updating with the history of gradients that you're like accumulating in the V vector, right? Like, this means if you are getting tiny gradients, but in the same direction consistently, you're going to eventually make bigger updates, right? So this is the idea of SGD with momentum, okay? So the second idea was idea of changing the learning rate, which is the adaptive gradient method, right? Like, so the popular example is RMS prop, okay? So where theta is updated with theta minus alpha by root mean square of the gradient times g, okay? So E of g square is rho times E of g square plus 1 minus rho times g square, and the root mean square is given by the square root of E of g square plus epsilon, okay? So you square the gradients, you keep the running average of the square gradients, and you're using that to adapt the learning rate, okay? Now, this is really nice because now for each parameter, I can have individual learning rate, right? When the gradients are larger, the denominator is going to be large, which means the learning rate is going to be automatically reduced. When the gradients are tiny, the denominator is going to be tiny as well, like, which means the learning rate is automatically increased, right? So this per parameter adaptive learning rate is one of the main reasons why we are able to train the neural networks the way we are training them right now, okay? Now, you could combine these two ideas. You could combine SG, like the idea of momentum and adaptive gradients, okay? So that gives us ADAM, the most popular optimization method that people use, right? Like, so ADAM basically has both the momentum vector and also the square gradients, okay? So it has M, which is beta 1M plus 1 minus beta times the gradient v, which is beta 2v plus 1 minus beta times the gradient square. Okay, so then theta is given by theta minus, sorry, this is eta. Eta by v plus epsilon times m. Sorry, this is just m. Yeah. Okay, this is not the exact version of Adam. Like you have to do bias corrections and stuff like, but this gives you the idea, right? Like, which is basically to combine momentum and adaptive gradient. So probably this is still the state of the art, even though there are like many other optimization methods that are being developed, right? Like this is an active area of research. Like people try to come up with new optimization methods that beats Adam, like, but Adam is almost unbeatable. And mainly because it combines the two significant ideas, like one is momentum, one is adaptive gradient method. Like, so it's not clear like what would be a totally new idea that would break this tough rank of Adam, right? Okay, so with the help of all these different tricks, right? Like, so now the final recipe for deep learning is to do some sort of pre-training. Okay, like now that we can train neural networks like in an efficient way with all these tricks, right? Like, so you could think about training a network to learn as good representation as possible, right? Like, so now this is the idea of self-supervised learning that we talked about before, right? Like people do either masked language modeling or simple next token prediction, right? And this gave us things like starting from ResNet, then word embeddings in NLP, all the way to BERT, GPT, VITs, to modern LLMs, right? Now, we know the current state of the art, and I think you're going to learn about all these things in the upcoming lectures, right? Like, so, like, I want to summarize this by one slide, which is basically, sorry, which is basically why. So just give me 1 second. Which is basically why deep learning works. Right? So it's not a mystery why deep learning works. Okay, so we had 20+ years of research that went into developing the most recent foundation models, right? Like, so there are many reasons why the current deep learning works. Like, so some of the obvious reasons are data. Like, so having access to more data means you can learn better representation. Compute, right? Like, so we have learned how to scale architectures, like in a way that we could train very large models with lots and lots of compute, like things like GPUs, TPUs, etc., right? Like, which brings us to hardware, right? And there's also this question of scale, right? Like, so we have learned that scaling helps. We will talk about it like soon, why, right? And most importantly, the tricks, right? Like, so there are many tricks. Like, so we covered most of them, I guess. Like, so ideas like activation, better activation functions, normalization methods, right? Like optimizers, the idea of skip connections. Sorry. Skip connections. Weight decay to train large networks like transformers, right? We did not talk about dropout, but better regularization method like dropout. Even the core idea of attention, which I did not cover because you're going to see transformers anyways, like in the future lectures, right? So like all these tricks added up to make current generation machine learning systems work, right? However, there is still this one big question, like which was bothering people for a long time, like which is like, why is it that when I scale networks, like I'm able to learn amazing things, right? So if you think about the traditional statistical machine learning, it tells us that as you increase the number of parameters, so the number of, let's say x-axis is the number of parameters, right? As you increase the number of parameters, the training loss goes down. That is nice, right? But then you are also starting to overfit when you have, let's say, more Let's say this is the number of examples you have. As you increase the number of parameters and you have way more parameters than the number of examples, like, so you will start to overfit, right? Like, so your test loss or validation loss is going to increase at some point, right? Like, so we call this overfitting. However, interestingly, we don't see this U curve with neural networks. Like, so when I train a neural network, like initially people were hesitant to train very large networks, right? Like, so there was nothing stopping people in 2000s to do LLM pre-training, by the way. Okay, so well, like they could have done a simpler version of this. Like of course the hardware was different, but they could have still done a simpler version of it. Like, I want to highlight that one thing that was really stopping the community from discovering LLMs 10 years, 15 years back is basically this idea that like more parameters means overfitting. And unfortunately, well, this idea came from the statistical learning community, right? Like, so which mostly focused on linear models and generalized linear models, right? Like, so when you have neural networks, it is not clear if this is the right x-axis, right? So the probably the right way to do this graph is to put the complexity here. And for linear models, complexity is basically a number of parameters, right? Like, it makes sense, but it doesn't make sense for neural networks. Like, when you have a neural network, just the number of parameters doesn't completely explain the complexity of the architecture. Okay, so it might be the case that you have more parameters, but the complexity is defined based on the number of layers, what kind of activation function you're using, like what kind of architecture you're using, and all those things, right? Even if you have highly complex models, right? Like, so even if the complexity is high, we know that we don't overfit. So this is something that I think the theory community has worked a lot in the last decade, I would say. So now we have a better understanding of why this is happening, okay? So one of the reasons for this is the implicit bias of gradient descent. So now we have theory which shows that gradient descent implicitly finds low-norm solutions. It's not going to overfit like in a naive way, okay? So this means that even if you have super complex model, the algorithm implicitly prefers a solution that is low norm, which is some sort of free regularization that you're getting, right? Of course, this regularization is not enough, which is why people use ideas like dropout or weight decay. Okay. So I want to bring this back to this question of expressivity versus learnability. So, like, yes, bigger models are more complex than smaller models, right? But interestingly, for gradient descent to work, you do need to go for over-parameterized space. Okay, so this probably means that gradient descent is not the best learning algorithm, right? Like, so, like in theory, I should be able to achieve whatever I'm achieving with 100 billion parameters with a billion parameter model. Okay, so they have the same expressivity. It is just that we don't know how to train this smaller model. Now, because we don't know how to train the smaller model, and we have lots of compute available, right? So we can just scale up the dumb algorithm, and this is going to give us very large models, which has the capabilities of like what you could have achieved with smaller models, right? So the proof for this is you can take a big foundation model and try to do as much pruning as possible, as much like reduction of weights as possible, like you would still end up with a very good performance. So what happens is you train a very large model to identify this small parameter configuration that you really need. Okay, so this kind of hypothesis is, sorry, I think I have used all these slides. This kind of hypothesis is was proposed by Frankel and Carbon in 2018. This is called lottery ticket hypothesis, which I really like. So it says that dense randomly initialized feed-forward networks contain subnetworks, which are basically winning tickets, that when trained in isolation reach the test accuracy comparable to the original network in a similar number of iterations, okay? But the catch here is we don't know how to start with these subnetworks. Like, so if we can identify these subnetworks before training, then we can just train that smaller network and like we can get the same performance, right? because we don't know how to find these subnetworks or how to train a random subnetwork, right? Like, so we start with a very large neural network and train this model to eventually get to the subnetwork that we are interested in, right? This is one hypothesis. There are many, many other hypotheses in the literature, like where people are trying to understand why deep learning works, okay? I'll take a couple of minutes and finish. I know I'm out of time. So are we done? So like, do we have we figured out the recipe for training the ultimate learning algorithm, right? Like, so we talked about a lot of tricks. We talked about how over parameterization is useful. Like, so in some sense, the current recipe is to take a very large model, as large as possible that you could fit with your hardware, and train it with trillions of tokens of data. And how to efficiently train, we know the tricks, we know the architecture, we have attention, we have the optimizer, everything, right? Like, so, and you do this $20 million run, and in the end, like, you have a network that is almost superhuman in a lot of tasks, right? Like, so does that mean machine learning is solved? Any thoughts? So, well, even though many people claim that we are approaching AGI in a few months or few years, right? Like, so I don't think that is true. Like, so there's one fundamental issue that we haven't tackled at all, okay? So like the current focus of all these methods in deep learning is this idea of IID learning that we started this lecture with, right? Like, so like you have the setup where things are independent and identically distributed, right? But this is not what true learning is. Like, a true learning is not IID. Okay, so often true learning is sequential, online, and continual. Okay, it is impressive that we could train ChatGPT and deploy it, right? But the moment you deploy ChatGPT, it is acting like any other piece of software. There is no learning happening after deployment, right? Now, if you want to train the system after deployment, then that becomes a sequential learning problem. And I would like to highlight that we have made close to zero progress in training neural networks online. Okay, so when you train neural networks online, you get into the problem of non-stationarity, and we just don't know how to solve it. Okay, so I will not talk about continual learning today because we have a separate lecture on continual learning by Claire, right? Like, so, which would be a perfect follow-up for like where I'm ending. Like, so, like, I want to highlight that even though it looks like we have solved AI, like we have only solved IID version of AI. Okay, like for me, the non-IID version of AI, like, so like a system that learns online, is 1,000 times more harder than like the version that we have solved. So it took us 50 years to solve IID learning. Like, so I don't know, maybe Claude can help us to solve non-IID learning in 2 years, but it could also take 200 years to solve non-IID learning, right? Like, so like I highly encourage all of you to think about these future problems, like, so as you go through the lectures in the summer school. And I also want to end with like this nice note, like, so like, well, I was at ICML this year, and I happened to attend the optimization tutorial by Mark Schmidt, like, which is probably the best like tutorial I have attended in a decade. Okay, so I asked all my students to watch this video at least 5 times. Like, I encourage you all to do the same. Like, so if you want to know how to train neural network, like, which very much looks like art, right? So this tutorial will teach you the science behind training neural networks. Like, so like I did not get into the optimization part of things at all in this lecture, right? Like, so if you want to learn how to train neural networks, like, so I highly encourage you to watch this tutorial by Mark Schmidt. Like, so I think the slides are available online, and I'm hoping that ICML will release the video soon as well. Plus, take a course on optimization. Like I encourage you to take a course on optimization and then question everything that you studied there, like, so that you can come up with new ways to train neural networks. Okay, so I think I will stop there. Thank you.
Thanks a lot for the lecture. Do we have any questions from the room? Okay.
Hi, thank you for the very insightful tutorial and talk. I was wondering, what is your opinion on whether inspiration from human learning can help us move to real, as you said, learning in terms of continual learning?
Well, human learning is definitely one of the main inspiration for, well, machine learning in general, but also in continual learning, right? Like, so if you think about it, humans are continual learners. Like, so like we somehow know how to integrate information every day. Like, so we also know how to learn from even irrelevant and useless things sometimes, right? Like, so like we don't learn for the sake of having this single objective, right? Like, so something that we learn today is going to be useful for us like in 5 years. Like, sometimes we know the value and we learn it. Sometimes we just learn it and we know how to apply it, right? Like, so we are really good in forward transfer, backward transfer, knowledge acquisition. And like, I would say we are lacking all these skills like with the current generation machine learning system. So in that sense, like, yes, it's definitely useful to think about human learning and get inspired by human learning to come up with new learning algorithms, right? Like, so it's an interesting direction.
Any other questions? I have time for a few more. You guys should be a lot more courageous.
Yeah, thank you for the talk. I was very interested by this kind of sequential pre-training thing. I was wondering, like, like in some sense, vanishing gradients are like to me, it feels like vanishing gradients are a problem because you don't get signal from the inputs, and like there you still get vanishing gradients, but like that's fine because like vanishing gradients are kind of like freezing the weights of the initial weights. So it feels like maybe that works because it's kind of like the vanishing gradients freeze the start of the network, but like the representations towards the end are still fine.
Yeah, so you're with the greedy layer wise training, like, so you already learn good enough representations, right? Like, so which means that if the gradients vanish, it's probably not an issue, right? Like, I also want to draw parallels between this and like things people do with LoRa fine tuning, for example. Like, so if you think about how people do fine tuning with LLMs, like you start with the base model. Now you want to update it for the fine-tuning task, which has very limited data, right? And typically you don't want to move too far, because if you move too far from the base model, like, so you're going to lose the capabilities of the model, right? Like, so which is why LoRa is interesting, because like with LoRa, well, there is this paper which says LoRa learns less and forgets less. Like, so it learns less actually, like, so it doesn't learn too much, like, so you're not moving too far, right? So with the classical greedy layer wise pre-training and fine-tuning, like, so you have that happening naturally, because even if you try to move much, you cannot move much. Like, so there is no gradient, like, or almost close to zero gradient flowing to the initial layers, right? Like, so in some sense, you're doing a glorified single layer training, right? So which is why it works.
Thank you.
Hi. I had one question on the overfitting topic. Do you think for LLMs specifically, we solve the overfitting problem by like having a bigger scope of like their task?
Having what?
By like broadening the scope of the model. So as in, is it possible for you to overfit an LLM?
Well, okay. So the idea of overfitting is also something that is worth revisiting, right? Like, so I did not do that enough in this lecture. But if you think about modern LLMs, they are overfitting. It is just that they are overfitting to the entire web data, that everything becomes in distribution, right? Like, so like I don't think we should think about overfitting as a bad thing. Okay, so if you have very limited data, then yes, overfitting is a problem. But if your data is large enough and diverse enough, right, like that it pretty much covers 99% of the applications that you care about, then what's the problem with overfitting, right? Like, so like in that sense, modern LLMs are probably overfitting. Like, so for example, there are a lot of studies which shows that if you test your LLM with truly out of distribution data, their performance drops significantly, right? Like this just means that they are not extrapolating, right? Like, so they are overfitting. But it's not a bad thing because for probably 90% of the applications that you care about, things are within distribution. So it's okay to overfit, right?
Hey, thank you. So I have a follow-up question to what you just said. You said that overfitting is a good thing, and that we kind of like this fact that everything is in domain, but we humans kind of know that we are overfitting stuff, and I feel like current models don't really do that. Do you have any ideas, hypotheses, or opinions on why is that? Why do models think that they are right when they are clearly not?
Well, I would like to think that even humans think they are right when they are wrong, right? Like, so in that sense, probably they are mimicking the human behavior. So is your question like what exactly is the okay. So, well, in some sense, well, you could call this awareness or like knowing what you know, right? Like, so like it's true that humans know their limits and like they know what is out of scope, like what is something that is out of their competency, etc. And I feel like modern LLMs are slowly getting there, like at least in the way we chat with these systems, right? Like maybe these are wrappers on the top, right? Like, so we don't know, but yes, there is a gap. Like, so models don't know all the time, like what they know, like, but we're making some progress on that, I guess.
I just wanted to make some publicity to some work that we've done with Petar and folks in DeepMind on confidence for large language models. And Gemini probably sucks at that. It's highly confident in when it makes mistakes, actually. But other models like Claude are much better at estimating their own confidence. Yeah, just
But I feel like this is something that people do as a post-training, right? Like, so people identified this issue, and like probably every big model team is working on a post-training recipe which like calibrates the model's confidence, right? Like, so I don't think they pick up this naturally yet.
Yeah, I mean, there's also some aspects about softmax and context length that play into it. So there's like structural issues where softmax needs to be confident for various reasons, but there was a question around here.
Thank you. I wanted to ask about the, I guess now that we've kind of moved from classical machine learning to large scale LLMs, the question is not really about overfitting, but often, and in certain domains particularly, about the long tail behavior that may bring emergent behavior or like in like specific safety domains or behavior in the model that is really hard to control for. And I'm curious, like, how do you think this is going to move forward? Like, should we expect 100% accuracy in certain domains where it matters? Or what should be the future of this problem?
Well, probably we already have recipes to get close to 100% accuracy in problems that matters, right? Like for specific, if you have a specific problem in mind, I think we have recipes to make systems work so well for the problem, right? Like it is just that this is not scalable for every problem, right? Like, so in some sense, this is closer to feature engineering that people were doing in 80s and 90s, right? Like, so like we take a problem and we try to fit things around so that the model works well on that. Like, so whether these recipes will generalize to every problem, like that part is probably not robust yet, right?
Okay, last question.
Thank you for the talk. And the last question will be, what do you believe from all the concepts you taught us is the biggest bottleneck? I mean, where you believe there will be a little bit update there and will unlock a lot of learnability to these deep learning solutions?
Well, my biased answer is like we should learn how to train neural networks online. So I think that will unlock a lot of capabilities that are simply not possible right now. So we are kind of managing with context in LLMs to do continual learning right now, right? Like, so you just have an MD file where the model is putting things and then it is trying to use this as a memory, etc. Right? Like, so like I would say figuring out how to train networks online is like one major bottleneck. Like I also want more people to think about memory, the idea of memory, right? Like, what does it mean to have an LLM or an agent which has short-term memory, long-term memory, like scalable ways of organizing this memory, etc. Right? Like, so probably these are the two major bottlenecks to unlock the next generation capabilities.
So Sarath is going to be around for the entire day and hopefully for tomorrow as well. So don't be shy to ask him questions. And that's true with all the speakers and organizers, you know, that's the whole point. But just to have a little bit of a break. So we're going to have at least 15 minutes. Okay. Yeah. And yeah, so let's have a break. And yeah, thank you so much. Thank you for the time.
Very nice talk.
Thank you.
Okay, please take your seats. We're starting. Please take your seats. Okay, welcome back, everyone. Hope you managed to grab a coffee. And yeah, thank you again, Sarat, for the wonderful introduction to deep learning. So we will now continue with our next speaker. It's a great pleasure and honor to introduce Phil Isola, who's associate professor at MIT, doing amazing work, research work in computer vision and machine learning. And besides receiving numerous awards for his research work, he's also recipient of awards for distinguished teaching. So we have an amazing teacher here. You're great students. I think this is the beginning of a wonderful distillation story. Okay.
Thanks so much for the intro. Yeah, so wonderful to be here. Thanks for inviting me and organizing. This is my first time at EEML. First time in Eastern Europe, I think, as well. So it's kind of neat to get to come and visit. Okay, so I'm going to assume that you now know deep learning. That's the starting point. So we got the previous lecture, and you guys all know exactly how these things work. And I'm going to dive into trying to dissect and look at some of the internal representations in these networks. What are the networks representing internally? What do these activations and embeddings compute? I'm going to try to give a perspective on it, which is kind of a geometric lens onto the structure of the vectors inside deep nets. This might have some parallels to what we'll hear later in the week about geometric deep learning, but it's a different geometric lens, I would say. And especially I'm going to focus on this question of how can you measure the similarity of one neural network to another neural network? How alike are they and how they represent the world? If I take like a computer vision model and a language model, how alike are they in terms of how they represent the world? Okay. So I want to start with this. This is one of my favorite papers from some years ago where they trained a neural network to classify scene categories. Okay, so the input is down here. It's this picture of the dining room, and the output is a scene label. And we know how this works now. We have some vector of activations, and we have a linear and nonlinear. Non-linearities that get mapped up, and eventually you have some layer here, which is a vector in RD, and I have some neuron A and a neuron B, and I can ask, what are those neurons actually doing? What are they representing? And the finding in this paper, Object Detectors Emerge in Deep Scene CNNs, is that if you look at the images or image regions that cause neuron A to fire, neuron A is at some layer within the network, they end up being pictures of things that we have names for. So it turns out that neuron A is a neuron that is like a detector for a dog face. Whenever you see a dog in the image, or whenever you see a part of the image with a dog, it will fire. And if it doesn't see that dog, it might not fire or fire with a lower activation value. And neuron B is a robin head detector. So this is, I think, still the biggest result of like the last 20 years of deep learning, not just this paper, but what this paper represents, which is that the internal activations inside neural networks have semantic meaning. They're nameable words. They self-organize to have things that act as like recognizable object detectors. And neuroscientists have shown the same in the brain. Even decades earlier, there's this idea of the grandmother cell, a single neuron in your brain that only fires whenever you see your own grandmother, and otherwise it doesn't fire. Okay, so this is super interesting. We'll hear more maybe about mechanistic interpretability work on this type of thing. Like, what are these actually representing? But does this happen because we train the neural network in order to do a semantic task, right? Recognize what is the scene category. Well, of course, if we train it on pictures of dining rooms, then to recognize them, it will identify, is there a dog in the room? Is there a table in the room? If there's a table, it's a dining room. If there's a dog, it's a park, and so forth. But it turns out that this is actually a more general phenomenon. So here's another neural network. This one is being trained to classify or actually just regress the color values inside this black and white image. So just predict the raw color values. This is the so-called self-supervised learning setting where we're just predicting some masked part of the image from some observed part of the image. In this case, we mask the color values and we try to predict them from the black and white. So you can play the same game. You can stick a probe into the network and ask, what does some neuron represent? When does it fire and when does it not fire? So what do you all think? This network trained to do colorization is never supervised with a single human word. What will it do? Will it represent texture, shape, color, some kind of photometric information? No, it represents the same stuff. It turns out that there's a neuron that fires whenever it sees a dog face, and there's another neuron that fires whenever it sees a flower, and the neurons end up having nameable interpretations. Okay, this is like the triumph of interpretability work, is that it turns out neural networks can be pretty well described with English or with natural human language. Okay. So somehow these two very different training regimes and different neural network architectures as well ended up representing the world in a similar way. They both kind of carved the world at its joints into these object categories that we have names for. Okay, so that's what I want you to have in the back of your head through this entire lecture. This is the kind of phenomenon that people have observed over the last few decades that I think is really fascinating. Different neural networks seem to somehow have internal organization that arrives at a similar point and is something that we can interpret with our own brains pretty easily. Okay. Oh, by the way, we don't have to only do questions at the end. I'm happy to make this more interactive. Feel free to just raise your hand. I'll have a few times when I ask the audience for questions. Okay, so I'm going to talk about these four things. So one is this geometric view on neural representations. Then how do we measure the similarity between two neural representations? Which representations are becoming measurably more or less similar to each other? And how can we make more representations more aligned? I'll argue that it's a good idea to try to make representations between different models and different modalities agreeing with each other, somehow aligned in how they represent the world. So how can we make that happen even better? Okay. So first I'm going to talk about this geometric view on neural representations. And it's going to reflect a lot of what we just heard in the first lecture. But we're going to look at the embeddings as points in some space. Okay, so we're going to take an example of this computer vision network again. And every layer of this network can be thought of as a representation of the input data, right? So this is the input, and this is W times X plus B. This is W2 times whatever was the output of the previous layer, and so forth, right? So every layer of this network can be thought of as a vector. Just for simplicity, we're thinking of these as the most vanilla neural networks, that, like multi-layer perceptrons that just map a vector to a vector via a linear transformation and a pointwise nonlinearity. Okay, but every layer is going to be a vector. More generally, it might be a tensor, but for simplicity, a vector in RD. And we will use the term embedding to describe those vectors, and we'll generically call them by a variable z. Okay, so z is a vector in RD, and x or z equals f of x, where f is the neural net up to some layer. Normally, the embedding canonically will be the last layer of the network or the layer right before you have the loss function or the prediction, but it can really be any layer of the network. Okay. So here's how I like to think of this. So this is high dimensional space, d-dimensional space, but we can simply look at a two-dimensional slice of that space. So this is Z1 and Z2, the first two elements of this vector. And let's look at where this car lives in that space. Okay, so it will embed here. So we call this like an embedding of the input X into some point in the space. And if I take a different car, it will embed somewhere nearby. Another car will embed somewhere also nearby. And a different type of image like this whale shark will embed somewhere far away. So this is kind of the typical organization that you get in neural net embeddings. You have stuff clusters. So alike things tend to embed to similar vectors, nearby positions, and different things tend to embed far apart. And this can happen for various reasons, but if I'm trying to train a image classifier, like let's say that this neural network was trained to classify, is it a whale shark or is it a car? This would make a lot of sense. It would be a natural organization that gradient descent would arrive at because the cars land in some region which is linearly separable from the sharks. And so if I have, a linear classifier on top, I can separate these two clusters, just like we saw this morning. Okay, but the interesting thing is this happens all the time. Like this is just the standard motif of internal representations in neural nets, no matter what you train them to do. Okay, you could train them with things like self-supervised learning, contrastive learning. They organize stuff so similar things are embedded to similar vectors. Okay. So of course, the picture is that these embeddings are a kind of point cloud representation of how the data is being processed. And every layer of this network is going to be a different point cloud. So the raw data itself will be embeddings. If these are images, the raw data, what is the raw data going to be? It's going to be embeddings in some space. So what is the raw space? Well, if they're color images and they're 256 pixel images, it'll be embeddings in 256 times 256 times 3-dimensional space. Okay, so a point, like a dog is some vector, some point in 256 times 256 times 3-dimensional space. Okay, and then the next layer will move those embeddings around to new locations until at the top of the network, they'll be organized so that it's easy to segregate them if this is a network trained to do classification. Okay, so the data comes into the bottom of the network and it moves around layer by layer into new positions that are better organized for the actual task or objective that we care about. Okay, so deep nets transform data layer by layer. Every layer is a representation of the data. Okay, so let's look at now what it looks like under this lens to train a neural network to do binary classification. Okay, so here we have our input data, and it's not linearly separable. And binary classification, well, the goal of binary classification, you can write it in a lot of ways. We can say it's to assign the label 1 to a cat and label 0 to a dog if it's cat versus dog. But oftentimes the output of the network, we want it to be a belief vector. So over two classes, it would be a two-dimensional belief vector, probability vector that sums to 1. So belief of cat would be 0, 1, 100% belief class 2 and 0% belief class 1. Belief of dog would be 1, 0, or maybe maybe dog would be 0, 1 and cat would be, well, okay, I guess I'm going to index y. Y is the second dimension and x is the first dimension. So dog will be 1, 0 and cat will be 0, 1. Okay, so the goal of a classifier is actually just to move all the blue points to this location and move all the red points to that location. Okay, does that make sense? It's just a geometric reconfiguration of the data distribution. This distribution to that distribution. And the thing that you have to do is every single layer is only linear and pointwise nonlinearity. It's extremely constrained in what it can do. It's not very flexible at all. So I can move the points around, but I have to do it in a linear fashion with only additional pointwise nonlinearities. Okay, so the goal of the classifier is to map the input point cloud to the vertices of the simplex, because the simplex is the set of probability distributions and the vertices are the ground truth labels. The vertex of the simplex is 100% belief of cat and 0 of dog, or 100%, the other vertex is 100% of dog and 0 of cat. Okay, the simplex is the line y equals 1 minus x. Okay, so here's my data that comes in, here's my embeddings that come out. And let's look at the options that we have for rearranging these point clouds layer by layer. These are the only two options that we have, the linear layer and ReLU, for a multi-layer perceptron, the most vanilla neural net. And then at the end, we'll have this softmax. This is an additional normalization layer we could use, but it's not as standard. Okay, so this is what you can do. Here's the points coming into a linear layer. This is like a Gaussian cloud of points, just as an example. And what does the linear layer do? It can only do geometric affine transformations of that cloud. Okay, so it can rotate that cloud, it can stretch that cloud. It's the class of affine transformations of a point cloud. That's all a linear layer can do. So somehow I have to achieve intelligence by just rotating and shifting around point clouds. It's kind of crazy. The ReLU is a pointwise operator, and this is what the ReLU looks like when I take its action on this input Gaussian cloud. Okay, it takes everything below 0, and it maps it to 0, and it takes everything in the positive orthant, and it's just an identity function. So it kind of snaps things onto the axes of the positive orthant. The softmax maps your points, which we can think of as logits. That's kind of the name for the unnormalized probabilities. It maps those to points probability vectors, which are vectors that sum to 1 of non-negative numbers. So that's just points on the simplex. This is the one-dimensional simplex. This is for binary classification. Normalization layers oftentimes will take data which is distributed kind of arbitrarily, negative infinity to infinity, and it will compress it to be having unit norm or unitary values in some sense. Okay, so the L2 normalization layer just takes, this is like roughly layer norm. It takes all of your input data and it will map it to the hypersphere. Okay, so this is all that neural nets get to do, and they just have to stack that and achieve complicated mappings. There's a few other layer types that you might hear about, attention and so forth, but they're roughly like just made out of the same building blocks. Okay, so if I stack that with an MLP of width 2, meaning that all of the embeddings are in 2-dimensional space, so I have 2 neurons per layer, then I train it with SGD. This is what it looks like. Okay, so you can just do this, and that's all it's doing. It's taking this, it's stretching it out because it wants to somehow separate the blue and the red. It's putting the red into the negative part of the first dimension so that after a ReLU, the red gets snapped onto this axis, which then helps it peel it apart on the next linear layer, which is kind of stretching like this. And then it's going to, at the very top, it will stretch things out a lot so that it can kind of scale up the log probabilities such that they, when they get squashed down into probabilities, they will get near the edges or the vertices of the simplex. So all the red points are going to the location of 100% belief it's a cat, and all the blue points are going to the location of 100% belief it's a dog. And this is iterations of SGD, stochastic gradient descent. Okay, any questions about what we're seeing here? I'll show 1 or 2 more visualizations for fun. Okay, yeah, oh, was there? No. Okay, so each layer is a representation, and you kind of reorganize the geometry of the space layer by layer. Okay, this one's more just for fun because I think it looks cool, but it's hard to interpret. This is a MLP with width 3. And so here at the bottom, I have 3 different kind of Gaussians. These are the 3 classes. At the top, so why am I getting these points on the edges of this triangle? This is trained to classify between these 3 color values. So what is this shape here? What is that triangle at the top? It's pretty hard to see. The simplex, yeah, it's a 2-dimensional simplex. Okay, so that's the goal. The goal of a 3-way classifier is to map all your input data points onto the vertices of a triangle, and that will be the beliefs, 100% belief it's a cat, dog, and elephant, for example. Okay, so sorry, the animation is a little choppy, but every layer is just linear, but now it's in 3 dimensions, so it's like warping a cube and stretching a cube. And so, of course, real neural networks are in D dimensions and high dimension, but this is to give an intuition for what's going on. Okay, I think one more example, oh, yeah, is this is the CLIP neural network, or this is a real high-dimensional neural network. It's doing the same thing, but in high dimensions. So I'm doing dimensionality reduction to visualize this. So this is not exactly the mapping, but roughly all the different classes in the input point cloud, which are different, the color indicates the class, they're getting peeled apart through these operations. And eventually they are all segregated so that CLIP can associate words with those classes. This is a different kind of a neural net that associates words with images. Okay. So, so this is how I like to think about representations in neural nets. A representation is a mapping from X to Z. The data is X and the embeddings are Z. Okay. And typically Z is a d-dimensional vector, so vector embeddings. And then we can think of a neural net's representation when it acts upon some data as being a point cloud. Okay, and the neural net itself is like a continuous function that can act on data. So we'll usually think of the representation of a data set under F as some set or point cloud, set of vectors F of X over all the X's. Okay, and we'll call that capital Z. Okay. So summary so far is that every layer of a neural network is a representation of the data. The input data is a representation of the data itself, and the output beliefs are also a representation of the data. It's just a very weird one where everything is on the edges of the simplex, or vertices. And then representations can be understood in terms of the geometry of these embeddings. Okay. So how can we measure the similarity between two representations? So between two neural networks? Well, we will simply look at if the point clouds are the same or different under different types of transformations. Okay, so the definition we're trying to ask, is one neural network the same as another neural network in terms of how it represents data? Or was one layer the same as another layer? You can ask this question very broadly for any embedding. Okay, so we'll measure representational similarity, which will be a mapping from two neural networks, F1 and F2, to a scalar value that says how similar are the representations induced by those networks. Okay, so it takes two neural networks as input, and it outputs a number that's higher if we think they're more alike in how they represent data. Okay, and often we'll just, again, measure this of the action of the network over some finite set of query points. Okay, so we'll have 2 point clouds, Z1 and Z2, or we're going to get a number out. So it's a similarity of 2 point clouds. That's the way to think about it. Okay, so Z1 is just the action of the neural network 1 on a set of probe points, and Z2 is the action of neural net 2 on that same set of probe points, on that same data X. Okay, so this is the central question. I have one neural net. This is a language model, or maybe this is like a word to vec. It maps from words to vector embeddings. And my first language model will embed words in this fashion. And my second language model will embed words in that fashion. And the key question is, how similar are these two representations, which we'll interpret as how similar are these 2 point clouds? Do they capture the same information, the same geometry, different geometry? Okay, so I'm going to walk through a few different popular metrics that we have in the field right now for answering this question. The first is the one that I think is maybe the most popular in neuroscience. So neuroscientists kind of laid the groundwork for this type of analysis about a decade or two ago, and now it's become very popular in machine learning too. And the neuroscientists really like these regression-based metrics, where I take neural net 1's embedding, and I try to predict from those embedding vectors neural net 2's embeddings. Okay, so what is this telling me? It's telling me if the information that is encoded by neural net 1 is predictable from neural net 2. Do they kind of represent the same information? And I can control how different these two things can be by changing the type of regression I do. So the most common one would be linear regression, where I'm going to say, is there a linear predictor from net 1 to net 2? Okay, so here's how you do that. You simply say the distance between net 1 and net 2 is how well, if I train a linear regression to predict net2, what is the residual error that I'm left with? If I find the optimal linear transform, okay, so H star is just doing linear regression, finding the optimal linear map from net1 to net2. What error am I left with? That's how much I could not align them with a linear transformation. Okay, so here are two equivalent representations under linear regression. Okay, so why? Because this point cloud and this one are simply a rotation of each other. Okay, so this is the power of this regression type analysis. It says, well, these two things, they look different. The exact vectors are completely different. Okay, the purple point is not at the same location in these two spaces, but the structural relationships, the relative relationships are all the same. And in fact, there exists a rigid transformation between them. And so we'll consider those two representations the same according to the regression metric. Okay, there's like a new, yes, if I wanted to use this neural network and input it and like stitch it together with this neural network, yes, I would have to have a rigid mapping between them, but that's easy. I don't have to retrain the whole thing from scratch. I can just find this like very simple transformation. Okay. But there's a problem. Are these under the regression, the linear regression metric? What is the distance between these two neural networks? Anyone have a guess? Yeah, just keeping y. Exactly. So mapping y to identity and x to 0, and that's also a linear transformation. So these two things have distance 0 according to a regression metric. So that's one thing I don't like about these regression metrics, is that they would say that these are the same representation of the world, but obviously this one is diminished somehow. This is not representing the x information. Okay, anyone have an idea for how to fix this with a regression metric? There's one like very simple fix. Yeah. Make the matrix invertible. Yeah, so you could require it to be invertible. That's one fix. Any others? Yeah. Measure the dude, by dimension. Yeah, so you could regress dimension 1 to dimension 1, then dimension 2 to dimension 2. Yeah, and so the one I had in mind, but these are all valid answers, is you could do the inverse regression and just symmetrize. You could say, I'll regress 1 to 2 and 2 to 1 and compute the total error that you incur in both of those directions, maybe divided by 2. Okay, so there are ways of fixing the regression metrics, but this is just to give you a sense of these regression metrics can be quite flexible. And people also sometimes will do regression metrics that are not linear. Like maybe I allow myself some flex. I allow myself an MLP that will map from one to the other. And then that's like measuring are the representations the same up to this kind of slack provided by whatever your regression model is. Okay, so that's one family of alignment metrics. Another family is these so-called kernel alignment metrics. So kernel alignment metrics are all based on the idea of, do two representations encode distances in the same way? Do they encode relative relationships in the same way? Okay, so we have vector embeddings as before, and we're going to characterize the representation by its kernel. The kernel is just the distance between any embedding of x1 and any embedding of x2. Okay, so for xi and xj, so we're going to create a matrix, and the kernel will, in each element, will say how similar in the embedding space, or what is the inner product or some base distance in the embedding space between the embedding of one thing, like the apple, and the embedding of another thing, like the orange. Okay, and this kernel, which is maybe some vision model, will say they're quite similar, whereas orange and elephant might be quite different. Okay, so from the kernel, you can immediately read out the clustering structure. This network clusters fruits together and clusters animals together. Okay, so a representation is kind of known by the company it keeps, or the relative relationships between things are what matters. Okay, and so we can ask these questions like, how similar is the kernel for one neural network? Maybe this is the Dino computer vision model, and another neural network. And kernel alignment metrics have this really nice property that they're invariant to the dimensionality of the embeddings. This could be a d-dimensional embedding, and this could be an m-dimensional embedding. But we've converted them to these kernels, which have the same, they're a matrix over samples. Okay, so you can compare two architectures that have different dimensionalities, which is really nice. Okay, so do these two representations have the same kernel or different kernels? I gave it away in the title here, so I'll tell you, yes, they're the same because, right, there exists a rigid transformation. Okay, rigid transformations don't change distances. This is called an isometry, a distance-preserving transformation. And in this diagram I drew, I just rotated in Keynote, so that's a rigid transformation. Okay, so it says that the distance between blue and green is the same as the distance between blue and green here, and that's the same for all the points. You can start to imagine riffing off of this and saying, well, I don't care about distance, I care about ordinal relationships, or I'm allowed to have a little slack. Like, again, like these things can all be massaged in various ways. Okay, another really popular one, I think this is probably the most popular representational alignment metric right now, is called centered kernel alignment, CKA. And so CKA is roughly a kernel similarity metric, saying do two networks measure distance in the same way? But the important thing is they notice, well, kernel alignment metrics are invariant to isometries, distance-preserving transformations, and that includes rotation, translation, mirror flips, and this other thing, glide reflections. And they said, well, we also want to be invariant to scale, because who cares about scale, right? If I give you some embeddings from one company and then from another company, and the only difference is just like a global scalar, an isotropic scaling of the thing, you know, it's very easy. It's one hyperparameter to tune. Okay, so scale usually is something that's, it's very easy to align scale. So we don't really worry too much about that. So we want to factor it out. So we're not saying these two things are different just because the nuisance, this like scale. I could just cannot like normalize to get rid of the scale, right? I could take my data and divide by the variance, and there I go. I got rid of the scale. Okay, so getting rid of scale is very easy. And so they do that. And yeah, I won't walk through the exact construction here, but we're basically measuring the similarity between kernel 1 and kernel 2. We're taking kind of all the dot products, which is what's computed by this trace here. We're normalizing by the scale, so like the similarity to yourself gets factored out. If you know the difference between covariance and correlation, this is roughly the same thing. Like with covariance, divided by the internal variance gives you correlation. So they're kind of doing the same trick. They have this thing H, which removes the mean similarity. So they're normalizing by the mean. So it's kernel alignment metric, which is a little bit more invariant to things that they consider nuisances that don't really matter for the types of use cases that we have in mind. Okay, why do we want to know how similar one representation is to another? Maybe so that we know if a tool that was made to use one representation can instead use a different representation. Okay, scale and mean and translation, these types of things don't matter much because I can factor those out. Okay. So, oh, the Zoom is delayed. Okay, here we go. Sorry, there's a lag in the slides being projected up here. Don't know if it will load in a second. Any questions while we wait for this to load? Yeah. Yeah. So, right, the dot product is kind of the, it feeds into these metrics. So the kernel alignment metric is like with respect to a kernel, and you have to say what is the kernel measuring? It's measuring the dot product between different embedding vectors. And that is, I don't know if people have put enough thought into that in this area, but that's kind of the standard way of measuring the distance between two neural vectors, embedding vectors. It tends to be dot product. And I'm not sure if it's fully justified. It might be better to do something that is Well, yeah, maybe there's more to say about that, but it's dot product is the standard, just maybe by tradition most of all. You could use other metrics. Okay, good. I think it loaded. So here are two equivalent representations under kernel alignment because we have the rotation, and under CKA.
Sorry, one question here. Sorry.
Yeah. Well, over here.
Hi. So what if you just learned the kernel from like using a neural network itself? Could you do that? Could you learn like the best kernel for your data using like a neural network? Is that
Yeah. So you still usually in those cases want to have some base. I don't think it completely gets around the issue of dot product. You would learn a kernel such that dot product is meaningfully predictive of something. So you'd say that I do metric learning. I have data that labels how similar things truly are, and I'll find an embedding such that dot products match that supervision of similarity. So it doesn't quite get around that fundamental question of what is like your atomic notion of distance. But yeah, really the perspective I want to give is that all neural networks can be recast as learning kernels. There's kind of I'm not sure if it's exactly a bijection, but there's some relationship between, you can think of a network as embedding data into vectors, or you can think of a network as defining a distance function between two data points, and that distance function is the base kernel applied to the embeddings under the neural network parameters. Okay, I'll come back to that duality in a second. Oh, okay, so finally, I think it got there. So now we say that this is the same as that because it's just rotation and scale. And CKA will treat these two as the same representation. Okay, so all of those kernel metrics so far are somehow metric in that they give you kind of a continuous measure that's smooth with respect to continuous changes in the inputs. But we might want something that's more ordinal or categorical, where we're not actually caring exactly the distances between two things, but we only care what is near to what. And that motivates these nearest neighbor alignment metrics. These nearest neighbor metrics, what they do is they will embed the points according to the two neural networks, F1 and F2, and ask if the embeddings have the same neighborhood structure. Okay, this is one that we called MKNN, but there's a bunch of these in the literature. So this one says, what % of my nearest neighbors under F1 are the same as the nearest neighbors under F2? And so here we have 2 out of 3 are the same. And so this is like, yeah, 2 out of 3 neighbors overlap. Okay, or maybe it would be, here's 3 total neighbors. Here's out of these 1, 2, 3, 4 total neighbors, 2 of them overlap. Okay. So both of these would measure distance with the same metric, like that would just be dot product. But that's, again, these are only true up to the choice of what is that base metric. So if I instead used like L1 distance, I might have a different, yes, mutual K nearest neighbors under a notion of what counts as nearest neighbor. Yeah. Right. So how do you evaluate? A lot of these are motivated by some argument that we don't care about scale or something from first principles. I don't think that there is really a standard way of like an evaluation metric for kernel alignment metrics. It's always a hard question. How do you evaluate your own evaluation metrics? Because this could be used as an evaluation metric. My favorite answer to this, actually, it sounds a little circular, but my goal is to find representational similarity metrics that reveal interesting trends. So we'll get into looking at our neural networks learning the same representation. So I'd like to identify what is the representational similarity metric under which it is true that they're arriving at the same representation, because that will tell us that these two things are the same under that sense. Two things are the same under what sense? So I want to find the sense under which they are the same. We'll kind of come back to this. Okay, so these are some of the things, and yeah, this is what I was just saying. Essentially, each metric measures similarity up to a transformation t. Okay, so here's a representation Z naught, and I can ask, what are all the representations that are the same as that vector? Okay, so what is the set of the space of all transformations of Z up to a transformation T? So Z equals T of Z naught under some parameters of that transformation. Okay, so if the transformation is nothing, it's just the identity, then it's like to be the same representation, I have to be exactly the same vector. But for kernel alignment metrics, we say that to count it as the same representation, I just have to be an isometric transformation of the data point, okay? And for regression-based metrics, to be counted as the same, I have to be a linear transformation or other regression models, like an MLP transformation of the data. And then you can be even more broad. You could have some mutual information perspective. You just want to ask, are these two representations conveying the same information in an information theoretic sense? And that's a very broad class. And that might be asking, is there a bijection? Because two variables that have the same mutual information, there should exist a bijection between them. Okay, and so you could use other ways of measuring similarity, like there's one called cycle consistency that checks if there exists a function f that can map from Z1 to Z2 and a function g that can map from Z2 to Z1. And that function can be anything. It doesn't have to be linear or MLP. It can be absolutely anything. It's asking if there exists a bijection. Okay, so every claim that you want to make about these two things are the same, really it's a claim that neural net 1 is equivalent to neural net 2 up to some transformation. And then you would want to reason about whether that transformation is one that is valid or uninteresting, like is something that you can be invariant to, or is something that's important and makes important distinctions between different representations. Okay, so which one is the best? Getting to this question. So my favorite is kernel methods. I don't know which of the kernel method it's going to be, but why? It's because I think the distance. So kernel metrics say, do these two representations measure distance in the same way? And I think that's really what matters for most of what we care about in machine learning. There's a lot more that could be said here. I don't have a proof for this, but two representations that are related by an isometry, I would claim that they're the same for all practical purposes. Okay, so one example is if you have a linear isometry, that means you can actually prove these things. You can show that you have equivalence in terms of k-nearest neighbor retrieval. Like that just makes sense. If two different representations measure distance in the same way, then they'll have the same neighbors, and a k-nearest neighbor retrieval method will behave identically. But it's not just k-nearest neighbors, it's also linear, min-norm linear regression, MLPs in the neural tangent kernel regime. There's a lot of cases where if you know the kernel, then you can, that's all you need to know in order to make inferences about how the system will behave or what it will converge to. Okay, we could almost make this definitional. A representation is a specification of the kernel, and we don't even need to think about representations beyond that point. Okay, maybe I'm wrong because the kernel doesn't tell me how much VRAM I'm using, right? Like the dimensionality of the embeddings is not in the kernel, and so maybe there are other things that matter too. But I really think that this is, from a kind of abstract theoretical standpoint, this is the one I like. Yeah, question. Yeah.
But we are actually entering the world where we use LLM as a job, our non-static.
So no, I think that everything should be learned from data, and there's like everything that we handwrite in 1 year, eventually it will be learned from data in a future year. I don't think there's much of a future for distance functions that are not learned, but I would say that every neural net is implicitly specifying a distance function, a learned distance that can be meaningful, and an LLM as a judge is a particular induced distance. Now, it might not be satisfying the triangle inequality. I don't know what kind of distance function it is, but it is a distance in that it takes two variables and outputs a scalar. And that would be the way I would think about it. It might not be like a Mercer kernel or satisfied sort of math properties. Okay. So representations can be compared by similarity metrics. or distance functions more generally. And each metric yields different inferences you can make about how it will behave and what you can do with it. And I'm just giving you a few of the ways I like to think about it, but really justifying what inferences you can make and what you can do with it. This is a much deeper literature to get into. Okay, so let's see how we are on time. Good. So which representations are similar under these notions and which are different? Okay, so I want to play a little game with you. Now we're going to measure your kernel. The whole audience is visual kernel. Okay, so how do you measure distance between two images? So I'm going to show you two images and ask how similar they are. This is from some work that we did called DreamSim a few years ago. Okay, so the question is going to be, which is more similar to the middle image, the right image, or the left image? Okay, so look at this for a second and make up your mind, and I'm going to ask you to clap. So clap now if you think this is more similar to the middle image than the right image is to the middle image. No one really? Okay. One, okay. Now clap. Everyone. And you know what? I knew what your answer was going to be, and so did Dino. Okay, Dino is a computer vision model. It agrees with you. It measures things the same way as you do. Okay, let's do another one. But it's obvious, right? It's just color. It's just color. So how about this one? Okay, left, right, Dino. Okay. Yeah, maybe, yeah, color and texture. Okay, pretty easy. Left. Huh, interesting. Okay, Dino. So it's not left, you know, I put this on the left, so it's not just left-right bias. Okay, but this one, colors, texture, I don't know what you're gonna do. Just make up your mind. Maybe people are shy. Sometimes there's one or two people that clap on that one. Dino too. Okay, so this is interesting. Everybody, these are examples where in our data, like 90% or more people agreed. So you're showing that with your clapping. And interestingly, Dino also agrees with people about 90% of the time on these and other examples. And it's the best model we had at the time of human perceptual similarity judgments. Okay, so this is interesting. I don't know how many of you are familiar with Dino and clipping these things, but I want to emphasize that Dino is not directly trained on any human judgments. No, it's not labeled, it's not trained on text, it's just a self-supervised computer vision system trained on internet photos. Yeah, it's trained on photos that humans took, and there's some bias in the experimenter's design, but it's something that is kind of surprising to, it was, you know, when we first saw these things, and this is like a replication of work from 10 years ago, before Dino, this LPIPS method, when we first saw this kind of thing, it was quite surprising to me. The neural networks that are not fit to human data end up being having the same kernel as the human brain to some degree. And then neuroscientists have done that a lot too. So they will not just ask how similar two images are, but actually stick probes inside the brain. So here's the kernel that you get by sticking a probe into a monkey brain, measuring the activity as electrical impulses, and that creates a vector of activity, which they call Z, and then you can measure the distance with dot product or Euclidean distance between the neural activity vector for a face and another face, and it's high similarity, so low distance, or between a face and a house, it's low. Okay, so this is the macaque kernel over these images, and here's what it looks like over a lot more images. Okay, so every row and every column is indexed by images. And this is like the cluster of faces and houses and other things. And this is for a deep net. I mean, this is an old deep net, but the story has kind of persisted over the years. Okay, so the kernel for the visual system of the macaque brain in the IT cortex is similar to the kernel for an old deep network, and newer deep networks, you have a similar story. Now, it's different in many of the details. So when you talk to neuroscientists about this, they'll be like, oh no, there's so many interesting differences. Like, you know, the fine-grained structure is completely different. And that's all true. So it's like you can see this as glass half full or glass half empty. But to me, the first order result is that we see visual similarity in a way that is alike to, we as humans and monkeys see visual similarity in a way that is alike to how it emerges in deep nets that were not trained to model similarity. Okay. So we can, yeah, my own personal bias is to look at the commonalities in all of this. There's a whole lot of people who study representational similarity that care more about the differences. So I'm giving a little bit of a glass half full interpretation. Yeah, question?
So regarding the previous paper, did they do any research into what parts specifically were different between monkey and the network? Like, so like, what are the classes on which they disagree?
Yeah, so I don't know this in particular. I think that the images that they showed were of this kind, faces and houses and objects on black backgrounds is kind of the simple data. So I don't know that in that year they got to the point of looking for precise disagreement. I know more recently in this area, people have been looking at, is there good agreement with the most recent models, with transformers, with RNNs, with other things, and they find that it's actually maybe not increasing, maybe going down a little, but it depends how you measure. So there's a whole lot of nuance on top of that. And yeah, I know that's just a partial answer.
Thank you.
Yeah, let's do one more.
Like, is this thing happening when it comes to images only, or like if you take like a picture of an image of a house, and like if we take the word house, will they have like similar representation in our brain and also in the neural networks, or
Yeah,
like?
yeah, that's so. Is this happening between images and text?
Between images only, or like can it happen within multimodal, like text
Yeah,
and image?
so I'm going to show a multimodal case now. It's just going to be between a language model and a vision model, not with the brain. I don't know if anybody's looked at this in the brain, but it'd be pretty interesting to look at if the brain represents language in an alike way to how it represents images. But we're going to look at that now for artificial systems. Okay, so let me keep moving. So how similar is the way a vision model sees the world compared to a language model? So the question is going to be, if I give a picture of an apple to a vision model and it outputs a z vector, is that the same z vector or the same up to a transformation as the LLM's embedding of the word apple, or maybe a caption that describes the apple? Okay, are those the same or different? Obviously, they're going to be different, but in what sense are they alike? Okay, and so we're going to ask, are they alike in their kernel structure? Okay, so we will compute the kernel for a vision system, and we'll compute the kernel for the corresponding captions that describe each of the images. So is the similarity as measured by a visual system between apple and orange the same as the similarity as measured by a language model between the word apple and the word orange? Okay, so we measured this on a data set of images with captions. So Yosemite and a caption describing it. It's not just a single word, it's a whole caption. You embed the images with a vision model, you embed the language with a language model. There's a lot of details about which layer do you extract and so forth, but you get some Z vector out of a language model. And the kind of finding from this work a few years ago was that there seemed to be this trend where as language models get better and better, and as years pass, so this is next token prediction, like this is likelihood of the next token roughly. And then on the y-axis is the kernel alignment as measured by the mutual k-nearest neighbors agreement. So do these two things measure distance in the same way with respect to their local neighborhoods? And over time, this was getting higher. And if I compare a language model against bigger vision models, you also get higher alignment. So it does seem like computer vision models and language models measure distance, at least with respect to local neighbors, in similar fashions, and that similarity is increasing over time. I don't know if this will continue. This 2024, we did rerun this in 2026. And the interesting thing is that open source language models perplexity, like performance, their base performance hasn't increased really. So you can't even see if this trend is increasing. Instead, people move to post-train, like the base model's next token ability is not what people focused on the last few years. They focused much more on post-training for math and coding and other types of things. So this particular trend, we actually haven't even been able to get further along on this axis. Okay. oh yeah, we called this the Platonic representation hypothesis. And the kind of most extreme version of that is that different models converge to the same representation. Okay, that these two things really are equal. But I think that the next step is to ask, well, what do we mean by same? Like, okay, yeah, this metric of similarity is going up, but I already told you that the metric just measures sameness with respect to some transformation or up to some equivalence class. Are they finding the same exact vectors, the same kernel, the same two things that have convey the same information, but otherwise have completely different geometry? In what sense are they the same? Okay, so you could imagine a few different hypotheses. One is that they're converging into identical vectors. So the embedding vector, the actual numbers in that vector for a sentence, this apple is red and juicy, it's the same as a picture of that apple. That's one hypothesis. Two is it's the same kernel and there exists an isometry between the two. Three is that it's not the same global kernel, but it's the same like mutual k-nearest neighbors or maybe local transformations are allowed. And there could be more. So just right off the bat, I want to say that this one's just false. There are arbitrary symmetries in terms of like, and you can prove that this won't happen in any reasonable model, that you're never going to get two things that embed to the exact same numerical vectors because rotations of your data, the actual modeling objective can be invariant to rotations of these kind. Or like if I have a linear regression at the top of my network and I rotate my embeddings right before the linear regression, I just have to rotate the linear regression hyperplane as well, and I'll get exactly the same loss. So there's like fundamental symmetries in things like training a neural network to do linear regression. Okay, so that one's wrong off the bat. So there's some interesting work that followed up on ours. Is Maria here? I think that Maria is, Barbuk is going to give a talk in a few days. And one thing that her group did is observe that CKA, which was one of those metrics that I talked about at the beginning, which kind of measures are the kernels the same globally, ends up having a much worse trend of language model capacity versus alignment division models than looking at the local neighborhoods with the MKNN metric. And additionally, they found that CKA goes up if you just increase model depth and width for a random model. So there's kind of a calibration error that we made that if you just make two models bigger, CKA will kind of inflate how similar it thinks they are, even though they're not getting any more truly similar. But this is not true or not as true for the MKNN metric. So the conclusion of this paper is roughly that if you look at local neighborhood structure, you do see this interesting trend of convergence, but the structure as measured by CKA does not show that same trend. This was another interesting nuance that was added by this group, Elias Efros and some of his students, in which they argued that, look, here is the nearest neighbor to the dino image in a dictionary of size 1024. Okay, so if I look over 1,000 images and I ask which is the nearest neighbor to this image under the dino metric, it's this one. And if I look at 1,000 captions and say which is the caption that's closest to this one, it's the same caption that matches that image. Okay, so this is great. We have alignment between how nearest neighbor structure works for these two models. But if I instead look at a much finer grained type of analysis where I say, what's my nearest neighbor in a dictionary of size 1 million? Now for Dino, it's the exact image or almost exact car. But for the language model, the caption turns out to be the caption of a fairly different car. So it looks like there is agreement between these two models in terms of some kind of coarse level structure, but at a very fine grained, like what Dino thinks is the exact adjacent point in vision space is not the same as what a language model thinks is the exact adjacent point in language space. Okay, so these papers are basically arguing, okay, one, Maria's
Sorry, a
paper-
question here?
Yeah,
Sorry,
question.
just a second.
Over here.
Sorry to interrupt, but
go ahead.
About vision models and language models being aligned at the course level, do you think that comes from some sort of loss of fine-grained detail between images and captions? So caption doesn't represent the full richness of an image. Do you think that is why?
I think that's the main reason. So in fact, okay, I think, is this your paper, Viorica? The paper that was showing that if you make the captions longer, you get better alignment. Yeah. And so basically, why is this not measuring distance the same way as this? Well, this is just a short caption. An image is worth 1,000 words. If I make this 1,000 words, the alignment goes up. And then what they did at DeepMind is they actually took these images and made them into videos, and then the alignment also goes up. So maybe asymptotically, as you have like an infinite length video and a whole book written about that video, the alignment would be at a much higher level. So that's an important consideration as well. Okay. Okay, maybe it's not quite the same global kernel, but maybe its local structure is aligning fairly strongly, global structure maybe more weakly, and it's not the exact distances, but it's kind of like an ordinal version of the distances. Okay, and there might be more hypotheses. I actually think this debate, like I think people online seem to take some of that work as saying, oh, there's no global structural convergence. I think that's not quite true. There's no CKA convergence, but if you look at course level clustering, actually the convergence is quite strong. So I think it might be more like you converge to the same local and global whole neighborhood structure, but it's like an ordinal version of the original argument. Okay, so there's more to say here. This is kind of open science, and yeah, I'm excited to see where this continues to go. Let's see. I think for the sake of time, I'll just mention very briefly that this is all empirical. I think the empirical stuff to me is the bleeding edge, but you can, for specific classes, mathematically prove when two models will agree on the representation or not. So for example, for InfoNCE contrastive learners, you can prove that the kernel that you converge to is the pointwise mutual information function. Just if you're interested, you can look that up. For clip-like models, you can prove that two independently trained clip-like models will converge to embeddings that are related by an orthogonal transformation Q, and it's the same transformation for the vision embeddings and the language embeddings. If you're interested, you can look that up. So for specific classes of models, you can prove specific notions of convergence. It doesn't say that they're going to converge to identical things, but to things that are related by an orthonormal transformation in this case. Okay, but the summary of this section is humans and deep nets both seem to measure distances between images in similar ways, and different models, artificial models, seem to, in some sense, be converging to representing the world in similar ways, but we have to specify what is the commonality. It's not they're the same in all senses, but they're the same with respect to certain geometric structures. In particular, maybe some kind of kernel structure, and there's a lot of ongoing work in trying to figure out exactly what structure. One more question. Yeah, let's do 2 quick questions and then I'll do the final section.
How would world models tie into that, like in terms of their representations?
Yeah, world models. So I don't know of work that's looked at kind of convergence in world models or alignment in world models, but I think it's a great question. There must be some work on that. I think the gist of what I'm saying would suggest that it would be in line with the argument that language models learn a world model. Like there's this debate in AI right now. Is ChatGPT a world model? What counts as a world model? And the gist of what I'm saying is if indeed different models are arriving at similar geometries and they're related by just simple transformations, then there might, this is true for these embedding models, then maybe for generative models, the same thing happens. And there's like a simple transformation that converts ChatGPT into JEPA or whatever your favorite world model is.
Thank you.
Let's do, I think I said one here, and then let me finish up and then I'll try to save a few minutes for questions at the end.
Is this trend of similarity seen between different concepts also in research in different languages? Because I think that most of those models are only trained on in English. So
yeah.
I don't know if there is another representation for another language, because I think that the relationship between words in different languages changes completely, even though in English or Spanish, the relationships
Yeah.
are not really equal. Yeah.
So do different languages have the same geometry in the embeddings? And the answer is to a decent degree, yes. Like on these metrics I'm showing, the language to language similarity, like English to French, will be a lot higher than the numbers I was showing. For vision, like vision to language is much lower than language A to language B. But it's definitely true in our own cultural experience that there's like huge differences in culture. But I would say that that's maybe because we humans care about those nuances, right? We care about the exact like concept of je ne sais quoi or whatever it is in French. It's like there's no translation for it. But I think that every language has a word for apple and orange and person and love and hate, right? So the similarities are still maybe 90% of it, and these cultural differences are smaller. Okay, so I think I'll have to make this a bit of an abbreviated section, so we have a few minutes for questions. But I want to point out that why do we care about measuring all of this alignment? It's so that we know how to interface between models and make them be able to share data and structures more effectively. So there's a lot of benefits to being able to make models more aligned. And in order to make models more aligned, we need to have measures that tell us how aligned they are. And then we can optimize those measures, or we can make informed decisions based on those measures. So can you share data and supervision between modalities? Yes, you can if the representations are roughly the same. Because if my representation for a vision model and a language model arrive at the same place independently, now I just have to learn a stitching layer between the two models. And there's a lot of work on doing that, just having like linear layers that stitch between vision and language. We can scaffold new models onto existing representations. This gives you ideas about transfer learning and fine tuning. So there's a lot of benefits to alignment. There might be some detriments to alignment too, like collapse, mode collapse, this idea that we might have this hive mind that just only has one way of thinking and it loses diversity, and that's not good. Okay, so the two things that people like to look at in terms of increasing alignment are, one is training a representation such that it's aligned with another representation. And the other is taking a representation and finding the transformation that relates it to another representation. So if I want to stitch together a language model and a vision model, I could do this. I could find the transformation T that relates them. Or if I want to train from scratch a new model, I might train them to be aligned from scratch. So I just want to kind of quickly show you like a few examples in this area. Okay, so CLIP is a model that trains an image encoder and a language encoder such that the dot product between the embeddings is the same. So it's like alignment up to identity. It's trying to make it so that the Z vector is identical. Actually, it points in exactly the same direction for the caption of an image and the image itself. Okay, so this is a popular language model. And REPA is another one that became popular a year or two ago, or maybe a year ago now. And what they do is they try to align a diffusion model that generates images with a representation model that embeds images. And so this model here is a pre-trained vision encoder, and this model here is a diffusion model. And they say that they should be aligned. It's a regression style alignment, so they're going to be aligned up to an MLP transformation. And that allows this thing to be kind of supervised by the internal structure of this pre-trained representation. And then the diffusion model trains a lot faster because you're aligning it to something that already was pretty good. Okay, so this is alignment up to an MLP transformation. What about alignment up to an isometry? This one has some really interesting property, which is you can do unpaired translation. Okay, so if I have sufficiently non-degenerate data, then I can translate between two representations related by an isometry with 0 paired examples. Okay, so let's say I have language embeddings Z2 and image embeddings Z1, and I want to find the translation between them. Now, if I know, because we did the science, that these two things have the same kernel, meaning that there is an isometry that relates them, that means that I can uniquely identify the transformation if I have enough elements in Z1 and Z2. Okay, so this is the idea here, is that if I have a point cloud of these 3 points in two-dimensional space, there's a unique rigid transformation that will align this point cloud to that point cloud. Okay. They don't quite look rigid to me, but maybe that's a visual artifact. Yeah, this is supposed to be a rigid transformation, just rotation. Okay, so I don't have to have somebody tell me that this is the blue point. These can be unlabeled points. So the color is just for visualization. And I don't know which one corresponds to which, but I can find the unique isometry that relates them. That's what they did in this paper. So they embedded images and words, and they found a isometry that relates them, and were able to do unpaired translation or unpaired alignment between images and words. No one told you that a cat is this image, but it just figured it out from the data set geometry. This paper did the same thing roughly, but it did it between 2 languages. So again, going back to this question, so this is like French and this is English, or I think actually in this case, it might have been this is like Llama and this is, Bloom or something. It's 2 different language models. And they found that they kind of hypothesized there should be an isometry between the embeddings for these 2 language models. And indeed, there was, and they solved for that isometry. Now, they had a little bit of these kind of distribution matching losses and cycle consistency, and also a bit of the kernel matching losses. So it was a combination of many different things, but eventually you can almost perfectly align these 2 point clouds. Okay, so the final summary is that many important problems involve aligning or translating between representations. That's why it's interesting to study this area. A fun thing is that once you realize this geometric alignment problem, you can find out, you can take that and show that you don't actually need paired data to align between different models for many cases. And you can instead align at the distributional level or at the distance, the kernel level, or at the relative relationships level. Okay, so I'm gonna end just with this, this slide saying that this is an area which has like a ton of growing interest, studying the internal representations and how they are alike or different between different models. There's a ton of neuroscience on this. There's a lot of people in psychology and cog sci that are doing this, and then machine learning is becoming a major area too. So if you're interested, feel free to look into some of these like review papers on the topic. Okay, thank you, and I'm happy to take questions.
Thank you, Phil, for the very inspiring talk. Any quick questions before we head for lunch?
Yeah, I'm curious, what do you think would happen if you take 2 models which tend to converge when they're embedding, so let's say a vision transformer and LLM, and train them to have a divergent geometry, so train them so their geometry is not similar, would they even reach the same performance, or there is only one true way of representing things internally?
Yeah, I really like that idea. Could you train 2 models to disagree according to these metrics?
Yes, to disagree on their geometry.
So we and others have tried to see if you can train them to agree, and will that causally improve the performance on each of the models? Like if I train a language model and a vision model to agree, do they get better? And there's some evidence for that. It's a weak effect, but there's some evidence for that. We never tried training them to disagree. I think that they would get worse, but it might reveal something really interesting. Like it might reveal there's 2 modes. Like you can represent the world in this way or that way, and both are effective. And that might be very nice for capturing like diversity and having a mixture of experts, or there might be reasons why that's a good thing.
And do you think there is only one way of representing the world, or this model of having multiple ways of representing it is more plausible?
I think that there is a small set of the equivalence class of things that fit the world is a small set. So I don't know if there's one way, but I like some of this work is kind of roughly in line with like physical realism, that like F equals ma is true. It's not like there's a different equation that would equally well explain nature. But I don't strictly believe that. I just think that there's probably a small set of equally good models for the universe.
I understand. Thank you.
Thank you for the talk. I have a quick question. I'm right here. I don't think you can see me. Okay. So what do you think about like how we tokenize the input affects these representations?
Yeah, how do we tokenize input? I haven't thought too much about that. I guess I'm a fan of methods that try to remove the tokenizer as much as possible and just go back to the raw bits. So byte level models, bit level models, pixel level models. And in those cases, it could be there's kind of a representation, there's a bottleneck to the degree of alignment you'll get, because if you use something which is too domain specific, you have lost the chance for the learning to like reveal the true underlying structure. Like if you do, I don't know, if you do byte pair encoding and you fit that on some small data set and it chops the bytes in a suboptimal place, then maybe you'll never reach the best model of the actual underlying data. So I'm a fan of getting rid of that as much as possible.
One question about this hypothesis of locality. So how do you think, to what extent it can be true, depending on what complexity of building blocks in neural networks that you use? Because, for example, I can have two classifiers, one which works on plane. Say there are two classes, and like say one uses just linear transformations, MLP blocks, maybe some non-linearities. And in another one, I just add one stereographic projection to the sphere. And as a result, this will work in the dimension n+1, but locality structure will be completely different. So yeah, how do you think how it depends on complexity?
Yeah, I think this is a little bit related to the question of could you optimize for divergence? It might be that there are these constructions that can create two equivalent representations for some particular performance level or particular task, but like you can create an adversarial case where they completely differ in their local neighborhoods, but they still achieve the same performance. It sounds like you're trying to construct such a case.
Yeah, but here, like, I suppose that we train naturally. That is, we initially don't want to do some adversarial thing.
Yeah, so my feeling, I think this is still in the kind of empirical, my empirical feeling is just the types of data we have and the algorithms and the training that we have right now are in this basin where it kind of converges in the sense I'm talking about. But there might exist some really weird architectures, like some lookup table that's just memorizes the entire universe that doesn't have this property at all. Like it might be you can construct other scenarios which don't match how people are doing things now, where you would not expect convergence. So yeah, I think there's a question like theoretically, I think you can have under these assumptions with this modeling system, you get alignment, and there's other cases where you don't. But in practice, I think we're mostly in this bucket over here.
Should I? Okay. Thank you for the really nice presentation. Again, I wanted to ask you a question about whether if you experimented with encoder-free multimodal models at all and what they look like. I think there was a recent release from Gemma team, for example, in which they got rid of the vision encoder and now you can just process both modalities at the same time in the same model. Do they look more like one of the, let's say, LLMs or more like vision foundation models?
Yeah.
If you experimented. Yeah. Thank you.
Yeah, thank you. I haven't looked at that, and I don't know of anything off the top of my head of anyone that has. But yeah, the architecture would be more alike between the language and the vision in that case. And so you might expect that somehow they align even better. I don't know for sure. Although I will say that I think of the language models, the decoder-only language models, as an encoder for the purpose of this talk, because we still map from an input sequence to a z-vector. So they're an embedding of a sentence. You know, they do that mapping in a different way that we call decoder only maybe, but I think that distinction encoder decoder is a little bit fuzzy. But yeah, I haven't looked at those models.
Thank you for the great talk. I'm curious on your opinion about when some papers that do training with human behavioral data or human neural data to increase representational alignment. I'm sometimes very impressed by these works, but it gets me thinking, isn't this some kind of like godlike imposition on the model? And what do you think we can learn about the mechanisms that make these good representational structures emerge by just enforcing alignment?
Yeah, so I think that for understanding the brain, it's fascinating to train models that are aligned with the brain. And that's like modeling the brain. You're trying to train a model that's predictive or aligned with the brain. And so I like the work that goes in that direction. The work that tries to align with human behavior or even human labels for the purpose of just AI engineering performance, I think it's one of these steps on the ladder, but we'll surpass it. So, the human brain, I don't think is the best representation of the world. And that's like maybe human level intelligence, but for super intelligence, it might be something else that we want. So I think that, yeah, it's like we had that era when we trained representations on like ImageNet, where it was labeled data by humans, and then people moved to self-supervised, where has less human inductive bias and things got better. And I think that's going to always be the trend. So it's useful stepping stone, but maybe it's not the best solution.
Maybe a second small question on what you said before on the alignment of language models with vision, that maybe you could have a GPT that's a world model. I was wondering, what do you think that could there be one type of representation or model that's better for some things than others? Because I can imagine if you have an embodied agent running around the world, maybe it's not the most efficient thing to describe every single detail, like a literature book, or when you're talking about high-level ideas, a vision might not be an efficient way. So I'm just wondering about, some people are trying to say that language is all you need, and I'm wondering about your opinion on this.
Yeah, I think, again, it's kind of like there's some truth to language is all you need. Yes, asymptotically, infinite language with infinite test time inference, whatever, maybe it is all you need. But all you need is not all you need. It's like you want efficient things too. You want things that are fair and honest. There's all these other axes. If what you care about is looking at is the representation sufficient for optimal downstream inference? That's kind of a very narrow question. And a lot of what I presented is just kind of from that perspective, like what do we converge to in terms of how the embeddings represent the world from the perspective of somebody that will use them, but not from the perspective of how much energy it took, or did it ignore data provenance, or there's other perspectives too. So I think that when you take all of those into account, then having this diversity of models and non-language models makes more sense. But if you just want super intelligence and you don't care how much it will cost, then I think language models will probably take us there. Infinite data can do every model with infinite data can do anything kind of argument.
Okay, thank you.
Hi. I want to ask about, you showed us the latest vision models that got a bit worse than the older ones. Is the reason mainly because of AI generated pictures, like because of the internet access for the vision models?
Okay, so recent vision models have gotten a little less aligned. Is that the point you're making?
Yeah.
I think that is true with respect to alignment to the brain to some degree, but that's a very messy area. So I'm not entirely sure I believe those results. It's also true the latest vision models are less aligned with the latest post-trained models if you query them in the same way that we did in our 2024 paper. But I think that's because the post-training requires querying them in a different manner. The embedding itself might not be quite as pure and faithful a representation of the underlying statistics of the data. So I think post-training changes the story a bit. And what was the second part of the question?
because like the vision models access the internet of
Oh,
the
is it
global
because they're being trained on synthetic data or the internet has become slopified?
Yeah, yeah.
I doubt it. I would be surprised if that's the explanation. It's possible. If so, that's very worrisome. But my guess is that hasn't made a dramatic effect yet.
Yeah, thank you.
Okay, thank you again, Phil, for this fantastic talk. Let's thank him again.
Thanks.
Okay, so lunch break. Lunch is somewhere outside. I'm not sure on that side or on the other side. Okay, on the other side, to the left.
We're gonna get started soon, so please find a seat. Please find a seat so we can start the lecture. Okay. Awesome. Thank you. Okay, so I guess we're going to get started so that we can try to keep the schedule as it is. It's my great pleasure to introduce our next speaker, Sander. He did his PhD in Ghent in Belgium, where you worked on echo state networks, right? Back then or not? You worked on echo state networks back then in Ghent or not really? You didn't? Because I did back in the day.
Yes. Okay. Yeah. No, I didn't work on echo state networks. I was in a group that was called the Reservoir Lab.
Yeah, I know.
Everyone else was working on echo state networks.
You are not. Okay.
I did
my
my
bad.
master's thesis with echo state networks,
But,
and then abandoned them forever.
Which was a good choice. But you worked on Lasagna, who's like a framework on top of Tiano, and then joined DeepMind and did a lot of amazing work in the space of diffusion models and generative models in general. And with that, I'll leave the floor to you.
Thank you. Yeah, so today I'm going to talk about diffusion models. I have this slide with like a little bit of an overview of my work over the years. So as Razvan said, I was at Ghent University doing my PhD before, and then I joined DeepMind 11 years ago now. And most of that time at DeepMind was spent working on generative models in various shapes or forms, initially with a focus on music and audio, because that was sort of the whole thing that got me into machine learning in the first place. So did a bunch of work on that, and then gradually sort of expanded my horizons and also started working on image generation, video generation, and a little bit of language modeling as well, which I'll actually briefly talk about later on as well. These days, I'm part of the generative media team at Google DeepMind, and we build models like Nano Banana, Gemini Omni, just anything Gemini that generates stuff other than text is the generative media team, basically. Cool. I have a blog, which some of you may know about. It's at sander.ai, really easy to remember. I write about generative modeling and diffusion models, especially these days. So a lot of the stuff that I'm going to talk about here is also covered in my blog. So if you're interested in sort of learning more or sort of recapping some of that stuff, you'll probably be able to find a blog post about it here. Right. So I'm going to do this in 6 sections. I'm going to give a very brief sort of basic overview of generative modeling, just to agree on some terminology. Then I'll talk about iterative refinement, which is the paradigm that most modern generative models use today. We'll go a bit more in depth on diffusion models, because that's what I'm here to talk about. And then I also want to talk to you about guidance, which is a trick that almost every diffusion model that's deployed somewhere nowadays actually makes very heavy use of. So it's important to understand that. Then I want to sort of take a bit of a different look at diffusion from a spectral analysis lens. So we're actually going to sort of take some Fourier transforms and then use that to understand what's going on. And then the last section is going to be a bit of a hodgepodge of everything else that I briefly want to mention that I don't have time to talk about more in depth about. All right, cool. So let's start with generative modeling. So this is going to be pretty basic, but just to make sure that we agree on the terminology here. So I'm going to presuppose that we have some distribution P of X that we want to model. And the only thing we have from this distribution is a bunch of samples. And so we have a bunch of draws X from this distribution P of X. That can, for example, be a data set of natural images. And then we're going to try and build a model of that distribution. And I'm going to make a distinction between explicit and implicit generative models. So in the explicit case, we're actually taking that P of X as a starting point, and we're going to try and build a model that gives us an estimate of P of X. And there's many sort of contemporary examples of that type of generative modeling. So there's autoregressive models, normalizing flows, VAEs, and diffusion actually also belongs in this category. And then on the other side, you have implicit models where you sort of build a mechanism that allows you to draw more samples of the distribution, but it won't tell you what P of X is. So you can draw new samples X from P of X, but it won't tell you what P of X is. And so the canonical example of that type of generative modeling is generative adversarial networks. To make generative models actually useful, usually we want to have some sort of control over them. You don't just want to generate a random sample of your entire distribution, but rather you actually want to capture a conditional distribution. So P of X given C rather than just P of X, where C is some sort of control signal. And I like to make a distinction here in terms of the density of that control signal, which can be quite useful in the context of diffusion models, which is, so we go from sparse conditioning to dense conditioning. Sparse conditioning, I basically mean you don't get a lot of bits of information about out of your conditioning signal. So if I have just a class label, for example, that I condition my generative model on, that's very few bits of information, but it can still profoundly affect what kind of samples you're going to get from your model, right? And then we can sort of go all the way to the right to get more dense conditioning signals. So signals that sort of constrain the generative model more, give you more information to start with. All the way on the right is this example of colorization. Like you can treat that as a generative modeling problem, where you already have a grayscale image and you just try to fill in the missing color information. In the modern era, you also have reference-based generation as a very common use case. Like, for example, you want to generate a video and you want to provide a photo of the main character that's going to play a role in that video. That's, I would argue, also a fairly dense conditioning signal. And then I want to talk briefly about mode covering versus mode seeking behavior. So when you train a likelihood-based model, usually the model is not going to be powerful enough to capture all the nuances of the data distribution. And the data distribution is usually going to be a very complicated thing, a very complicated object, very multimodal. And so when you're fitting a model, you're making a compromise. You have to sort of decide, how is my model going to use the capacity to try and capture as much of structure as possible? And the standard compromise is the mode covering compromise, which means that if a sample is likely under your data distribution, then it should at least have some probability mass under your model as well. So the example that I'm showing on the slide here, I'm representing this data distribution as a mixture of two Gaussians, and then our model is a single Gaussian. So we're trying to fit a single Gaussian to a mixture of two Gaussians, so obviously that's underspecified. That's not going to be able to capture the full complexity of the distribution. And then you can see what happens in the mode covering case is we're sort of stretching out the Gaussian so that the tails cover both of the modes, but in the process, we're actually putting most of the probability mass in the middle where there isn't actually any probability mass in the data distribution. So we're kind of overgeneralizing in a sense. And the way that manifests in the image domain is you're often going to see blurry samples from models like that, because they're sort of interpolating between multiple samples. And then the other option that we have is to choose a mode-seeking approach, where we're going to say, okay, if we can't have our data distribution fit the whole, if you can't have our model distribution fit the whole data distribution, let's just pick some modes and focus on those. Right? And that's what I'm showing on the right. Like you can basically just center your single Gaussian on one mode, and then you can ensure that any sample from your model is going to look like a data sample, but you're also missing out on entire modes of your data distribution. And so this is, in the image case, we talk about a focus on realism as opposed to diversity, which can sometimes be a useful compromise. And so the canonical example here is, this is what adversarial models do. This is what GANs do. Cool. All right. So now that we've sort of got that out of the way, I can talk about iterative refinement, which is essentially how all modern generative models tend to work. The key idea is divide and conquer, right? Generative modeling, especially of like high resolution images or video or whatever, or even long form text, it's a really challenging problem. It's really difficult to learn the complexities of those complicated distributions. And so the way we've addressed that is by essentially breaking up that task into much smaller, easier tasks, and then just learning to solve those one by one. And ideally, we do that in such a way that each of those tasks are similar enough that we can use the same model repeatedly, right? We can use the same model repeatedly to solve all these shorter tasks. and we ensure that all the steps are similar. And then to generate from such a model, we can just apply the model repeatedly, right? And almost all modern generative models operate in this way. There's some challenges that come with this, like you get discrepancies between what the model might see during training versus at test time, right? Because you're sort of feeding its own predictions back into the model to do this. And of course, it makes generation quite expensive because you have to run the model many times to generate a single sample. There's two main approaches today to iterative refinement for generative modeling. The most familiar one probably is autoregression, where you sort of turn everything into a 1D sequence and then generate it one step at a time. That's how modern LLMs work. And then diffusion is just another variant of that, where instead of using this sort of step-by-step sequence generation approach, you instead create an iterative process by first defining a corruption process, where you gradually corrupt the data points with noise, for example. And then you learn to gradually invert that corruption process step by step. But they're sort of two sides of the same coin. They're both implementing iterative refinement. Yeah, I think autoregression at this point probably don't have to explain. It's the chain rule of probability. You start with P of X, you decompose it into what I call sequential conditionals. These are simple scalar distributions usually, and then you just use the same model to model each of these sequential conditionals, and then you get a modern language model. You can also do that in pixel space. So this is work from my colleague Otto van den Noort, who actually leads the generative media team these days. So about 10 years ago, he was working on applying this autoregression idea directly to pixels. So taking an image and just sort of serializing it into a sequence and then predicting it one pixel at a time. You can do this works, but it's not very scalable. It works for like 32 by 32 images, and then if you want to go larger, you have to make your model really, really big to make this work. We also tried it for audio. We had a model called WaveNet about 10 years ago, which was basically this idea of taking audio signals and sort of viewing them. The digital representation of an audio signal is basically a sequence of amplitude values, right? You can kind of see that on the left here. If you zoom in completely, you can kind of start seeing the discrete elements. And then that's just a sequence. So you can do the exact same thing there that modern language models do on token sequences, and you can just predict it one by one. Back then, we didn't have transformers yet, so we used stacks of convolutions, and that was called a WaveNet. To make these approaches scale slightly better, there's one thing you can do, which is to apply them not directly in the input space, but rather in what's called the latent space. So first, you learn a higher level representation of your audiovisual signal. And usually that's done by like training an autoencoder or something to sort of learn a compressed representation that you can then reconstruct the original signal from with reasonable fidelity. So we're sort of trying to capture the perceptually meaningful structure in the signal in this more compact representation, which then becomes much easier to model autoregressively. Yeah. All right, cool. So now let's talk about diffusion models as sort of an alternative way of doing this iterative refinement. So as I already said, it's based on iterative denoising. So you take an example from your data distribution, in this case an image, and you gradually add noise to it. So you add a little bit at a time. And if you do that for long enough, eventually it should just start looking like there was only ever noise to begin with, right? You shouldn't be able to see anything left of the original signal. So at that point, it's sort of the corruption process has destroyed all the information. So we're going to try to formalize that a little bit. I won't use a lot of math. I won't use a lot of formulas in this presentation. I like to talk about the intuition behind things instead, but it's still helpful to have a few symbols to refer to different things. So concretely, with training data, I'm going to talk about x0 or x0. So we add this index, and this index is kind of a time index in the process. If you think of the corruption process as something that gradually happens over time, then this index is sort of telling you where in the process you are. So if t equals 0, we're at the start of the process, and no corruption has happened, and so that corresponds to the training data. And then somewhere in the middle of the process, we might be at some arbitrary time step xt, and there we might observe a noisy version of our data point, right? Because we've been gradually adding noise to it. And then if we take that all the way to t equals infinity, we will have added so much noise that the data disappears, right? That we only see noise at that point. Concretely in practice, this noise will typically be Gaussian noise. So these increments delta that I'm adding here are very small amounts of Gaussian noise. So with a small finite variance. And one nice property of using Gaussian noise for this is that you can kind of summarize all your progress in the corruption process up to a particular point quite easily, because if you take lots of small increments of Gaussian noise and add them together, that's just Gaussian noise again, but with a larger variance, right? So Gaussian noise has this particular property where it sort of composes additively. So that means we can actually always jump to any point in the process from the starting point, t equals 0. We can jump anywhere in the process with the simple formula, where xt is just equal to x0 plus some scaled amount of Gaussian noise. So here, epsilon, I will use to stand in for standardized Gaussian noise, and the Gaussian noise with standard deviation 1. And then we just scale that by some standard deviation sigma, which depends on the time step in the process. And then that will tell us what xt looks like, what xt looks like at time step t. So this sigma of t is what we call the noise schedule, right? So that's going to tell you how rapidly is our corruption process actually adding noise at different times. I'll add one remark here. So I'm kind of talking about this from a traditional diffusion perspective. You can also look at this from the flow matching perspective, which is very popular these days. One interesting choice there is they decided to flip this convention. So when they say t equals 0, they're actually talking about pure noise. And then they say t equals 1 corresponds to the data distribution. This is kind of arbitrary. You can do it in either direction, right? So I'm just sticking with the traditional diffusion convention here, but just to avoid any confusion, I thought I should mention that. Okay, so we can kind of summarize the process. We can jump to any point in the process. That's sort of the key thing that you need to remember here, because this is going to be very important for diffusion model training, where we want to simulate this corruption process. You don't want to have to do that iteratively. You want to be able to jump anywhere straightly. In reality, we complicate things slightly. So usually, instead of just adding a little bit of noise at every step, we're also going to rescale slightly. And the reason we do that is essentially to avoid things blowing up towards infinity. And if you don't do that and you add a tiny bit of Gaussian noise an infinite number of times, then eventually you end up with Gaussian noise with an infinite variance. And that's kind of, it's not insurmountable, but it's not super pleasant to work with. So what we prefer to do is to always rescale at every step to sort of keep the variance of xt at bay, basically. And so we can again summarize that by saying xt is now actually this linear combination of our sample from our data distribution and our noise with this extra scale factor for the data component, which allows us to sort of shrink it down over time as well. And then another change we're going to make is we're not going to run this process an infinite number of times, because that's too expensive. We're going to choose some maximal time step, capital T. Often people just set capital T equal to 1 for convenience. And that's where we're going to stop the process. And so we're going to have to make sure that we choose the hyperparameters of the process in such a way that at this time step capital T, it basically becomes impossible to distinguish what we have from pure Gaussian noise. All right, so to summarize with this forward process, we have the sigma of T. That's called the noise schedule. So that's going to determine how rapidly information gets destroyed. It controls the rate of corruption of the process. And then for this alpha of T, the scale factor for the data, we have many different possible choices that have been made in the literature. So traditionally, people like to do variance preserving diffusion, which basically means if you ensure that your data distribution has a variance of 1, and your noise also has a variance of 1, then choosing alpha equal to the square root of 1 minus sigma squared ensures that xt will always have a variance of 1. So that's variance preserving diffusion. And that's obviously, numerically, that's a nice property to have. There's a few other reasons why you might want that. But then people also figured, well, actually, it's not really a problem that the variance goes to infinity if we don't do this, because we will always take a finite number of steps. So we're not actually ever going to hit infinity. So there's some papers that say, let's just set alpha equal to 1 always, and then you get variance exploding diffusion. And that also works. It's just a different convention. And then arguably the most popular convention today is the rectify flow one or the flow matching one, where you say alpha is just equal to 1 minus sigma. And so that means that now we get this very simple linear interpolation between data and noise. So every XT is just a linear interpolation between the two. In terms of variance preservation, this has an interesting property. It doesn't preserve the variance, but it actually sort of shrinks the variance towards the middle of the process, and then it grows back to 1 again. But the key thing is it doesn't blow up, right? And so it turns out that's actually good enough. So people like to use that because it's simple. Cool. All right. Now, the backward process is where we're going to do the actual generative modeling. So here we actually want to start learning something about a data distribution. Because if we want to go in the other direction, the deltas that we have to add now, they're not just going to be random Gaussian noise, right? Because if you add Gaussian noise to Gaussian noise, you just get Gaussian noise. You're not going to get any structure appearing in that signal. So here, knowing what this delta has to be to go to the data distribution actually requires some understanding of that data distribution. And that's how you can actually start using a denoiser to do generative modeling, right? So now we have to learn what these deltas are going to be. To explain how that works, I like to use this geometric explanation. So basically what I'm doing here is I'm projecting very high dimensional objects, images, down to 2 dimensions, because 2 dimensions is all I have on my slide. So that's all I have to work with. So I'm going to try and represent these images as points in image space, like in pixel space. And then we're going to sort of try and look at what a diffusion model actually does with these points. So I have a sample from my data distribution in the bottom left. That's X0. And then I've artificially constructed a point in the reverse corruption process, right? Like we're going in a backwards direction. We're doing generation here. So at some point we will observe a noisy image, and I've artificially constructed that here from the data with the formula that I showed you earlier, because that's also what we do during training, right? We're sort of going to pretend that we got XT through diffusion sampling, but actually we're artificially creating it by taking this training example and adding noise to it. That's what I've done here. So we're at time step t, we're in this in XT. That's our current observation. And then what a diffusion model is going to do is it's going to take that noisy observation and try to predict what was the clean version of this image. Like where could we possibly have come from if this is a noisy observation that I'm currently seeing? And this is an ill-defined task, right? Because the whole point of adding noise to these images is that it corrupts them, that it removes information from them. So you can't actually predict with 100% accuracy what the original image was, because some information has in fact been removed. And there's potentially many possible images from the data distribution that could have given rise to this particular noisy observation. So what we're asking this denoiser to do is an impossible task, right? There's actually a whole distribution of images that could have been the original image, and we're asking it to make a single prediction. So what is this model going to do? Naturally, it's going to predict the centroid. It's going to predict the mean of all these possibilities. And if you try to visualize that, usually what that will look like in the image domain is a blurry image, right? Because it's sort of averaging out over all these images where the details are slightly different. And so the details average out, but the global structure is roughly the same. And so you get this blurry image as a prediction. So the way to think about that actually is that this denoiser is not predicting a single image per se, but rather a region of the image space that contains all the possible images that could have given rise to this particular noisy observation. By the way, if at any point something is not clear, I'm okay with you interrupting me. If you do have sort of longer form questions or maybe more philosophical questions, I would say let's leave those for later in the week. I'll be around until Thursday evening, so you can just come find me to have those types of discussions. Cool. All right, so we're sort of predicting a region of input space. That's what I want you to remember. And then once we've made that prediction, we're going to take a small step in that direction. We're not going to jump all the way to X0 hat, because then we would just get a blurry image, and that's not really the point. We're trying to sample from our data distribution here. So we're only going to take a small step in that direction and then just ask the model again. And you can compare this a lot with how we do optimization of neural networks, right? So when we're training a neural network, obviously we're operating in the weight space of the neural network then and not in the input space. But we're kind of doing the same thing where we're calculating a gradient that gives us an update direction. But we're not just going to take a massive jump, right? We're going to take a small step in that direction because we know that that update direction is only really valid locally. It's an approximation, right? And the same thing is true here. We know that this direction is sort of valid locally, but if we treat this as a global update direction, we're just going to end up in a blurry image. So that's not really the point. So we take a small step, and then we're going to do something that is a little bit different from what we usually do in optimization of neural networks. Is we've just removed a bit of noise by taking a small step, and then we're going to add some noise back. So this might seem counterproductive, but of course the key is that you never add as much noise as you just removed, right? Because otherwise you wouldn't be making any progress. You add a little bit of noise back, and what that's going to do is it's actually, I mean, there's theoretical reasons why this makes sense, which I'm not going to go into. But in practice, why people often do this is it kind of helps avoid accumulation of errors. Because in practice, what we're going to do is we're approximating this update direction with a neural network, and that neural network is going to make mistakes. And then we're using that information to calculate a new input for the next iteration. And so if you're not careful, you're going to get error accumulation, right? You're going to sort of feed the errors of the neural network back into itself, and it might go off the rails. And it turns out if you do this, if you apply this trick where you add a little bit of noise back, that actually greatly robustifies this procedure. And so often you can sort of see great improvements by doing this sort of 2 steps forward, 1 step back type sampling. I will say, though, that there are many diffusion sampling algorithms that do not do that. I think the standard flow matching sampling algorithm, for example, is not stochastic. So there you don't have this sort of this extra step. And that also works, but these algorithms have sort of different trade-offs in how well they work depending on how many steps you take, things like that. But in standard diffusion, it's common practice to add a little bit of noise back at every step. So that brings you to a new iterate, xt minus 1. So we sort of made progress in the reverse process. And then the same thing just happens again. We just rinse and repeat. So now we're going to, again, make a prediction with our denoiser. That prediction is now going to be a different prediction than what we saw before. And the reason is, of course, that the noisy observation that we're starting from right now is slightly less noisy, right? So there's more constraints. And so the prediction that the denoiser is going to make now is actually going to correspond to a smaller region of input space, because there's fewer images now that could have given rise to this particular noisy observation. So we sort of locked in a little bit of the structure there. And of course, if you keep doing this over and over, eventually that region is going to shrink down to a point, right? And at that point, you're done sampling, because then you've sort of chosen a particular sample from your data distribution. Yeah, again, might add a bit of noise back depending on the algorithm. And that just goes until t equals 0. So all of this that I've talked about so far is sort of based on this idea of a denoiser. So the denoiser observes a noisy image and predicts a clean image. Now, traditionally in the diffusion literature, almost all papers talk about predicting the noise rather than the data. So rather than predicting x0, you're actually taking in your xt and you're predicting this epsilon component. And it turns out those are actually equivalent in many ways. So if you have a model that predicts x0 given xt, then you can actually take its prediction and turn that into a prediction of epsilon, because these are linearly related given xt. Like xt is equal to alpha t times x0 plus sigma t times epsilon. So that's a linear relationship. So if I give you, given xt, I can give you a prediction of x0, and I can just plug those two in there, and then I can use that to calculate the corresponding prediction of epsilon, right? So there's a linear relation there. So whether you predict epsilon or x0, it actually doesn't really matter, because you can convert one into the other. That's not entirely true, because it does actually affect the relative weighting of the noise levels in the loss function. And that is really important. And that's why people still sort of consider these different, carefully consider these different prediction targets. So we can predict x0, as I've been talking about so far. We can predict epsilon. We can also predict other things. We can predict any linear combination of epsilon and x0, because with any linear combination of those two, you can always convert predictions of one linear combination into predictions of another linear combination. And so people have done that with V prediction in the context of diffusion. And then the default prediction target in flow matching is also an example of this. It's usually epsilon minus x0. And this is what they refer to as the velocity or the flow. But these are all equivalent. Once you have a trained model, you can take a flow matching model and convert it into a traditional epsilon prediction diffusion model really easily, or vice versa. It's just during training, it has an impact on the training loss. So that's why it's still important. I also want to highlight that the same is true for whether you predict x naught or xt minus 1. So in the original DDPM paper, so denoising diffusion probabilistic models, they actually formalize this slightly differently because they say we're going to make the corruption process discrete. So there's going to be, for example, 1,000 discrete time steps. And then they say what the diffusion model is actually doing is it's learning to reverse one step at a time, right? So from xt, we're predicting xt minus 1. And everything I've been explaining so far is actually about predicting x0, like going all the way back to the data, not just one step back. But again, it turns out these are equivalent because you have these, you don't have to like try to parse this. This is just, it's basically a proof. But because you have these linear relationships between all these quantities, whether you predict xt minus 1 or x0, these are equivalent. You can always write a prediction for one in terms of a prediction of the other given xt. Okay, and then there's one more perspective on diffusion that I do have to mention, which is not so commonly talked about these days, but it was very key to sort of the original development of it, which is score matching. So that's this idea of training a generative model by learning the score function. And the score function is defined as the gradient of the log likelihood of log of p of x with respect to x. So we're basically taking the gradient with respect to the input. And what that is going to give us is a direction in which we should move to make a particular input more likely under the distribution, right? You're sort of finding gradients that point to regions of high density. That's what the score function is. And score matching is just the idea of applying a mean squared error to that. So like if you have the score for your data distribution and the score for your model, you just train that with mean squared error. There's a bit of a challenge there because you don't actually have the score for your data distribution. You can't measure that. But it turns out there's ways around that using something called denoising score matching, which I won't go into. But the key thing is that you can kind of construct a model like this, a score matching model. And then if you start looking closely at what you're actually doing, it turns out you're just learning a denoiser. Like learning to predict this quantity is the same as learning denoising. So this is, again, actually turning out to be a linear combination of x naught and epsilon. And a way to sort of think about that intuitively is that if I give you a noisy input and I ask to look at the score is going to point to regions of high density, right? It's going to try and make that input more likely. And for a noisy input, the direction in which you should move to make it more likely is usually the direction that removes the noise. Right? So that's sort of roughly intuitively how denoising and score matching tend to coincide. I do briefly want to mention that because it does sort of make guidance a little bit easier to understand, for example. But yeah, I guess mostly if you're like doing flow matching stuff, you don't really need to think about this much. Okay, right. Any questions so far? No? Shall I continue? Oh, maybe one there. Sorry.
What is flow in this context?
Flow, yeah, flow is one of those words that people like to use without defining them, isn't it? So flow, I think flow in this context refers to, if you think about what a diffusion model does, it sort of traces a path through the input space from a noisy data point to a clean data point, step by step, right? And in that process, you're actually traversing a trajectory through the input space, right? Like at every step, you can sort of look at it and visualize it if it's in the image domain. And so you sort of trace out this path, and basically the flow is sort of the direction that you're moving in at any instantaneous point on that path. That's like, so you're sort of, if that path is curved, then your flow is going to be this vector that sort of slowly rotates as you progress, if that makes sense. So it's sort of it's the gradient of the path that you take through the input, basically. Yeah. All right, cool. Where am I for time? Oh, doing okay. All right, I'll continue with guidance then. So guidance, I like to talk about as a cheat code for diffusion models because it makes them perform way better than they have any right to. And I show some examples of that later. So guidance enables trading off sample quality for diversity, and that's actually a very useful tool for practical generative models at scale, where often we can achieve diversity through other means. So we can actually, in the core diffusion mechanism, we can actually focus on sample quality and then bring diversity back in other ways. And it basically allows diffusion models to punch way above their weight, which is good because sampling from diffusion models is expensive. And so if you can make them smaller, that is actually very valuable. And in practice, we do see, for example, if you compare the typical size of a modern language model with the typical size of a modern image generation model or video generation model, those models tend to be a lot smaller still today. To explain what guidance does, I think it's, again, useful to use this type of diagram. Again, keeping in mind that this is actually happening in a very high dimensional space, not in two-dimensional space. Often when you, in machine learning, when you try to generalize from 2 dimensions to high dimensions, you often end up fooling yourself. You have to be very careful with that. In this case, you'll just have to trust me. It's instructive. So with classifier guidance, we modify the sampling procedure. And the way we're going to do that is we're going to, again, make a prediction with our denoiser to sort of determine what direction we should be moving in to sort of bring the data point closer to the data distribution. But we're also going to find a classifier, like this could be like an ImageNet classifier. And we're going to ask that classifier for its gradient with respect to the input of a particular class. Like in this case, let's say I really want this image to look like a rabbit, right? And so we're going to classify the image with our classifier, but then we're going to take the gradient of that output with respect to the input image. And so the idea is that if we follow that gradient, we make that class label more likely, right? And so hopefully by following that gradient, we would also make the image look more like a rabbit. So this gives us another update direction in input space, right? Because the denoiser is also giving us an update direction in input space. So we have these 2 vectors now, and we can just do a little bit of vector arithmetic with them and just add them together. If we add these 2 together, we can now use that as the new update direction in our sampling procedure instead of just the denoiser direction. And then it turns out that if you sort of reverse the process from sort of going from the score matching perspective back to probability, you can actually see Bayes' rule in this. So I want to explain that a little bit more. So what we've just done is we've taken a classifier gradient and we've added that to our denoiser direction. Now, as I said before, the denoiser direction, you can think of that as corresponding to the score function, right? So that's, do I have a laser on this actually? Yeah, I do. So that's this. So that's the denoiser direction. And then the gradient of the classifier that we've just added is this, right? And if you add these 2 together, you can see that that actually corresponds to the gradient of a conditional distribution. Right? So this is still a score function, but now it's a score function of this conditional distribution rather than this unconditional distribution. And then if you sort of go backwards from here to here by undoing the gradient and undoing the logarithm, you recover this, which basically says the distribution, the conditional distribution is proportional to the unconditional distribution multiplied by the probability of this classifier, which is, this guy. So that allows us to take an unconditional diffusion model and then turn it conditional after the fact, right? Just by introducing this classifier. There's one big caveat here, which is that this classifier has to be noise robust because we're going to be feeding it noisy images, right? So you can't just take an off-the-shelf ImageNet classifier. That's not going to work very well. It actually has to be noise robust. But so that allows you to sort of steer the sampling process using an external model without changing the core generative model. And the real power of this idea is actually unlocked when we start scaling these vectors before adding them together. So we can actually take our classifier gradient and we can say, scale that by a factor gamma, and we'll call this the guidance scale. And then we let that determine our new update direction. Now, what does this actually mean? It's basically saying, I would really, really, really like it if this image looked like a rabbit, right? We're sort of putting more emphasis on that update direction rather than the denoiser direction. So we're kind of changing the trade-off between staying true to the original unconditional distribution, the prior, if you will, and sort of following the gradient of this classifier. And so this is effectively classifier guidance. So you have this guidance scale, which you can kind of think of as a sampling temperature. and then we basically use that instead of the denoiser direction to sample. So if you look at what that actually means, so we can sort of apply the same treatment here. So now we again have our score, right? This is sort of what the diffusion model captures. And then we have this classifier. And now there's this scale factor gamma here, the guidance scale. So we get this new distribution, which I've called P of gamma x given C. And then again, if you sort of undo the gradient and the log, what we see now is that this new distribution is actually proportional to P of x times the distribution of the classifier raised to this power gamma. And so this raising distributions to powers, that's what you do when you tune temperatures, right? Like if you're sampling from an autoregressive model, a language model, you will often sample with a different temperature. And that's effectively what you're doing there, right? You're sort of raising it to an inverse temperature. So in this case, the gamma that we have here is actually an inverse temperature. So you can think of 1 over gamma as being a temperature, which means that if you want to lower the temperature, you need to increase the guidance scale, right? Like if you pick a larger guidance scale, then implicitly what you're doing is you're lowering the temperature of this distribution. And what does lowering a temperature of a distribution do? It actually puts more mass on the modes, right? Like things that are already very likely become even more likely, and things that are unlikely become extremely unlikely. So you're sort of concentrating the mass. And that's sort of effectively what we do here when we pick a guidance scale greater than 1, because then we're effectively lowering the temperature of that distribution. You could imagine doing it in the other direction as well, right? You could increase the temperature of that distribution, and that will make it more and more uniform. And then effectively, at a very high temperature, this factor sort of disappears because it becomes uniform, and then you recover your unconditional distribution. Okay, nobody actually uses classifier guidance these days. But what they do use is called classifier-free guidance. But it's helpful to explain classifier guidance first to understand why classifier-free guidance is called classifier-free guidance. As the name implies, we are not going to use an external classifier here. We're going to do this purely with our generative model. But what we're going to do is we're going to train our generative model to be conditional from the get-go. So we're going to give it a conditioning signal during training so that it can understand how that influences the data distribution. But like maybe 10% of the time or so, we're going to drop it out. So 10% of the time, we're going to hide the conditioning signal so that we have one model that can operate both as an unconditional and as a conditional generative model, depending on whether we provide the conditioning signal or not. And so that allows us to make 2 predictions with this model. So we're sort of back where we were before, where we were predicting the denoising direction. We're going to make an unconditional prediction for the denoising direction. And we're also going to add to that a conditional prediction for the denoising direction. And what you'll typically see is that if you try to visualize these, the conditional one should be slightly less blurry. And why is that? It's because the conditioning signal is constraining us more, right? It's giving us additional information that constrains the number of possibilities, like the number of possible images that can give rise to the current noisy observation. And so this should be a slightly less blurry prediction. And what we're interested in is actually the difference vector between these 2 predictions. Yes? Can you speak up, please? Or use a microphone, even better.
Thank you. Sorry for interrupting.
No worries.
If the blurriness comes from the fact that the initial image could have been a bit tilted or like the details get mushed, how does the conditioning make it less blurry? I don't understand.
Okay, so let's say we're working with like the ImageNet dataset, right? ImageNet has 1,000 different image classes. And if you train an unconditional model across all of these classes, when you start sampling from the model has no idea what class the image is going to be, right? So it could be any of the 1,000. But if I then tell it, actually, this is a rabbit, right? So that's sort of narrowing down the distribution quite significantly, because now we know that that the original image was of a rabbit. So there's a lot of sort of slight deviations in the image that actually don't make sense if this image was a rabbit. And so that's why there's sort of fewer possibilities now.
So in that example, the original guess would have been like a mess instead of a blurry squirrel.
A what, sorry?
in the ImageNet example, the original prediction, the X0 hat, would have been a mess?
Yeah, I mean, it sort of depends how far along you are in the denoising process, right? Like at the very start of it, yes, absolutely. But then as you sort of go along in the sampling process, you sort of start narrowing things down, right? And so at this point, it's like, yeah, I mean, at this point, maybe this could still be like another rodent or something like that, right? But if we then actually tell the model, no, this is definitely a rabbit, then it can actually narrow things down and give you a slightly less blurry prediction.
Thank you.
Make sense? Yeah. Cool. All right. So we have these two predictions, and what we're interested in is the difference, the delta between these two predictions. This is again a vector in input space. And what we're going to do in classifier-free guidance is we're going to amplify this vector with the guidance scale. And that is then going to determine our new update direction. And what we've done here is actually very similar to classifier guidance, even if it doesn't look that way, because what we've actually done is we've implicitly constructed a classifier using our generative model. And this is called a Bayesian classifier. Like it's sort of a way of constructing a classifier using a generative model where you basically say, I'm going to train a generative model for each of my possible classes. And then to classify an image, I will just measure the likelihood of my image under each of those models and see which one is highest. That's a Bayesian classifier. And that's sort of implicitly what we've done here by contrasting these two predictions. And we can basically then, again, take that classifier direction and amplify it, just like we did with classifier guidance. And then, as before, the rest of the procedure is completely unchanged. So the sampling procedure proceeds as normal, but using this new update direction. And this is what really unlocks the power of guidance. So as I said, this delta is effectively a Bayesian classifier. And ultimately, what we've done here is just applied Bayes' rule twice. We've applied Bayes' rule to construct this classifier, and then we've applied Bayes' rule to sort of decompose this conditional score into an unconditional score. And this is basically the classifier here. This difference is what has become our classifier. And as I said, during training, we can get both the conditional and unconditional distribution in the same model by training up a conditioning dropout. So we usually give it the conditioning signal, but then 10% of the time, we drop it out. The reason why this works so much better than classifier guidance is that if you construct a classifier from a generative model, it's going to be way more robust. Classifiers that are trained from scratch as classifiers actually don't have to learn that much about the data distribution, right? They only have to be able to recognize some patterns that allow for a good classification to be made. But that means that there's probably a lot of structure in the data that they're not modeling. So if you then take a gradient with respect to that classifier, you're sort of asking for adversarial examples, because that's effectively also how adversarial examples of classifiers are found, right? You sort of take the gradient with respect to the input, and you sort of nudge it in weird directions until a class label flips or something like that. And it turns out there's actually tons of adversarial directions in these classifiers. But a Bayesian classifier has way fewer of these because it's constructed from a generative model. Yes.
Is it common in practice to use the same condition generation for guidance at multiple steps? So for example, we used at time step 50, and then we use the exact condition generation to draw the direction for the next time step.
So so at every step during sampling, you will make two new predictions, but the conditioning signal tends to be constant, right? If that's what your question is. Like the conditional signal is usually in practice nowadays, like modern production diffusion models are text to image or text to video, right? So it's not a class label, but it's actually an entire text prompt that you're conditioning on. And that is usually
using it like once and using that direction multiple times. So using the condition on that noisy sample to get the direction and using that same direction for the next iteration.
I see what you mean. No, usually we recalculate this every update direction. And I think that's kind of important because you're sort of contrasting these two model predictions, but those two model predictions are also going to change at every step, right? So the difference direction between them is also going to change at every step.
One final follow-up. Would it be like more likely to work if the diffusion time steps are a higher number of steps? So each
You mean like reusing the?
Yeah.
Yeah, I would imagine that if you have a lot of steps, then probably the direction doesn't change that much from step to step, and you could probably get away with sort of reusing it a few times before recomputing it. Yeah. All right, cool. Yes. So what does guidance actually do? To find a nice demonstration of this, I have to go back to 2021 because ever since then, any diffusion paper just enables guidance and leaves it on for all experiments because it's just such a crucial thing to get good results from these models, right? So nobody actually turns this off anymore. And so it's really hard to find modern examples of samples without guidance. In fact, I think some of the sort of flagship models out there, if you sample from them without guidance, you'd be surprised at how bad they are. The guidance is really doing a lot of work. And this is from the GLIDE paper from OpenAI from 2021. It's one of the first sort of text-to-image diffusion models at scale, where they neatly demonstrate this by showing samples without guidance on the left and with guidance on the right. And you can immediately see two things. One is diversity goes off a cliff, right? All these samples on the right look much more similar to each other than the one on the left. But if you look at the prompt and the overall sort of adherence to that prompt and the quality, obviously the ones on the right are preferable, right? So if you're just after a single sample, you would pick one from the right side. If you're after a lot of diverse samples, it's sort of a trade-off where maybe this is not ideal, but it turns out you can actually bring back diversity in other ways. Like one very common trick that modern diffusion models use is they first ask a language model to rewrite the prompt, right? You give it the user prompt, and then the language model rewrites it. And you can just do that like a few times, right? Just rewrite it 5 times, and then sample 5 samples from your massively guided diffusion model, and those will look very different because the conditioning signals are different. So yeah, that's why this is still such a useful trick today. Another example from the same paper, kind of the same story, much more similar on the right side, but also much better quality with respect to the prompt. Yeah, if there's one thing you remember from all this, it's all just Bayes' rule. You just apply Bayes' rule twice, you get classifier-free guidance. Okay. Actually, yeah. There's one caveat to this. So like all this is a really nice story in terms of classifiers and stuff. It turns out it might actually be a little more complicated than that. So it's a really nice paper from a few years ago where they basically say, rather than contrasting an unconditional and a conditional model, you can just take your model and during training, just save an earlier checkpoint of it. Like maybe 70% of the way, save that checkpoint as well. And then just use that as a stand-in. So like contrast between your final checkpoint and your earlier checkpoint. And that's going to give you an update direction that sort of points from a slightly worse model to a slightly better model, right? So what if we then scale that update direction? Do we get better samples? The answer is yes. So that also works, guiding a diffusion model with a bad version of itself. This paper also has a really nice analysis of what guidance is actually doing, which is worth checking out if you're interested. All right. How am I doing for time, actually? Sorry. We started a little bit late. Okay, I'll just keep going. All right, spectral analysis. So the next thing I want to talk about is sort of Fourier view on diffusion, because I think that's quite instructive to understand why it's been so effective for modeling images in particular. So if you think about natural images, and you take the Fourier transform, and you look at sort of the distribution of the different frequencies in an image, usually what you'll find is a power law. So the power or the energy of a particular frequency is proportional to the inverse of the frequency raised to some power. And so if I plot that on a log-log plot, which I've done here, I get a straight line that slopes downward. Right? So, and this is sort of a law of nature. Like you can do this with almost any image. You calculate the spectrum and you look at sort of the distribution of frequencies. It's going to look like this. In fact, I will show you that is the case in a bit. But so this is sort of a schematic diagram of the same. If we do the same thing with Gaussian noise, what's interesting about Gaussian noise is it has a flat spectrum. Gaussian noise actually, in expectation, sort of contains all frequencies in equal measure. So if you look at the spectrum of that, it's going to be a horizontal line. Actually, if you take an individual Gaussian sample and look at the Fourier transform of that, then does anyone know what the Fourier transform of Gaussian is? it's a Gaussian, right? You're just going to get Gaussian noise again. So, but in expectation, that Gaussian noise becomes sort of equal energy over all the frequencies. So what happens if we then take a sample from our image distribution and a sample from the noise distribution and add them together? That's going to have a spectrum with this shape. So the Fourier transform is linear. So we can just add up the spectra, but I'm plotting them here on a log-log plot, and that's why this doesn't look additive, right? But effectively, this is linear, and so what we get is that where the noise spectrum is dominant, we're sort of going to have our new spectrum follow the noise spectrum, but where the image spectrum is dominant, the new spectrum is going to follow the image spectrum. So you get this sort of hinge shape where up to a certain frequency, we follow the image spectrum, and then from that frequency onward, we follow the noise spectrum. And that's sort of what you see here, right? And so what that means is effectively that adding this certain amount of noise to our image has actually only erased the high frequency information in our image. Right? The low frequency information is much more powerful than the noise and sort of juts out above this waterline, basically. But the high frequency information has much less power, and so that is sort of being overpowered by the noise here. And if we increase the noise level, then basically this noise floor shifts up, like more energy, right? And what we see is that this hinge actually shifts left. So this shifts to a lower frequency. So if you add more noise, we're actually destroying more of the lower and lower frequencies that are present in the image. And of course, if you then use this as a basis for a generative model where you reverse this process, what that means is that your diffusion model or your denoiser is actually going to start out by predicting the low frequencies and only the low frequencies. And then as you sort of remove noise, it's going to gradually add more high frequency information step by step. So it's sort of generating from low frequency to high frequency. And therefore, diffusion is spectral autoregression. You're effectively doing something that looks a lot like autoregression, but in the frequency domain, starting from the low frequencies and then generating the higher frequencies conditioned on the low frequencies that you've already generated. I usually ruffle a few feathers with that because it's very hand wavy, but I think it's a very useful intuition to have about how these models actually work in practice. I said I was going to show you that this is actually true, and that I'm not just making this up. So here I have 4 images from the ImageNet dataset, and I've calculated their Fourier spectra. Images are 2D objects, so their Fourier spectra are also 2-dimensional. I have here the magnitude component and the phase component, because these spectra are complex valued objects. We're going to throw away this mess. We don't care about phase. We care about the magnitude here, the energy that is present in each frequency. And we're going to summarize that into a 1D curve, because these are a little bit easier to work with. And this is something called the radially averaged power spectral density. So I'm basically just taking these radial slices from my Fourier spectrum, slicing them, and then basically just averaging all of those together. And then for these images, we get this. So this is for a single image. And if you look at a spectrum, it already has a very good approximation of this power law structure, right? Because what you get is almost a straight line. Obviously, there's a bit of noise there because we're looking at a single image. But if you look at a full data set of images, I think I looked at like 100 images or something, you get something like this when you average them all together. So that's, that's way closer to a straight line than I thought it was going to be. Because those diagrams I was showing you earlier, I drew all of those before I actually looked at this, right? So I drew all those diagrams and like, oh yeah, that's probably what it's like, right? And then I calculated this and I was like, yeah, okay, this is way closer to the truth than even I thought it was. So you get this sort of power law spectrum here, and then for noise, you get the flat spectrum, the horizontal line. And then if you combine the two and you look at the spectrum for that, you get this hinge. It's maybe not quite as well defined as in my schematic diagram, but it's there, right? You sort of get the spectrum following the noise where the noise is strongest and following the image where the image is strongest. And then, of course, if you increase the noise level, the hinge shifts left. I have this animation here that sort of shows this. So this is calculated on a data set of images, but I'm showing a single example from this data set on the right. And you can kind of see, if you follow along, like when the noise level is at the top and it sort of it juts out above all of the image content, then you can actually see in the image that you can no longer see anything, right? You can only see noise. And then when it's sort of halfway, you can sort of see in the image that you can still make out it's a truck. You can still see the large scale features, the low frequencies, but all the detail is gone, right? You can't really see the foliage on those trees anymore, for example. So yeah, there's this nice correspondence. Okay, last thing I want to talk about is just a bunch of random stuff that I didn't have enough time for to put like a whole section in. I think one thing that's worth talking a little bit about is how do we actually train denoisers? How do we actually train these neural networks that do this denoising task, right? And traditionally, people use UNets for this. So UNets are these convolutional neural networks that have this interesting U-shaped structure where the input and the output have the same topology, right? Because you take as input a noisy image and your output is a denoised image. So the prediction space has the same topology as the input space. And so UNets achieve that by having these skip connections and then this sort of U structure where you operate at progressively coarser resolutions, but you always go back to the full output space. So people originally developed this for segmentation, image segmentation, biomedical image segmentation even, I think. And then the diffusion community just sort of adopted it as the architecture of choice. Nowadays, though, it's all transformers. People figured out pretty quickly that transformers can do this well as well. And as you scale up, transformers become better. It was ever thus. So now everyone just uses transformers. Another architectural discussion that I want to highlight is the case of video specifically. So we've already talked before about how autoregression and diffusion are sort of two forms of iterative refinement, and you can use either for any modality, right? You could do an autoregressive model of video. The problem is that a video is this 3D cube, basically, right? A 3D volume with a height dimension, a width dimension, and a time dimension. And if you want to model that autoregressively, you have to somehow turn that into a sequence, right? So that's going to be a very long sequence if you roll out that whole volume into a flat sequence. So what people do instead is they prefer to use diffusion for video generation, because then you can sort of generate this whole volume in parallel, right? And you don't need as many steps. But what if you want to generate video in real time, right? What if you want to do sort of real-time interaction where you respond to the user in real time? Then diffusion over the time dimension just isn't really an option, right? You can't predict what's going to happen in the future. So there's this interesting compromise that people have been experimenting with where you do autoregression in time and then diffusion over the spatial dimensions. And you sort of have this nested loop where your model is actually an autoregressive video model over the time dimension, but then at each time step, you have a diffusion model that's generating the next frame. And so this is sort of being explored in the context of real-time generation, like the Genie model from GDM, for example. Another thing I want to briefly mention is that these days we don't do diffusion in pixel space or in the input space in general. Just like I talked about in the context of autoregressive models, we tend to use latent representations. And these are just compressed representations of the input. So we are essentially doing compression, but in such a way that we preserve the original topology of the images, which for example, standard compression techniques like JPEG and H.264 don't do that, right? They sort of, in the process of compressing, they destroy the topology. And that makes it really hard to use generative models to generate sequences in the compressed domain because there's just no structure that can be used as an inductive bias in the denoiser model or in the generative model. So the reason we do our own compression, we roll our own, is because we want to preserve this topology. We basically want a compressed representation that still has sort of the same spatial structure, but at a lower resolution, right? We went from, in this example, from 256 by 256 to 32 by 32. And then we compensate for that a little bit by having some extra channels so that we can still capture some of the high frequency structure that would be lost if we were to just take this and resize it. Right? If you just take an image and resize it, you lose all the high frequencies. But if you learn a representation, you can actually try to learn to capture the high frequency information that's perceptually relevant in these additional channels. And then hopefully this still looks and behaves as much like pixels as possible so that we can just apply diffusion to this more compact representation. And so that's how most modern state-of-the-art text-to-image and text-to-video diffusion models work. I will say on the image side, pixels are making a comeback. People are sort of tired of having to first train a compressed representation and then train a diffusion model It's much nicer if you can just train it directly on pixels, but it is, of course, more expensive. But for images, I think people are sort of starting to feel that the cost is worth it. For video, unfortunately, that's not going to happen anytime soon because video is just massive tensors, right? If you try to store a 30 FPS 1080p video, like 10 seconds of video in like a pixel tensor, that's more than a gigabyte of data, right? So if you have a batch of videos that you want to train on, you're just going to run out of memory. It's just not feasible. And then this approach of learning a latent representation often allows you to save 1 or even 2 orders of magnitude of space. In practice, though, these are very low-level representations. So there's this nice diagram from a paper called EQVAE, where they talk about how to regularize these latent spaces to make them easy to diffuse. But I like this visualization because they actually show for a few different latent spaces, like what do these latents actually look like if you try to visualize them, right? What if you take the 3 most prominent PCA components of the latent space and map them to RGB? What does that look like? Well, it looks like this. And if you look at these latents, you can still tell what the animal is, right? Like the high level information in these images is basically unchanged in the latent space. It's only the very low level stuff like the grass in the background here that's maybe abstracted away a bit in these latents. But they leave the high level structure untouched. And that's why I like to call latents fancy pixels, basically. They're just pixels, but with a little bit of extra information. All right. Another topic that I didn't have time to touch is distillation. So distillation is about reducing the number of steps that you need to sample from a diffusion model. And this is generally true in iterative refinement setting. Sampling is expensive because you have to run the model many times. So the fewer times you can run the model to get good samples, the better, right? And so distillation is this, sometimes called step distillation, is this idea of trying to reduce the number of steps required. You can usually kind of think of that as sort of tracing out this path through input space that we take over the course of sampling. Like I've sort of tried to indicate it here with a dashed line. You can trace out this path, and then we can ask the question, for example, okay, rather than sort of learning the tangent to this path and sort of predicting it at each point, can we just learn to go directly from here to here? Like, can we directly learn to predict where the path is going to end up? And if you have a deterministic sampling algorithm, like in flow matching, for example, you can actually do that, right? Because there's always a one-to-one mapping. You're always going to end up in the same point. So you can actually just learn to predict that directly. That's what consistency models do. Of course, this is a much harder task. So often this doesn't work quite as well. So people often compromise and sort of do multi-step consistency or things like that. But this is kind of the gist behind distillation. My latest blog post is all about flow maps, which is a paradigm that's very popular right now for distilling diffusion models. So if you're interested in that, I recommend checking that out. Yeah, before I finish, I do want to talk a little bit about diffusion for discrete data, because that's sort of a hot topic these days. So everything I've talked about so far is about continuous data. So what do you do when your data is discrete? You have 2 options. One is you have to redefine your corruption process to be compatible with discrete data. So for example, gradual masking or uniform random noise in a discrete space. The other option you have is to embed your data in a continuous space. And for a while, these 2 were sort of equally popular, and then the former sort of completely displaced the latter. So I'd say like the last 2 years or so, 2024, 2025, everyone was doing discrete corruption processes. And then since 2026, I would say this option is making a comeback. So that's why I wanted to put it in here, because I should have showed this. So this is from a survey paper on diffusion language models, where they kind of show this. I think yellow is continuous, discrete is green, and you can kind of see after 2023, there's no yellow. There's like one lonely thing here. So that idea kind of died out, but this paper was from 2025, and in 2026, it's actually making a comeback. I did some work on that myself some 4 years ago. It's a paper called Continuous Diffusion for Categorical Data. The idea there was to sort of try and do language diffusion with continuous mechanisms, but in a way that would sort of not alienate existing language modeling practitioners. So we wanted to stick with a standard transformer, and we wanted to make sure that we could train it with a standard cross-entropy loss that everyone is used to from autoregressive modeling. And we ended up with something that actually looks a lot like BERT. So BERT, if you remember, is this sort of masked language modeling approach where you try to learn good representations by basically masking tokens and then trying to predict the masked tokens given the unmasked context. And what we did with CDCD is kind of similar, except that the noise is not masking noise, it's Gaussian noise on the embeddings, right? And you're sort of trying to disambiguate these superpositions of different tokens. So we like to frame this as a kind of multidimensional version of BERT back in the day. Okay, and then the last thing I want to say is in the context of, I work on these models in sort of industry context at scale. And one thing that's super, super important is the data that you train these models on. And this is something I feel that in academia doesn't get a lot of attention, because in academia, if you want to publish a paper, you should use a prepackaged data set so that your results are comparable to everything else that has been published before, right? So that there's no incentive to start cleaning your data and tweaking it. But this is actually often probably more important than the sort of making the modeling more effective or tweaking. Like if you're deciding between trying a new nonlinearity and your transformer or spending that time cleaning up your data a little bit, you should always do the latter. Is kind of the point that I'm trying to make. And I will leave it there. I think, yeah, I have a few more things that I think are interesting that I just didn't have time to put in here. So there's a lot of interesting work recently on generalization in diffusion models. Why do they generalize? There was a really great tutorial at ICML actually a few weeks ago, and they have all the materials online there. I didn't talk about multimodal generative models. That's also coming, right? Like we have the Gemini Omni project, which is sort of anything in, video out, and we want to go towards anything in, anything out. That also comes with very interesting challenges that I could talk about for another hour, probably, maybe next time. And then another interesting topic that I'm actually learning about myself right now is reward-based steering and fine-tuning of diffusion models. There's a lot of papers coming out on that. But yeah, I'm actually not the right person to talk about that yet because I haven't read them. But I'm very interested in that topic as well. Cool. I have a blog, as I said. I'm also on Twitter, LinkedIn. You can email me. I will respond. Sometimes it takes a month, but I will respond. And you can also just find me here until Thursday evening. Thank you.
So we have time for a few questions, if anyone.
Hello, thank you so much for amazing presentation. So you said on your slides that the diffusion is approximate spectral autoregression. And from what I understand is that we first learn some global features. We learn actually gradually, low frequency first, and then all the way to high frequencies. So my question is, did you measure, or is it possible to measure whether the different layers of the noise are specialized to different frequency gaps, like bands, or it is purely maybe the property of the diffusion itself?
That's an interesting one. I think, so we tend to sort of train the denoiser conditioned on the noise level, right? So we train a single denoiser network, and then we give it a noisy input, and we tell it, this is approximately how much noise there is in this input. So it's actually a single model that has to learn to perform all of these tasks, right? Like when I was talking before about iterative refinement, sort of divide and conquer, splitting it up into many subtasks, we're actually trying to use the same model for all of these tasks. Now, I do think in like modern models, like mixture of expert models, for example, you can probably go in and measure which experts are used more at which time steps, and you will probably see some specialization there. But I haven't done that myself, but that would be my guess. Yeah.
Yeah, thank you for the talk. It was very informative. One thing I've started to notice with diffusion models is that if you unroll them through time, they start to look very similar. If you assume like an epsilon parameterization and like an Euler step sampler, they start looking very similar to like residual networks, like ResNets. So I'm just wondering, like, is there any truth in that they're just like glorified ResNets or something?
Yes. I think I have a blog post from a few years ago where I talk about that perspective. I like to say diffusion models are just RNNs, right? Like if you unroll the sampling procedure, especially a deterministic version, like if you have, as you said, the Euler algorithm, if you have a deterministic algorithm, you unroll this sampling procedure and you sort of look at the computational graph that you get. This is just an RNN, right? And from that perspective, you can look at diffusion as a trick to train very deep and very complicated RNNs without having to backpropagate through the whole thing, And it's essentially a trick to train very deep computational graphs without having to do backprop through the whole computation graph. I actually like to talk about this in the context of like depth in deep learning, right? Like when I did my PhD, we were training, deep learning was already a thing, but deep learning meant that you were training neural networks that were 4 layers instead of 2, right? Before deep learning, 2 layers was sort of all that anyone did because it was hard to get gradients to propagate through more than 2 layers. And then deep learning came and said, oh, you can actually do layer-wise pre-training to sort of initialize your deeper network in a good space, and then you can fine-tune. And it's a very complicated procedure, very annoying. And then someone invented the ReLU. And then we realized, oh, actually, you don't have to use like a saturating nonlinearity in your neural network. You can just use the ReLU. Now we can train networks with like 10 layers, no problem. Why didn't anyone think of this before, right? And then came like normalization layers, then came residual connections. Now we're talking potentially hundreds of layers, right? But that's sort of where it stalled, right? We can do hundreds of layers, but if you do 10,000 layers and you try to backprop through that, it's actually still quite hard, right? And if anything, because it's sequential, right, it's very costly. So I like to frame both autoregression and diffusion actually as the next step in this process where we're training even deeper computational graphs, but to make that tractable, we've sort of given them a particular structure so that we can train them a segment at a time. And that's essentially what diffusion is. So like if you sort of extrapolate from that, if compute keeps increasing at the rate that it has, then maybe in 10 years, we can just all go back to training VAEs again, right? Because then it will be perfectly feasible to train 100,000 layer VAE just end to end with backprop, and we won't need these iterative refinement tricks anymore. Maybe.
Thank you. Thank you.
Okay. I have some sort of an open question.
You hold it a little bit closer, so
yeah. I want to ask about REPA. Did you come across any interesting like work doing progressive REPA? So instead of always aligning the representation to the final layer of semantic model, DINO or whatever, did you see anything about progressive alignment?
Well, I think that the closest thing to what you're describing is CellFlow from Black Forest Labs. They just released a new video model, Flux 3, and that's trained with CellFlow, and it's kind of doing something REPA-like, but it's actually supervising layers of the denoiser with other layers of the same denoiser at different time steps. So you're sort of like adding extra high velocity channels to sort of propagate that information between the different noise levels, basically. Personally, REPA is like, it's an interesting one. I have a feeling that a lot of these sort of tricks to sort of accelerate convergence, like REPA, right? They help a lot until they don't. Like they help a lot at certain scales, and then as you scale up, they actually become a limiting factor. Like if you train these models at scale, you'll find that you get progressively less benefit from REPA, and then eventually it actually starts hurting. That's my experience. Because DINO is also just a pre-trained model of a certain size, right? It has a limited capacity, it has a particular representation. It's sort of, it's biased, right? And at some point that bias starts to hurt you more than it helps. Which I think is true of almost any inductive bias, right? People used to use convolutional models for vision a lot, and then they found that actually at scale, at some point, the transformer starts doing better, right? You sort of reduce the amount of inductive bias in the network, but you actually start getting better results at scale. Yeah.
Okay.
Makes sense, yeah.
I have a quick question about discrete diffusion models. Hi. And I was wondering, like, for images, diffusion works so well, but I haven't been following the literature on discrete diffusion and masked language diffusion models, but I was wondering, like, what's possible in your opinion? Is it going to be like, is like conditioning, like style transfer, all of these things will be possible in the discrete space? And also, like, what other maybe like other discrete domains other than language, I mean, could it be applicable for?
Yeah, I think a big one, to answer your last question first, I think a big one is sort of the biomedical space and just general biology space. Like you have a lot of sort of discrete sequences with very small vocabularies that are quite common in biology, like amino acids or the bases that make up DNA. So people are experimenting a lot with discrete diffusion there. Personally, I'm very excited about this comeback of continuous methods for discrete data, because I think there's a lot of powerful machinery that's been built for diffusion over the years, like various distillation methods, guidance tricks, all these things, that if you try to apply continuous diffusion to discrete data, you can inherit most of those, like you can reuse those. Whereas if you switch to a different corruption paradigm, like mass diffusion, for example, you have to start adapting these. You have to reinvent them, basically. And there are certain things that actually people haven't quite figured out how to do yet with mass diffusion. Concretely, if you try to distill a mass diffusion model into fewer steps, you hit a kind of roadblock where at some point your model starts making independence assumptions between the tokens that are just too painful. That like basically, like in the limit, let's say you try to distill a mass diffusion model all the way to one step, it's just going to sample all the tokens independently, which defeats the point of having a model, right? And it turns out with the continuous methods, continuous distillation methods, especially these flow map methods that I briefly mentioned, that doesn't happen. So you can take a flow map model and distill it all the way down to one step. And at least in theory, it's still equally as expressive. Of course, in theory, you would also need a bigger model then to capture a much more complicated task, which often we don't do in practice. But the key thing is there's not this fundamental blocker to go all the way down to one step. And I think that's partly motivating the resurgence of continuous methods for discrete data, which is incidentally going to be the topic of my next blog post, which should be out in the next few weeks.
Really cool. Thank you.
You mentioned, thank you for the talk. You mentioned that when you build a classifier-free guidance model, that you also have a classifier for free, which is kind of more powerful than general classifiers. Have anyone been using that part of the model, like as standalone classifiers?
I think there's a long history of people using Bayesian classifiers, and like I guess also in the context of like robustness, there's been a lot of work on sort of robust training of classifiers, like making them more robust to adversarial attacks and things like that. But actually using Bayesian classifiers is a very powerful method to achieve that kind of robustness. I think the main reason they're not more popular than they are is it's just very expensive. Right? It's often way weird. If your goal is classification, it's often way weird cheaper to train a classifier than to train a generative model for each of your possible classes.
Thank you.
Yeah, so from what I understand, diffusion models have been used a lot in images, and there are a few niches where they have been used also. But I'm curious, what do you think is the future of diffusion models? Because if they can predict stuff like latent space, I guess they are quite general. So could they predict, for example, the latent space of another network, like use network A to predict latent space of network B or something like that?
So generative modeling in the weight space of another neural network
yes, pretty much. So
is actually very challenging in general. Like so I talked a lot about like the spectral view on diffusion here, right? Like and how that maybe partially explains why they've been so successful for images. I think if you look at I haven't done this, but I think if you look at the weight space of a neural network through the same lens, you're going to see that the story is a lot more complicated there. So I think there's sort of certain traits of diffusion, certain aspects of diffusion that give it a leg up for image generation that are not going to apply in the weight space of a neural network. But the same is true also for language, right? The diffusion for language is a hot topic right now. Language doesn't have this spectral structure that I talked about, right? But still, there are other benefits there that you can reap by doing diffusion in that space. So yeah, I think it's not straightforward, but definitely possible.
So I actually had a paper with UI on exactly that, using diffusion on weights. I think in the interest of time, we're going to stop here with questions. So Sander is going to be around until Thursday, so you guys can ask a lot more questions. Let's thank him again for that.
Thank you.
We'll have a break.
So now we'll have a short break just to grab a coffee, and then we'll start the tutorial session. So there are two groups. The lists were shared on Slack. One group will go to the municipality. The volunteers will guide you there. And then after the tutorial, you're coming back here, and there will be the welcome drinks with food. So don't go elsewhere to search for dinner. There will be food here. Leads for the multimodal learning tutorial. Ross is a PhD candidate at UCL. Probably he will tell you a bit about himself. I would also say he has lots of startup experience. So in case you have any ideas in that direction, I'm pretty sure he can give you good inputs. And yeah, he has lots of expertise. He's working in computer vision, human-computer interaction, and reinforcement learning. So I'm sure you'll have a lot to learn from his experience. So thank you, Ross, for joining us. And yeah, let's get started.
Testing. Okay, great. Thank you very much, Viorica. That was quite a nice introduction. I like to sort of maybe think I'm jack of all trades, master of none, which maybe doesn't qualify me to be speaking to you here. Yeah, as she has said, wow, that's quite a slow transition. Maybe, okay, they're just slow transitions. So we're going to have to wear that. I have kind of a diverse background. I've previously worked in quant derivative trading at JP Morgan and at a hedge fund. Then I have my postgrad degree, my master's degree at UCL in machine learning. After that, I did start a startup. We supplied RAG pipelines in production. So yeah, if you maybe in the mentorship sessions or afterwards, you want to hear about what it's like to start a company, move to SF and live on an airbed. I can tell you about that. And now I'm doing my PhD in the same lab as Skanda, in the Prism lab. There seems to be a little bit of feedback. How's that? Okay. And at the Bold lab, which is basically just a renamed version of our initial lab, which was the Dark lab. I don't really know why. I am quite interested in visual representation learning, neural computers, in particular interactive neural computers. And of course, generally they take the form of world models and in video understanding tasks. So that is me. Oh yeah, if you haven't spoken to Skanda, you should speak to Skanda. Skanda is a hero in this space. Just published best paper in CVPR. I am learning a lot from Skanda, so you should too. So you should go and speak to him. He is in the municipality building today, and he'll be around today. I think he's leaving tomorrow. So this is the first tutorial session, which is going to look a bit different, mainly because the idea is to get you guys working at this. So rather than me just presenting content and slides, there is a Colab notebook, which I would really love if you could all open right now. Maybe you guys are faster than I anticipate. Does everyone have the Colab open? Show of hands. Okay, looks like we're all going to need to get opening some Colab. The reason why we're doing this is because obviously it's great to consume content and have it sort of like wash over you. But in terms of like getting it in, there's an element of like you kind of have to just make it hurt and like go through it line by line, get errors, fix them, etc. So this is supposed to be sort of an interactive session where there is a Colab notebook, there are certain tasks, we're going to work through them. There's quite a lot of content. We're going to try and finish it all, so we're going to move at a pretty solid clip. So yeah, so please continue opening it as I speak. By and large, kind of the way we're going to do this is there are 13 to-dos in the Colab. Each to-do is clearly marked. You can control F to do. You have to complete them all in order because most of the session sort of relies on you having completed the previous to-dos. If we're 1 minute away from when I want to advance from to-do 1 to to-do 2, I will ask you to look at the hints which are in the Colab. You can just open the hint. There is basically a solution in the hint. There's a little bit of a kind of line-by-line comments as to why it's a solution. I would ask you to copy paste that into the to-do, and then we'll progress. The one thing which I would ask you to do is to please attempt the to-do without looking at the hint and without asking Claude Code, because then it's kind of not really useful for any of us to be here. So work through it. It's going to break the first time, and we'll get through it together. How are we doing in terms of opening this Colab? Show of hands. What are you doing? Okay, I'm going to continue speaking while you're doing that. What are the blockers from opening the Colab? Are there anyone's running into issues or? Sorry? Okay, it's just slow. That's not good. When you do have the Colab open, I presume this is like fairly vanilla. Please change the runtime to a GPU. We don't really need a GPU. If you overload Colab's servers, we can continue for most of it with a CPU, but ideally you have either a T4 or an L4. And then please run the first code cell 1C. There are a few different imports, which, I mean, it'll import Torch, it'll import, and it'll download the data set. So maybe if I'm going to give everyone another 2 minutes to do that, and then we'll do another show of hands, and if we're ready with the show of hands, then we'll continue. The other thing to bear in mind is that you're all very talented individuals, which is great. The acceptance rate for this year was like an all-time low, I'm told. So that's fantastic, but you also have quite a wide variety of experiences, at least from what I can infer. Some people are doing PhDs in machine learning, and then other people are undergrads, perhaps in a topic which is not quite related to machine learning. The goal of this tutorial is to have a low floor and a high ceiling. So we're going to go over topics which may seem relatively elementary, but the idea is that we'll just go over them. We will go through them rapidly, though, because we have hints, so you can just copy paste the solutions if you need to. We want to be able to go start to finish to training vision transformers to do different tasks with different losses. And we ideally step through it each way. If you are finished rapidly any particular part and you're kind of fed up because oh, I'm finished so fast and everyone else is taking a long time, that's fine. Maybe just help out your neighbors, chat to them, and we kind of all get through together. Please feel free to interrupt me if anything is unclear. Very happy to receive questions. There are also TAs in the room who are familiar with the content of this tutorial, so maybe I'll ask the TAs to hold up their hands. Maybe if you stand up as well, just so everyone, okay. If I could also ask the TAs to kind of float about while people are doing the to-dos, such that like if anyone is really stuck and the solution also doesn't make sense, just kind of ask a TA. Okay, show of hands, who has the Colab open and has a GPU? That's pretty good. I think I can maybe crack on anyway, and we'll kind of, okay. Yes. Has everyone made a copy of the Colab before you started to connect it to a GPU? I'm going to hope that people are doing that. So the outline of what we're going to try and cover today, we're going to start with attention and vision transformers, kind of the base fundamentals. As I said, many of you will be familiar with this, and that's fine, and we can run through it quickly if so. We're then going to look at 3 different types of training these vision transformers. As you'll notice, the architecture is going to remain the same because guess what, we use transformers in everything these days, but the loss is going to look quite different. So we're going to have a supervised loss with cross entropy. We're going to look at self-supervised methods of learning, for example, in masked autoencoders, and then we're going to look at a contrastive learning example in CLIP. So as I said, we're going to kind of reuse a lot of the building blocks that we're going to build up. So like we're first going to implement attention, we're going to implement patchification, and then kind of we're going to continue using them as we go along. Then finally, we're going to look at what is kind of like the new funky side of multimodal learning, which is the unified understanding and generation models, where we can kind of step away from image in classification out or image in text description out, and actually we can have one model which does both things, being image or perhaps even video generation and also understanding. This, depending on time, may be a take-home task. So obviously, kind of the canonical example of a vision language model maybe is a VQA task. You know, this is just one example that we feed in this clip of this heavily pixelated Euro 2024 scratch card or something, and you say list all the countries in this image in the format of JSON, and it manages to do this, and it also manages to have some sort of like plausibly sounding reasoning traces. Underpinning most of these vision language models, we can kind of be very, very crude. Wow. The internet is slow because that's okay. We're at like 0.1 FPS. yeah, if I'm really crude about what a vision language model is, there's basically a vision encoder, which kind of decides what's the visual component of the model. There is a text encoder. There's multimodal fusion. So we'll talk about kind of various different ways that happens, where we need some way of bridging our understanding of the visual space with the understanding of the textual space. And people can get very opinionated on like how humans actually do that, and the reality is no one knows, so we just kind of do what we can. There's then a prediction head, which takes the output, ideally some sort of latent representation from the multimodal fusion, and then we can produce an answer. Today, we're going to concentrate mainly on the vision encoder part. I have clicked the next button, so at some point in time, oh my God, it's actually disconnected from the Zoom. Okay, while that reconnects, yeah, we're just going to continue. Imagine you saw the previous slide, and imagine that there is now a red square over the vision encoder part. We're going to focus on the vision encoder part, and okay, maybe what's the cell coverage like here? Like it's 5G. So maybe I could like tether on my phone. Or maybe there's a wired connection to the internet. Oh, maybe I'm back. Okay, I think we're actually good. Nice. I don't know what you did, but that was magical. Okay, it's now even faster as well. Maybe you're like an antenna. Okay, so here is the red thing that I was talking about. We have a red box around the vision encoder, and this is what we're going to concentrate on. What is going on here? Okay, yeah. I'm going to skim through this very rapidly. We know that vision encoders and vision language models are very useful. They don't only do VQA tasks, as you're all very aware. We can also do things like image captioning, action classification, motion tracking, object detection and segmentation, though that's kind of like, that was state of the art years ago, few shot learning and kind of like visual reasoning tasks. So we're going to look at a few of those as we go today. We know that a vision encoder is, in a sense, it's all about representation learning. We want to map an image, which is like height by width by RGB channels, into some sort of vector of real values. And we know that we have certain kind of conditions and heuristics that are fairly obvious. What would you want from a representation? You'd want them to be somewhat invariant to nuisance factors. For example, the background, if you're worried about the foreground, etc. There's other things that maybe you want them to be rotation invariant to things in the scene. For example, in medical imaging, you would really care actually that like this cross section of a tumor is similar. It gives us similar representations to the other representation of a tumor, i.e., they're both tumors. And things like that. And we can talk about ways of sort of conditioning the learning of the representation space in order to ensure that we have those things. Okay. So the two things that we can ablate when we're learning this representation function, we're going to look at the architecture and also the training regimes. Spoiler alert, we're not actually going to do anything funky with the architecture. It's all going to be the same in the tutorial today. It's all going to be a vision transformer, which looks like this. I'm going to skip the slide because we'll sort of repeat it a little bit. And we're going to go to this slide, obviously. And we're going to look at 3 different types of loss. So one vision transformer architecture, 3 different types of loss. That's going to take us up until like the part 4 before we do the unified generation and understanding slides. We're going to look at fully supervised learning, self-supervised learning, and contrastive learning. So this maybe is familiar with most people, but for fully supervised learning, the kind of idea is you take maybe CFAR 10, you have a data set of images that have 10 classes, and you say, hey, here's this picture of a flamingo. You want to be able to accurately classify that this is a flamingo versus the other preordained distinct class that you have in your data. Self-supervised learning is more of a general learning framework where the idea is that I'm not actually just trying to predict the caption of an image, or not even the caption, rather the class. In self-supervised learning, I am masking parts of my input and I'm trying to go and recreate that. So this, obviously you can see the relation between this and just masked autoencoders in general. It's a form of dimensionality reduction and then reconstruction. And then finally, we're going to look at, well, not finally, part 4 is we're going to look at contrastive learning. and where that originates from, i.e. language models, models such as CLIP, where the idea is basically, can we learn a joint representation space between text and image, such that I can go from text to image and vice and back the other way as well. Okay, so now no, we're still okay if you don't have connection just yet. We're still going to go through this. We are okay. Yeah, the architecture by and large that everyone uses in the field is a vision transformer. The way, again, this should be like relatively vanilla for the audience. The idea is kind of borrowed from language modeling tasks, where we were very good at language at sequence modeling. We said, hey, can we do that with vision? And guess what? You can. So the first example perhaps is in the VIT implementation, where the idea is if I patchify my image into these patches, I can actually look at image understanding as perhaps a sequence modeling task. So I divide up my image into these non-overlapping patches. This is quite straightforward to do if you use a 2D convolution with the same stride as the kernel. I pass them as a sequence into my transformer encoder. There's a linear projection of the flattened patches, which gets added to the position embedding before it goes into the transformer encoder block. In practice, the position embedding, what is a position embedding? Obviously, it's important for the model to know that this particular part of the image is actually here rather than somewhere else. In practice, what we do is we have some learned positional encodings. So we don't have to hard code what these positional encodings are. Part of the reason why that is good is because you can kind of have better generalization performance if you were to kind of use a varying sequence length. You can imagine if I was to like hard code that this position is always the top left, and then this position is always the middle bit, and I was to add some more patches in the sequence, I'd not have a good time. Okay, I've talked about that. I have just talked about that. Really should have used this slide. That would have been great. And okay, so yeah, so the final part, obviously, the kind of like the meat in the sandwich of a transformer, or what makes them so powerful, is the attention mechanism. I think kind of like let's spend 2 minutes on attention for those that are like are familiar with attention, maybe not like exactly familiar with it. The kind of fundamentals are there's 3 different matrices. There's the queries, there's the keys, and the values. The way to kind of think about this, if you haven't thought about it in this detail before, is an example would be, here you are at EEML, and maybe you've covered loads of topics in sort of like kind of shallow level detail today. You've looked at diffusion, you've looked at multimodal, you've looked at attention mechanisms, etc. And maybe you sort of have like an idea of the overall topics, but maybe you have some queries or things that like you would like to know more about in order to solidify your understanding. So you can kind of form those sets of queries. Imagine like each patch of an image, you have your own query about like things you would like to know more about if you were to go and do some sort of fact-finding mission. So you take away those queries about like what parts you don't know about machine learning, and then you open a machine learning textbook, and guess what? It has a table of contents, and that contents would be the keys, right? So you have your keys of like, oh, here's diffusion modeling, and here's transformers, and here's self-supervised learning, blah, blah, blah. The first thing you want to do then is you want to figure out, well, how well do my queries align with my keys, right? So I have my questions, and I've just opened this book, and here's this table of contents. Well, does this book have any of the answers? And then you would put the Bible away anyway. Then we're going to, so we multiply the queries by the keys. We map mull it in, we get some scores. We softmax the scores, so we get some probability distribution over what we want. We divide the QKT matrix by the square root of the dimensionality of K. We do that for training stability. We can discuss why exactly you do that, or why the math works if people want to. And then we go and we take those scores, and then we multiply them by the values. And then the values remaining in this particular example would be the actual content of the chapters. So let's kind of imagine that your scores, or your attention map that you're going to generate by doing a softmax of your queries matmulled by the transpose of your keys, is going to give you sort of like your map for how to traverse this textbook. And then of course you need to actually go and apply the map and get the values back, because you're going to need to learn that. So without further ado, what you're going to do is you're going to go and implement attention in the Colab notebook. This is a visual representation of what attention is. Obviously, sort of this is the original image. You get some sort of like heat map around the values of the image that you actually care about, depending on the task or the task at hand. And of course, yeah, Q's and K's get matmul. We scale them by the dimension. There's a mask, which we're not going to look at right now, but we will. There's a softmax, and then there's a matmul by the values. You may have seen this in another form. You may have seen this backwards, i.e. the keys transpose multiplied by the Q, in which case you will softmax over the columns rather than the rows. If they are equivalent, you're going to end up with a square matrix after doing QKT at the end anyway. But just so if the treatment that we're going to do today in the tutorial is QKT, and it's not that. So if you've looked at that before, it's just the opposite. So first up is, we're going to skip through this. We're going to skip through this. We are now in to-dos 1 and 2. So hopefully by now everyone has the Colab open. Everyone's on the cell. Everyone's connected to a GPU. You don't actually need a GPU to do this, obviously, because it's a dummy problem where there's dummy Q's and K's. Ideally, if you could all fill in your implementation in the to-dos of the scaled dot product attention. Matmul queries and the keys, scale by the square root of the dimension, softmax the resultant matrix. Obviously, just be wary of the dims, depending on how you've multiplied it through. And then please use those new scores in to-do 2 to multiply by the values, and then return. Okay, the signature of this function leaves a little bit to be desired. You need to return the values after you've actually attended over them. So like modify them in place. So please go away and do that. Show of hands, who's done that already? Okay, great, cool. Please do that. I'm going to not speak for 4 minutes, and then I'll kind of call time and say, if you haven't done it now, just we'll go through the solution. Any questions thus far that would help people in doing this to do? Okay. While you're doing that, maybe just like best practices, because now when people have learned to program in the era of Claude Code, people learn different best practices. Maybe I'm old school now, but I think kind of like if you're stuck, just rely on, just like grab some new cells in the Colab. Don't try and just implement the function. Don't try and like jump into a debugger here or whatever. Just get some new cells. Just get some like torch.rand tensors, and just like mess about. Print out the shape of each of the tensors as you go through. Literally just like line up the dimensions of your matmuls and just sort of like visually inspect. Use a whole load of print statements, and please do it just line by line. At the end of the day, it's not rocket science. Like you're just multiplying, but torch can be very pernickety if you don't get your dimensions correctly. Okay, 1 minute warning. Maybe show of hands who's done. Okay. Just for the sake of okay, I'm well. Let's maybe give everyone 3 minutes more because I think it is important that everyone sort of has grokked this because it's crucial to everything else we're going to do. Okay. If you haven't completed it and you would like to complete it yourself, then look away now. But I think just given the amount of stuff we want to do today, this is the solution. Maybe compare your solution to this, and if it differs, just implement it line by line, please. Obviously, it would be somewhat handier if you could copy paste, but I think for pedagogical reason, it's actually quite a good idea to just type it all out. Okay, what are BND? We've got the batch, we've got the number of patches, and we've got the dimension of the embeddings. To get the attention logits, as we looked at before, we're doing Q matmul by the transpose of K. This 1 and 2 just means that I'm changing the second and the third dimension, i.e. I'm flipping this n by d matrix into a d by n matrix, because Python zero indexes, most people know that. And I'm dividing by the square root of d, such that I can make the variance after doing the dot product a unit. It's just going to be 1. The attention scores, then we're going to softmax over the attention logits. We're going to do over the columns. And then we're going to get the values at the end are going to be attention scores multiplied matmul by the values, which came through from the arguments in the function. And now we are returning the values. So if you would like to go deeper into that, either now or later, you can see the hints which are above this to do. You can kind of work through it step by step, and you can mess about with it. But for now, maybe let's just pop that in and continue. Show of hands for me not to click advance on this slide. Okay. We're going to give it 1 more minute, and then we'll take this as our implementation of SDPA, scale dot product attention. This is self-attention. If you didn't get this in 1, that's completely normal. This is, although not rocket science of what's going on because it's just linear algebra, just aligning the dimensions and making this work and making Torch not complain about it is unfortunately just a little bit annoying. A word on speed. There are faster ways of doing this, for sure. Ideally, we would just use Torch for everything, and we wouldn't just use like Python's math library, for example. There are reasons why it would be far faster to do it in other ways if we were to do it at scale, but for the sake of exposition and for this dummy example, we're doing it line by line in a simple way. Okay, I'm going to crack on if that's good. So we're straight into to-dos 3 and 4. So basically, what we want to do now, as we know we need to do, is after doing the attention, we then want to feed it through an MLP to produce another output. So what I will ask you to do here in deduce 3 and 4, there is an object called MLP, which inherits from a PyTorch module. If you don't know what that is, that is fine. We call the super and the init of the module, which means that we can get things like gradients, and we can attach optimizers to things, and Torch will do nice things. But by and large, all you need to care about is, can you please add 2 linear layers alongside an activation function? We're going to use GELU in this example. Please add those to the self of the object, so we can just use them elsewhere. And then please implement the forward pass through your network. And well, relatively straightforwardly, the forward pass will be the second layer operating over the activation of the first layer, which is itself operating on X. So I'm going to give everyone 3 or 4 minutes to do that, and then we'll do kind of show of hands again, and then we'll crack up. Again, if anyone wants kind of help midway through doing this to do, maybe if you just pop up your hand, and then the TAs in the room can kind of disperse and kind of give you a hand. Please don't be afraid to ask questions or to ask help from the TAs. The idea is that we'll kind of all work through this, and we'll have some pretty cool stuff at the end once we get the kind of basic building blocks done. But I wouldn't like to sacrifice the rigor of implementing the basic building blocks correctly for sake of seeing the cool, fun stuff later on. Okay, maybe 30 seconds before we crack on. Maybe raise your hand if you would like to see the solution. Oh, audience of 1. Okay. Solution going up. Here is the solution. This one maybe was a little bit harder to kind of debug on the side because you do need to initialize a module. Well, you don't actually. Anyway, here, okay, we at the layer one, here just L1 on itself is just a linear layer where the input to the linear layer is the number of in features and the output is the hidden feature dimension. We have an activation function, which is the GALU here. Linear layer 2 needs to accept hidden features because they're coming out of the first layer and then output the out features. So this to do is quite straightforward once you have this. So it's layer 2 multiplied by the activation of layer 1, which is itself a tensor coming from Torch. Is that clear? Yeah. Sorry. We could have added a skip connection. We have just not added it just for the sake of kind of clarity because we haven't really covered it. But yes, you're very right. In most transformer architectures, there will be skip connections. But in this example, we're not using it. Okay, so maybe if everyone just has 20 seconds to implement it this way, and we'll crack on. If you like, you could also add a skip connection. The rest of the code will work regardless of how this is. As long as you get to out features, you're good. Yes. Yes. Yes, it will. Yeah, yes, exactly. Reasons why you wouldn't do that is because of memory, because you're allocating that memory each time as you go through. Whereas when you torch compile this module, it knows to do it faster this way and not continuously allocate memory that way. Don't worry about that. If it's easier to actually step it through step by step, for sure, that makes more sense. And probably for the purposes of this tutorial, I should have done that. Okay. The verification of this solution, if you have gotten this correct and you also have your attention correct, there is a part of the collab which maybe just grep or control F to find this part, and please run this part. If your implementations are correct, you should see this printed to standard out. And you should see that the attention output shape is the same as the MLP output shape, and they align with your expectations. If everyone could please just run that. If it matches, then great, and then we'll continue. If it doesn't match, then while I'm speaking, maybe copy paste the solution from the solutions, and then we can continue. If you are really stuck and something is just weird, maybe just put up your hand. We'll speak to a GA. As a check-in, so far, we're a little bit over time, so we might speed up a little bit, but you have just implemented self-attention from scratch, so that's great. We all understand attention now. We understand how that works. The other good news is that this is kind of the core of most state-of-the-art methods today. So it is very important that you understand it from first principles. You've just implemented it from first principles. This is great. And then you've also basically integrated it into the beginning of well, we haven't done it yet. We've implemented the basic forward passive vision transformer, or rather from an MLP, and now we're going to go and implement that into a vision transformer. Key takeaways. So far, for our purpose of a vision transformer, an image gets converted into a sequence by dividing it into patches and adding positional embeddings so the model knows where each patch belongs. We saw that in the positional encoding side of stuff. The core engine is that the model is going to use stacked transformer blocks, where we're going to do self-attention to allow all of the patches of the image to exchange information globally. We're going to get an MLP to process each patch's features independently, i.e. the MLP you've just implemented. And then after processing that, we're going to try it out in a classification task, which we'll get to. And I'm going to skip that for to-dos 5 and 6. Okay, to-dos. That doesn't look like a to-do. Okay, please look for to-dos 5 and 6 in your training, in your in your code. Yeah, that's the solution. Okay, so don't look at the solution which is on the screen right now, and this is what you're looking for. Please find that. This is the wrong screenshot. And please implement to-dos 5 and 6 for the vision transformer. The idea of what we're trying to do basically right now is we already have the MLP, we already have the self-attention mechanism, and all you want to do right now is just pop it into the normal transformer architecture. At the end of this, we will have a vision transformer, which by and large looks very similar to the paper's implementation vision transformer by Dozovitsky et al. So yeah, again, this is not the right screenshot, but maybe give everyone 3 or 4 minutes to implement the vision transformer, and then we're going to go and use it in various different tasks. So I think I hear less typing, so I'm kind of going to assume that most people are okay with this. Put up your hand if you're done. Most people have just given up then. We'll give it 1 more minute and then we'll do the solution. Okay, solution is coming up. To be fair, I probably should have highlighted that you need to use the patch embed function. That may be through a few different people. What's going on here? Here's our vision transformer object, the forward pass of it. For each X, which is going to come in, X being an image, we're going to patch it up and we're going to embed it. For block in blocks, i.e. for a transformer block in the set of transformer blocks, which this transformer has, we pass the model through, we pass the representation through the model sequentially. Each output is basically updating the residual stream of the transformer. After the final block, we're going to normalize the sequence that gets outputted. This is fairly standard in most models, and also is well, you could have seen it in the initial diagram architecture of the vision transformer. And then to do 6, what are we going to do? We're going to take the average, and then we're going to pass it through the MLP head to get the logits for that particular patch. So I'm going to give everyone 1 minute to maybe grok this a bit, copy paste it, and put it in their code, and just make sure it runs, please. And I think there might even be a verification step. Yeah, so the initial to-do screenshot is actually the verification step, which is this one. So you will have a part of your code which looks like this. If you run this, and if you have implemented self-attention correctly, the MLP correctly, and the vision transformer correctly, you should see that the dimensions line up. So that's kind of your check to know that you are doing it correctly. For those who didn't have the solution, I'm popping the solution back here. Sorry? I'm not sure I fully understand the question. The CLS? You mean to reference the class of the object, or you mean to reference the class of the target? That I think is already done in the patch embed method. It should be in the code. If it's not, then maybe that's a bit of an issue. Okay. Maybe there's a bit of an issue. It's not in the patch embed method. Okay. Implement it this way, and then we'll worry about it later, I think. Otherwise, I need to get out of my slideshow and go back in. It's a normalization step. So we do take the norm, and then we also just take the average, because we want each output to be kind of the average of the representation of the information that particular patch gives us. I'm sorry, I can't hear you.
Using CLS, you just take the mean of all patches, and that's what X equals.
Yes, you are correct. That is, yeah. Okay. Ideally, where we are now, you have implemented self-attention and a full forward pass through a vision transformer. Great, cool. now let's go and do something with that. So we have a vision transformer implementation, and that's great. Like we've solved the architecture part. But now let's go and try and use this architecture for particular downstream tasks. So the first, this brings us on to part 2 for the agenda for today. Obviously, we're a little bit behind time, but that's fine because I think we've covered the fundamentals, and now we're going to go into the use cases, and we can move kind of quicker through those. The first task we're going to look at is a supervised learning task using pretty basic cross-entropy loss. So we're going to use all of the architecture of this massive vision transformer to do something as relatively trivial as outputting a class of a particular image. So the data set which we're going to be using is CFAR10. So you have already downloaded this when you you ran your first cell. This is basically, there are 10 classes that they range from airplane, automobile, bird, cat, etc. No flamingo. And the classes are completely mutually exclusive. So that means that we don't have headaches later, which we'll talk about. The idea now is we're going to feed each of these images into our model, and then we're going to output a classification over the particular class. We're going to use the cross-entropy loss function. The idea is that we want to minimize the negative log likelihood of your model's predictions with respect to the true labels. There are 2 ways that we can derive the cross-entropy loss. We can either do it from a maximum likelihood perspective, or we can do it from a KL divergence between your learned distribution and the true distribution. Your true distribution in this instance is basically sort of like a one-hot over the target class. So clearly this is a bit of a toy example for something as complex as a vision transformer. But just to kind of make sure that our transformer is set up correctly, we want to run through it all start to finish first time. So to do number 7 is please implement the cross-entropy loss from scratch. There is a fast way of doing this which some of you may be familiar with. If you can use log sum exp in Torch, which caters for things like overflow, and also will compile all of the operations into one. I would ask you please to do it line by line, i.e. please exponentiate everything, please sum along the correct axis, please divide by the sum. Take. What is that take going to tell me here? Nope. Okay. Take is a weird bullet point. Please implement the cross-entropy loss for to do number 7. And I'll give everyone maybe 5 to 7 minutes to do that. How's everyone getting on? A reminder, TAs in the back, if anyone wants to chat about cross-entropy loss. Hands up if your implementation is complete. Okay. We'll give it another 3 or 4 minutes. Is that a hand up or a stretch? That's a stretch. Okay. Okay, so I think let's move on to the solution. Hands up if you're there. Okay, I think that's reasonable. So yeah, here is cross-entropy loss implemented step by step. In reality, when we use Torch, we can use the cross-entropy loss function. If you didn't want to use that, you can also just do the log sum exp, which does kind of most of that as well. The reason why we wanted to do it step by step, even though we know that there are faster and more numerically stable ways, is just so that like you can kind of see what's going on here. In particular for the case of multi-class classification problems. So first off, we have our logits which come through. Our logits are basically of dimension batch by dimension of the output. We're going to exponentiate every single value in that matrix. We're then going to take the sum of the logits, and then we're going to divide through by the sum in order to softmax it. So we've sort of basically just softmaxed it ourselves, even though we could have just used torch.softmax. What we're then doing is we're taking the negative of the log of the probability, which was assigned by our model to the class which ended up actually being the correct class. And that comes from the cross-entropy loss definition, which we had prior, which I'll just jump back to. In a sense, for this cross-entropy loss, we actually only care about the weight which our model is placing on the correct class. And part of the reason why that is just because this is the probability, the true probability distribution is basically just a one hot over the correct class. So yi is 0 in all examples where it's not the correct class. So you kind of have this weird situation where you actually only need to care about the mass of the distribution which you're placing on the class which ends up being correct. What you could have done instead of doing it that way, okay, yeah, please verify that your implementation is correct. Ideally, you tie out if it's a sign, just error, just flip it. What you could have done instead is you could have one-hotted the labels which you have, and you would basically get you would get a matrix which is the same size as the matrix of your logits. You could have multiplied that element-wise, and you could have either taken the max or the sum in order to find it that way. They're all sort of like different ways of doing it. Long story short, you could just do NN cross entropy loss, and you should tie out with this exactly. But it's good to kind of work through it, particularly to figure out how torch gather works. Everyone familiar with torch gather? Okay. Yeah, torch gather can be a little bit funny to get the hang of. In a sense, what's happening is I'm passing in a matrix here, softmax. I'm telling it the dimension to look up over, and then I'm telling it the index to use in order to pick out the elements of the softmax matrix, which I actually care about, where the index is these labels. So in this instance, the labels are something like 0, 1, and 2 in the toy example we have for you. So we're picking it out that way, which basically is the same operation as you would have had you one-hotted the labels and multiplied it that way. Great. Okay, so now we have a loss. So that's pretty great. So just to check in again where we are so far, we have self-attention, we have a full forward pass through the vision transformer, and now we also have a loss for supervising this particular task, where our task is a classification task on CFAR 10. The good news is that we know ex ante that there's only 10 classes of images in the world. So we're able to go and learn learn an implementation for this task. So what I would like to do now is for us to train the model. So you have a model training step. I think in your collab, it may only go for one epoch. You can change them if you do have access to a GPU and you haven't lost it so far. It would be really great if you could all start training your models, and just let me know if you have like something vaguely similar to this. If you don't, just copy paste all of the previous stuff so far, just so kind of we all have a working version of a vision transformer. And I think kind of what's clear to see thus far is, you know, if you look at the images in CFAR 10, like personally, I struggle to kind of delineate whether they're a plane or a truck. I mean, they're all quite blurry, etc. You've managed to implement a vision transformer, self-attention, and the full forward pass and the loss in the space of like under an hour while trying to listen to me speak while sat in an uncomfortable position. I think kind of like, you know, pat yourselves on the back. We're now training a model which is able to actually do reasonably well, i.e. By minimizing this average training loss, we're getting a training accuracy of 55.64%, which is clearly better than random chance, which would be 10% because they're evenly divided classes for this particular thing. So maybe I'll leave everyone maybe 2 or 3 minutes to run this and just see some reasonable looking output, and maybe just pop up your hand once that happens, and then I'll sort of concatenate the Mexican wave visually. Okay, is everyone getting some reasonable training going on? Hey, put up your hands if you have observed some form of reasonable training. Okay, that's great. Cool. So Yeah, as I said, you've basically implemented self-attention, you've implemented a vision transformer. This is kind of the easiest of tasks which you could have applied. We didn't need vision transformers to do this before. This is kind of just proof of concept that we know all your building blocks works. Obviously, then the question is, are we done? Like, can we just end the tutorial right now and go to the weird nightclub which happens to be in the basement of this hotel? No, for reasons other than it looks kind of sketch. The first is the wider point of like, well, how useful is classification? I mean, if you tell me that there's only 10, yes. Okay. If you tell me there's only 10 classes that exist in the world, then great. That'd be a pretty boring world to live in. I've done really well on this benchmark, but it's not very useful for me that I have this massive vision transformer that can tell me whether the image contains a flamingo or not. In fact, the model you just trained couldn't do that. So yeah, classification is clearly kind of silly if it's over a finite and a discrete corpus of things. It's not very open-ended. Yeah. Okay. So yeah, first thing is we have more labels than those. The second is, where do we even get the labels from? Like the task of labeling 30,000 images with loads of classes is not a very fun task. There's a bit of an issue because our models are getting bigger and bigger and we're getting more and more GPUs, but our data sets aren't really getting bigger and bigger. So in order for us to just not overfit to the data that we have and make NVIDIA a multi-trillion-dollar company, it's important to try and figure out, well, how can we scale our data sets beyond those of just internet scale data? That's what I have said. So what we'd like to look at now is the idea of self-supervised learning via masked autoencoders. I think I have some blurb on why we want to do this. Yeah, okay. Why do we want to do this? Part of the reason why is kind of a data problem. We don't actually need to go and label loads of data and kind of get and scale that, because that doesn't really work. This is a form of unsupervised learning in the sense that we literally just take input images, we mask them up. We feed in a masked version of the image through the encoder. We generate a latent representation out of that encoder, and then we go and we try and decode the image. And what's quite nice, kind of the way of looking at this is like, as a human, well, actually, this is quite a difficult task for a human. But well, I would struggle at this, but you can sort of infer why it's a reasonable thing to assume that if you were to take an image and you were to kind of like randomly mask out certain parts of it, that you internally inside your brain, you're sort of doing some sort of reconstruction there. And the idea is that, can we learn some sort of general understanding of image representations via this masked autoencoder setup? So this is kind of the initial paper that tried to do this in the vision space. That's why we're kind of borrowing their architecture and their diagrams. What's beautiful about this as well is that it's really simple. So we just mask random patches of the input image and we reconstruct the missing pixels. Where and how this fits in, let's do this. Yeah, okay. So this is a unique task which doesn't require label data. So great for that. It's self-supervised, since the supervision signal is actually the input itself. We don't need labels. And the last side is that what's going to be really quite interesting is if we train the encoder alongside the decoder for this pixel reconstruction task, what happens if we actually then just throw the decoder away, and if we use the learned latent representations to do other tasks. So what we can do with this is we can do some sort of fun examples of transfer learning. And you can kind of see vaguely how this relates to, for example, we're training massive autoregressive text generation models. They're trying to sort of fill in the blank where the blank is the next word. Then we take their latent representations and we go and try and get them to do other stuff like reasoning and coding, etc. So this is kind of like an early example of kind of that vector. So before this paper came out, actually, the NLP community had kind of been doing this for years. There was like, okay, here's the missing gap word in the sentence. What do we do? So this is kind of like not completely new. What made this sort of easier to apply was transformers. So we started applying transformers into the vision space. We started actually treating images as sequence modeling tasks. So that lends itself very well to just borrow a lot of what we've already observed works in language. It's kind of like a little bit trickier to try and figure out how your mask would actually propagate through the layers of a CNN, let's say, where it's quite simple to be like, okay, here's the missing part of my sequence. There was also an element of information density, where like if I say to you like, I really needed to run across the road because, and then I don't tell you what that last word is in the sentence, that's like, you're really, really confused as to what I'm trying to tell you here. But if I were to show you an image of like me standing against some blue backdrop of the sky, and I was just to remove some patch of sky, you kind of you've grokked what the image is. This kind of paper, their solution is just to mask more, so they just mask 75% of the image. But that's kind of like how this paper fits into the literature. So now what we're going to do is we're going to use the same architecture which we already have, which is the vision transformer, which you already implemented. We're also going to use self-attention. However, we're going to make the loss. We're going to do two things. We're going to implement masking, and then we're going to change the loss. Because now no longer are we trying to do cross entropy loss because we have no label, but rather we're actually trying to going and reconstructing the image. So the first thing we want to do is we want to divide the image into a grid of non-overlapping patches. We've already done that. We already have patch embed. What we then want to do is we want to randomly select a certain percentage of the patches to mask. We're going to use 75%. Then we're going to return the visible patches, the masked patches, and then the indices that are going to allow us to reconstruct that image. Which you may have noticed here, if I just jump back a slide, one extra kind of, okay, one extra nice to have here. What you may notice is that we're only passing the visible patches into this encoder. And then here into the decoder, we're passing the encoded representations of those visible patches alongside the indices, which you're going to need to reconstruct it. So there's an argument to be made that actually this is a more efficient manner of training because you don't need to pass the total image into through the network at each time. We need to obviously figure out how to do that. I'm going to click through. We've already seen this stuff. Great. Reuse the old patch and embed code, mask patches, visible patches go through the encoder, add learnable mask tokens to the output of the encoder that allows the decoder to reconstruct the missing patches, and then unpatchify the output reconstruction to visualize it. So most of it's done for you. And the other good news is that your to-dos are actually quite straightforward here. The to-dos kind of mainly concentrate on just implementing the loss, which is going to be mean squared error and pixel reconstruction, and the masking logic. But the masking logic, we've kind of removed. Last year's tutorial involved actually constructing the mask and how to like randomly shuffle the patches which we were going to mask and adding them to the space. We've removed that for the sake of the more interesting part was at the end of this tutorial. So I'm even though this kind of looks like it could be clunky and quite like messing around with PyTorch heavy, I think these to-dos are relatively straightforward. So the loss we're going to use here is mean squared error. So this should be very similar to most people. Your first to do is going to be to implement the mean squared error. And then, yes, okay, we're already at the to do. We're not going to do 2 in 1. Great. So now to do is please find to do number 8 and please implement mean squared error. Yes, that's it. Yep. There's no code, sorry. Oh, really? We have the solution into 9? Okay. Okay, that would, yeah. If we have left the solution in to do 9, then to do 9 is done. Okay, that could be an error. Yeah. It's not okay. Yeah. Oh, I see, really? Okay. Yeah, maybe just have a double check on to do number 9. I think to do number 9 is basically just mapping it into a fixed integer number of masked token. Yeah, it should be fairly So yeah, and if you're unfamiliar what's going on here, N is the batch size, C is the channels, and H is the H by width of the image. We want to do it over each pixel. So I'm gonna pause here for 5 minutes, or maybe even a bit less, because this is a relatively low-hanging fruit. Okay, yeah. Okay. We're gonna crack on. This is quite a straightforward one. Torch.mean by the preds minus the targets squared. If you did it in a longer, more complex way, great. It's going to have aided your understanding. Here, we're just going to take a bit of a shortcut. We're just going to take the scalar value of the loss. And now, if you could do, to do number 9, please calculate the number of visible unmasked patches via the mask ratio. This is probably easier than the description would read it to be. You just need to cast a float to an int. Okay, so in the interest of time, yeah, the length to keep is just the int of the total length multiplied by 1 minus mask ratio. So clearly we're keeping 25%, and we're just going to take an integer value here. Ideally, we're all here now. So success, your implementation is correct. Maybe just put up your hand if that's true. Okay, awesome, great. So yeah, we've kind of trivialized this part of the tutorial a little bit. That was a decision we made because I don't feel like it's a huge boon for your understanding that you're able to implement masking correctly. I think it's kind of more important that you understand the core parts of attention and the transformer architecture rather than kind of how to implement the mask. And I think kind of by and large, we have we've kind of grokked what's basically going on here. In the hints, I think there are the hints for the previous year's tutorial where you did actually have to implement this from scratch. There's a particularly tricky part where you need to figure out where the different masks are, and then you need to expand it along the dimension so you can still have actually the dimension of the projection. if you are interested, I would recommend actually working through it later. But just in the interest of time, we're gonna kind of move forward. There is a verification that you've already done, so that's great. Great. Okay, yeah, we need to do the final to-do number 10, which is actually a little bit tricky. So now I'm going to leave with to-do number 10. The good news is that, again, as we looked at before, we were able to reuse a lot of what we've done earlier. So what we want to do is we want to patchify the image. We want to run the patches through the forward encoder, and then we want to return encoded versions of the visible patches. What we then want to do is we want to run the decoder over the patches. In this instance, we just set the decoder architecture to be almost identical to the encoder architecture. There's no cross attention going on. There's kind of no funky stuff. It's deliberately left kind of quite minimal. Your decoder is going to get the encoded representations of the patches, and it's also going to receive, as you can see in the function signature, the masking grid. So it's going to be able to go and recreate it once it's done the decoding. And then what I'd like you to return from this function is recon images, which should be the reconstructed images alongside the actual images. And this is going to be useful for us because we're going to want to do mean squared loss on these two different representations. So if you could please sort of rely on what you've covered previously in the supervised example, leverage what you have now in your mask. Your random masking method should basically be already correct right now. And your loss, as long as you've implemented it in your return a scalar, should be correct as well. So this shouldn't be absolute rocket science, but maybe I'll leave us until 10 to 6 to do this. Yeah, we started a little late and we've sort of timed this tutorial to be almost 2 hours. Well, I can run until 20 past 6. You're free to go, obviously, whenever you want to. I think I kind of will aim to sort of wrap it up around 20 past if that's okay with everyone. So yeah, the other group actually started quite late because they had to walk to the municipality building. So we should be all going until 20 past 6. So we will get all the to-dos covered. So some of the methods in the solution to this return tuples. So if you are getting a bit stuck or a bit confused, you feel free to look at the hints above if it kind of helps what's going on here. But if that's like a little bit of a clue, which should be relatively clear from the function signatures, but it's good to bear in mind. Hands up if you're done this section. Okay, we'll leave it another 4 minutes. Okay, so 2-minute warning. If you're stuck, maybe just look at the hints for now. Okay, how is everyone getting on? Maybe hands up if you've completed this to do. I think that's reasonable. There is a distracting method in the class, which is patchify, which has been pointed out by an audience member. The one you want to use is patch embed. Ideally, that should have been clear, but could definitely be made clearer to you. What are we doing here? We're getting patches from the batch of images which are going through, which we've already looked at before from the patch embed. We're running the forward encoder over the patches when we're telling the forward encoder what the mask ratio is. Just in this particular example, we're passing, in a sense, all of the patches into the forward encoder. As the paper implements, the paper only actually encodes the visible patches. That is happening inside the forward encoder. So kind of don't be confused by the fact that they're all going into the method. That's why we're passing the mask ratio. Then what we're going to do is we're going to run the decoder over the visible encodings alongside the IDs that it needs to restore. And then we're going to get the reconstructed images by unpatchifying the predicted patches. So I'll leave everyone maybe 2 minutes to copy this code here. And then maybe just sort of give me a bit of a thumbs up wave once you've done that. And then we can start training. Everyone okay if we move on from here? Okay. So now, first, can you please run the cell titled visualize the reconstructed output before training? If we look at this, I think this kind of gives us just an example of what we're kind of dealing with here. Here are the original images. As discussed before, these are all coming from CFAR, so they're kind of these arbitrary, stupid classes. And here they are if you mask 75% of them. And I mean, I don't know about you, but I look at this and I mean, I would find it pretty hard to go and reconstruct an image out of that. Nonetheless, so and you know, with no training, obviously a model does pretty poorly at reconstructing some images. This is just sort of like noisy TV. In fact, you'll see a warning when you first run this that matplotlib will say, hey, you're trying to represent these as images, but actually some of the outputs are actually negative because you're just outputting some random noise. So this is what happens when you plot random noise. The good news is though, that if you have implemented your self-attention and your vision transformer and your loss and everything correctly, if you train this for 5 epochs, which depending on the GPU you have available to you, you should be able to do now. There is the training code in your notebooks. Like already we're actually doing like vaguely well on these reconstructed images, despite this being kind of like a pretty difficult task. And then if we were to look at this over time, what we end up seeing is that this kind of fun thing where low frequency information and color get learned first. So we can kind of see these basic building blocks, and that's kind of relatively straightforward. I mean, if there's some green pixels in the image, I'm probably going to infill them with some green pixels. But then the higher frequency structure starts to appear afterwards, and even if we're only running it for 5 epochs. So kind of the cool part about this paper and this implementation when it first came out is like, hey, like you can actually use this like really simple training objective, just mask out some parts of the image and try and reconstruct them, and we can already do pretty well in reconstructing them. However, it gets even better because if I were to kind of maybe stop you at a bar and you weren't a machine learnist, and I was to say to you, hey, I've got like, you know, I've solved it. I am able to mask an image and reconstruct that image. You might kind of say, that's really great, Ross. Why wouldn't I just use the initial image? And that would be a very valid thing to say, right? Like, why are we doing this? And the idea of like why we're doing this is because it is a toy task that we've set up this way, because it allows us to do this thing, which is where if we take the architecture of what we've just learned, again, vision transformer, self-attention in here, target that's going to be updated with the loss, that's going to be supervised by the loss that you've implemented. If we take this thing and we train it, and then we say, hi, the decoder, I actually don't really care about reconstructing patchified images, and we just relegate it to the bin. What if we thought about using this latent space of this model for another task on which it was not trained? And that's kind of like the whole point of this, where the idea is that we can massively scale up the data, which we can learn if we do it in an unsupervised fashion. We can train it on an objective as simple as pixel reconstruction. And then this decoder, which we used for training purposes, we can actually just throw away. And then we can use these latents to do a different task. So in this example in your notebook, I don't think this is a to-do. But what we do is we bring back our cross-entropy loss criterion. We add an optimizer, which is Atom. And for 5 epochs, I think I ran this earlier. We basically go and fine-tune the encoder in parallel with an MLP to go and output a classification on the CFAR task, which we had earlier. So beforehand, we trained this. We tried to solve this task using cross-entropy loss, and we framed it as a multi-class classification problem. But we sort of struggled, right? Because we needed to rely on the good folks in the University of Toronto who went and labeled 30,000 images of pixelated trucks. And now we were able to do this without any labels whatsoever. And purely by training on that and just throwing away the decoder, I'm able to achieve a training accuracy of pretty similar to what I actually got by training for a similar amount of epochs on the supervised side. So I think kind of what I would implore you to kind of take away from this self-supervised manner of training is that sort of this toy example that you train it with is actually that's not the point. The point is to then go and take the latents and do it for other things. And then kind of in relation to my previous point earlier about like how this relates to LLM's reasoning, You know, we scrape loads of just snippets of text on the internet, and we get LLMs to just go and output the next token. That seems kind of like fairly redundant unless it can go and do downstream tasks, but that's just the pre-training step. Then we can go and post-train, and we can align them to do things, for example, like generate blog posts on LinkedIn, or actually useful things like maths. Okay, does that make sense to everyone? Any questions? Okay, nice. So we have 25 minutes and we have 2 more sections remaining. I think that might be okay. We're going to spend a little bit of time on contrastive learning, which I think is kind of like the remainder of the 3 types of loss which we could use in concert with the architecture of a vision transformer to learn vision tasks. And then I do want to spend some time on unified understanding and generation. Clip, if you're looking, so in the same vein, as I said, if you're looking for like an in-depth treatment of master autoencoders, look at last year's tutorial. If you're looking for an in-depth treatment of Clip, look at the tutorial, which was actually in 2024. They have a really interesting use case for Clip, which is like semantic image search, etc. We are going to cover Clip and contrastive learning for the sake of covering it. We're going to get you to implement the loss, but we're not actually going to go and use your implementation of the loss for anything in this tutorial. So I think we'll spend 10 minutes here, and then we'll do unified understanding and generation. Who is familiar with Clip? Show of hands. Okay, cool, great. That is less than I thought. Okay. Clip, great. So the kind of core idea here, if we look at the losses which you've looked at before, the first is we have like a multi-class classification. Okay, we need labels, and we want to learn basically a distribution which is just going to one-hot over the target class. That's sort of like the initial early days of ML. Great. The second side is self-supervised learning, where we want to learn some sort of general understanding of the latent space of images, and we want to then go and leverage that to do other downstream tasks. What Clip tries to do is tries to learn a joint representation space between text and images. And the way you can kind of understand what's going on here is that, like, if I was to give you a description in text called Pepper the Aussie pup, or if I were to actually give you an image of Pepper the Aussie pup, ideally, the embedding which would come out of the text encoder would actually be fairly similar to the embedding which would come out of the image encoder. If I could do that, that would be really useful for 2 different reasons, principally. The first reason it would be very useful is that I could do semantic image search, for example. I could, open my Apple Photos app and I could type in a query and it could return pictures of dogs, and that's how they work. That's how this works. The other reason why it might be useful is if I wanted to train a vision language model to receive an image and then ask questions on it, we need to be able to map that image into a textual description of that image. The reason why that is kind of, it's just the way it is, unfortunately. In general, we have models that are very good at reasoning in text. They're able so their reasoning traces by and large is outputted in text. You can dial up your inference time compute. It's just going to output more text tokens. If you can tell it like, oh, please be really specific in chain of thought, the reasoning all happens in text. But before you can reason about an image in text, you need to have some sort of textual description of the image. So that's kind of what motivated having this in terms of a usefulness use case. But there was another motivation for Clip, which was released by, which is an OpenAI paper, which is that if you scrape the internet, there's actually quite a lot of data of labeled images. So obviously there's a whole lot of crap out there as well. So there's a big cleaning step. But if you do have images with textual descriptions, for example, like, me and my mum at the park, well, then the model would try and learn who your mum is, I suppose. Yeah, I mean, you'd want to have a better caption than I just gave you there. So what we're trying to learn here is a multimodal embedding space. And what you can kind of see here, a laser pointer would be pretty great right now. If I output all of the text encodings for 5 different text captions right here, or N, actually, that's an N, and N different images, what I would really like is actually that this text encoding, if this is the correct label pairs, I'd want these ones to line up such that the dot product of those would say, yes, these are super, super similar. And I'd want the off-diagonal ones not particularly to be 0, because you may have like a few kind of similar descriptions of kind of vaguely similar images. So that's why training clip can be a little bit tricky in terms of like what do you do with the hard negatives and soft negatives, etc. We won't get into that today. But what you can sort of understand by this is you sort of want your if I was to do this, that your resultant matrix would kind of have like a ridge along the diagonal there. So this is kind of what I said, but there are two things which we're looking at. The first thing here is you have the image encodings representation and the text encodings representation. We dot product those to look at the pairwise cosine similarities, and there's a temperature parameter here, which we'll go deeper into temperature in the next section. And then, well, you can kind of understand intuitively what we're doing as basically we're sort of doing a cross entropy loss along 2 dimensions. So for this image encoding, you're going to say, for this image encoding, which is the correct image? And then for this text encoding, you're going to say, which is the correct image? So you're going to have a cross entropy loss on one axis, and you're going to have a cross entropy loss on the other axis, and then we're going to take the average cross entropy loss. In reality, when you're actually training things, this thing is kind of hard to get to stably train. But the most basic version of the clip loss is, well, actually for you to implement, that is to do number 11. You should have in your collab the maths of the clip loss. It should be fairly straightforward. There's a dot product. Well, okay, there's a few different things going on. The first is you want to map your image encoding and your text encoding to the same dimension. So there's a linear projection. There's a dot product between those two. There's a norm, and there's a temperature parameter. But like it's no crazy stuff that you haven't seen before. So to do number 11 is to please implement the clip loss. I think let's spend honestly, 5 minutes here, just for you to try it. And then I'm gonna run past, because I think there's kind of more interesting stuff to do than contrastive loss. In fact, show of hands who wants to skip implementing the clip loss to do the, yeah, okay. I'm going to overrule the majority, and we're going to skip the implementing the clip loss, mainly because it's kind of just implementing just the algebra. The second thing is I think we've already covered the motivation behind clip and why you would use it. And the third reason is we're not actually going to use the clip loss for anything. We can't actually go and train a clip model. So this is a useful exercise to go through. There's a verifier in your code to check that you have implemented it correctly. If you're interested in actually understanding how clip works and kind of stepping through it, please look at it later. But for now, we're going to go and look at this solution as if you did it. And it's pretty straightforward. We want to normalize the image embeddings and normalize the text embeddings, because in general, they kind of come from different models. And they may just have different magnitudes of the embedding space entirely. We want to get some logits after the cosine similarity, scale it by the temperature, cross entropy on the images, cross entropy on the texts. Okay, it's fairly straightforward. The reason why we're skipping that, I'm going to skip this as well, is because I think I want to spend the next 5 minutes to talk about just a bit of a recap on what we've just done. And then we have 10 minutes to look at unified understanding of generation. What we have looked at, we have self-attention done, we have vision transformers done, and we've tried to experiment learning with 3 different losses. So in reverse order, we've got the contrastive loss, which is clip. Then we've got the masked autoencoder self-supervised learning paradigm, which is kind of the more de facto paradigm these days, rather than using the labeled data in the cross entropy one-hot classification task. How do I choose which one to use would be a very good question. In reality, you don't really have to choose. So there's an interesting paper recently, Cambrian 1, it's like an image VQA model, and they have this kind of smart spatial vision aggregator, where basically you got like the output of the encoder number one, of like one particular type of vision encoder, output of another type of vision encoder, output of another type of vision encoder, and they use this SVA, so like a spatial vision aggregator, to aggregate the latent representation, to choose how to attend over the different latent representations from different encoders into one sort of merged latent representation. So that's kind of one way we could look at things. They will actually do a full ablation as to like, well, we could use all these different vision encoders. You can use SIGLIP, which is relatively similar to CLIP, except we're using a sigmoid loss. Dino V2, which is a self-supervised method of learning. So that's kind of similar to the second one we looked at. Notice that none of these are fully supervised vision encoders because we don't have enough data to do that. And they will ablate they have ablated their performance on a wide variety of benchmarks involving like general reasoning, OCR and chart understanding, etc., using different concatenations of vision encoders. So kind of this is all to say that you don't actually need to make a hard and fast decision. And actually, as we'll look at in the unified understanding and generation side, there's an example of that. Things that you should bear in mind when you're choosing a vision encoder for your particular task. Dataset size. There's a good paper called Scaling Language-Free Visual Representation Learning. It should be called In Defense of Language-Free Visual Representation Learning. It's kind of authored by people who are understandably upset that language-supervised visual representation learning generally tends to outperform self-supervised visual representation learning, i.e. CLIP and SIGLIP are kind of like de facto used more than the self-supervised methods. They make the argument that actually that's a data set issue. CLIP is trained on a massive data set, and the self-supervised learning paradigm, despite the fact that you can massively scale up data, they're not actually trained on that much data. That's not as much the case anymore with the advent of Dino V2 and V3, but they kind of talk about the competitive dynamics between the kind of the second manner of learning and the third manner of learning, which we looked at. The other thing which you need to be aware of are bias and priors in language-supervised encodings. And what I mean by that is that if you language supervise your learning of visual representations, in general, your data set is like text annotated images. And you generally don't find a text description of maybe a room with like 7 doors, because there's not a lot of rooms out there with 7 doors, and of them on the internet. So when you language supervise it, you kind of have these biases which come in just from your data set. And what you can actually find is for VQA models when you're assessing them, for VQA models in general, you pass like a natural language question and then you pass the image. There are documented failure cases where VQA models actually do remarkably well, even if you pass a completely blanked out image. Like they manage to do very, very well on the benchmark. And the reason why is just because you can kind of figure out when the question is like, how many doors are in the room? Well, it's probably 1 door in the room because it's a standard room. So be aware of these things. If you want to maximize your benchmark performance, use some language supervised stuff. And if you want to actually learn proper representations, maybe don't. But great. So we have 10 minutes, which is probably not enough time to go through what we're going to go through right now. But this is, in my opinion, the most interesting part. But I think it's well structured for like a take-home task. There's not a lot of to-dos yet. Half fast, great. Okay, cool. This sort of marks a departure from what we looked at before, in the sense where if we look at the labeled or the supervised example, our task was like, hey, here's an image, like what's the class? Okay, like that's great. Your output is literally just like a classification. If you look at the self-supervised example, obviously your output is like, I want to reconstruct the image, but then we're going to go and use the latents to go and do something else, like fine. But like the purpose of learning that is just to kind of learn a useful latent representation. It's not to actually go and generate some images. And if you look at the CLIP example, you can pass in some text and you can kind of figure out like, what does the embedding of an image which would refer to that text look like, but you can't pass in text and get an image. So it's like, it's not a diffusion model as Sander would have looked at. So the kind of this part of the tutorial is going to look at like the idea of well, what if we were to unify the tasks of generation and understanding? And this is quite cool because it both require, like both tasks, if you think about it, they do require reasoning about and ideally in a visual world, right? Like if I ask you what's in this image, and if I ask you like to generate an image of like Reykjavik at the summer solstice, which apparently this is an image of, though Reykjavik looks quite sparse, both involve you sort of having some sort of visual representation of what's going on. There's another reason. Some reasoning in image space is easier for particular tasks. Like if I were to show you an image of loads of distinct colored pipes and you were to answer with a single integer, like ideally you would be attending over that particular image. That would be great. You shouldn't just be kind of like relying on the biases that are in the language. And also for tasks that now we're kind of like stress testing VQA models on, four circles are placed in the general position of the plane. What's the maximum number of distinct regions they divide the plane into? It's quite hard to answer that with a purely text understanding of what's going on. Ideally, you sort of like you visualize that, and then you sort of you count up in your imagined representation. But and of course, there's other examples why reasoning in text space is easier. So like let's not abandon text reasoning, but like, let's look at this. Yeah, there's a lot of models that try and do this lately. It is new, but it's kind of like, you know, what the whole field is kind of looking at. There's another reason why, I mean, even if you think about like large scale labs, which might have video understanding models, i.e. Gemini, they might have video generation models like VO. There's an Omni project. Then there's like interactive world models, for example, Genie. All of them probably involve some sort of visual understanding, particularly in the visual understanding and visual generation models. It would be quite useful if they could all borrow on the same latent space and you wouldn't have to go and pay like N dollars to go and train each one again. So there's economical reasons why the field would converge this way as well. It's important to be aware of those. There's sort of three axes which divide the space here, which I'm going to skip over in the interest of time. But basically, you can read these papers afterwards if you can look at the slides. What we can do is we can like discretely autoregressively generate tokens that we can decode into the visual space. There's like discrete diffusion ideas where you generate some like discrete representation, maybe some sort of like VQVAE or something, and then you go and you run a diffusion model from there. There's the same, but from a continuous autoregressive representation. Like there's various different examples of this. There's the other axis that you can kind of divide things. So this is sort of this would be like the axis of how does generation happen? Like, are you outputting tokens? Are you running a diffusion model? What's going on? The other axis would be the parameter coupling. So probably we're going to leverage some sort of text encoder that we already have because there's loads of them, and probably we're going to leverage some sort of visual encoder that we already have because there's loads of them. But how do we get them to speak to each other? We'll talk a little bit about that alongside this tokenizer strategy, where the idea is that is there like some single shared tokenizer? It tokenizes text, tokenizes images, or do you decouple them? How does that work? And then also there's the element of, in particular for like your for encoders here into your model, there's generally a tension in the field between semantic and perceptual fidelity. So if you were to ask a text task like, oh, Bob went to the shop and then Bob spent €5 and then got €2 back, like how much did Bob spend? Like you're dealing with kind of semantics here. Like there's a person called Bob and there's a shop here and he spent €3 or can't remember what I said. I don't need to visualize what the shop looks like, but if I'm actually going to try and like generate some sort of like video of this scene, I probably do care what that shop looks like. So it's kind of unclear whether you would use some sort of language supervised encoder here or some visual supervised encoder. So that's like a bird's eye view of what's going on in the space. You can kind of do the reading lately. We are going to look at a model called Janus. Janus kind of cheats in the kind of way that most models kind of do these days, where they say, I don't want to choose, so I'm not actually going to choose. This thing should have better contrast, but it doesn't, and I've just realized this. Janus is basically two models bolted to one. We say three parts, but like just understand it as like two models where basically you have the short for understanding. You have the understanding encoder, and then you have the understanding text tokenizer. And then here you have the generation encoder and the generation text tokenizer. In the generation encoder, you basically like they're using two different encoders for each individual task. If you ask Janus, so Janus, okay, I should preface this with why Janus is useful. Janus can both output understandings of images, but it can also generate images. But what's actually going on behind the scenes is it's using, you need to put it into two different modes. So there's an understanding mode and there's a generation mode. If you use the understanding mode, you basically are going to go image in through the understanding image encoder, and then it's going to output a textual description of what that image is. And if you use the generation mode of Janus, you pass some sort of language instruction in, and then if you want to pass in an image here, it's going to use the kind of textual, the fidelity understanding encoder. We are not going to go into the weeds of Janus. In the interest of time, we're going to look at kind of like two applications of using Janus, and kind of a failure case of that. Yeah, the first thing we're going to look at is everyone at the Janus side of their tutorial? Has everyone scrolled down to Janus yet? Before we continue, what would be really great is if you ran the cell that loads the Janus model. You will need a GPU for this part of the tutorial. There are two to-dos in this section. They're the last to-dos that we need to do. But ideally, you can load the Janus model from Hugging Face and you can load it onto a GPU. Before we do that, then we'll speak about these two things that we're going to do. Maybe just give me like a hands up once you're there. How's everyone getting on loading Janus? Yeah, all good. Okay, that's great. So let me remember what we're doing here. Have you loaded the part of Janus where there are two cats there and there's a remote and it's asked the question about it? Yeah. Okay. Cool. You'll see in the code that you will have had to set in the prompt and the chat prompt template, basically, the mode that you're interacting with the model there. You basically interact with the model there in an understanding mode. You've passed it this image of a cat and it's able to output kind of the general thing. We're going to look at doing two things with Janus here. And then like in the code already, you've seen the understanding example, but we're going to look at the generation now in the next step. And we're going to look at two kind of levers which we can pull. So the first thing that we're going to do is we're going to do classifier-free guidance. And yeah, you saw Sanders talk on classifier-free guidance. Turns out we can actually do it too in autoregressive generation. Obviously, kind of like the main benefit of classifier-free guidance is you don't need a classifier. It should be kind of like relatively straightforward for most people to kind of intuit that if I have a generative model and I have a classifier, it says like, this is a cat and this is not a cat. It should be easy to kind of guide the guidance of my generative model toward more of the cat space. But what's quite nice about classifier-free guidance is that we don't need a classifier. And then so how do we actually do this? I think maybe is already clear from the previous talk, but it's kind of worth looking at again because you're going to implement it in the to-do. Your logits are basically the unconditioned logits plus a guidance scale multiplied by the difference between the conditioned logits and the unconditioned logits. So I think we might have a diagram of this. We don't have a diagram of this. There is a diagram of this in your collab. Basically, it kind of shows there's like this 3D representation of there's like three-dimensional logits, and you can see one logit is being guided by the other one. What you kind of should take away from this is that if you were to take an autoregressive generation model, and if I was to run it through with a prompt saying like, hey, generate me an image of a cat, like a cute cat, and then I was to go and generate an unconditioned generation, i.e. something that has nothing to do with the prompt, ideally, the latent space of the conditioned generation should be more toward the direction of what I care about than the unconditioned latent space. If it's not, you have a very ill-conditioned latent space. And the idea of what classifier-free guidance is trying to do is basically kind of saying like, okay, well, I don't have a classifier, but I know the direction in the latent space that I need to move to get more toward what I care about. So we are going to hack into the generation step of one of the Janus model to guide its generation via classifier-free guidance. You have quite, in the to-do, don't worry too much about understanding every single line of the code. There's quite an efficient implementation, which maybe makes understanding a little bit harder. But basically, we generate an attention mask, we generate a conditioned attention mask, and an unconditioned attention mask in kind of like one particular for pass, just for efficiency purposes, but don't worry about that. So one of the things we're going to try and do is we're going to try and implement classifier-free guidance. And the other thing which we're going to play around with is temperature. Basically, for those of you who have covered temperature before, I'm going to run through this relatively quickly. Physical systems at low temperature settle into states, and at high temperatures, they explore a lot more. For autoregressive generation, if we have a higher temperature, we get kind of like more crazy and wacky outputs. You can view temperature as like a sliding scale for adjusting the relative log odds of particular trajectories in your path. Like a super high temperature will basically make your softmax a uniform distribution, and a super low temperature in the limit will collapse to a one hot. So we're just looking at the generation step of Janus. We're playing around with classifier-free guidance, and we're playing around with temperature. This is a graphical representation of what I've just said, so I'm going to skip it. Can you please now do to-dos 12 and 13, where you basically want to implement classifier-free guidance, which is basically implemented in the description, and divide your logits by temperature so that we can control the temperature of our generation. And then we'll do that until like 26 past 6, and then we have 4 minutes to look at why it's cool. How is everyone doing with these to-dos? Hands up if they're done. Okay. In the interest of time, we're going to wrap up this section. If you could copy and paste classifier-free guidance alongside temperature sampling here, just so we can get some images, and then we can understand what the capstone project is. Hopefully, classifier-free guidance in this setting is actually really quite straightforward. Again, it's cool because we have no classifier. We're just pointing in the latent space. And then temperature sampling is literally just dividing through by temperature alongside the correct dimension. So yeah, it's like just these lines that you need to implement in the step. And then if people could just maybe raise their hand once that's done and it's running a generation. Okay, great. Hopefully you now have a really creepy red panda and much nicer corgis. So the code is basically set up such that, okay, temperature sampling you can play around with in your spare time, and you can kind of figure out what makes more diverse generations. As you can see here, we're changing the classifier free guidance weight. So ideally, when you say kind of like, oh, I actually care about a nice corgi, you should get a nicer corgi as the classifier free guidance weight increases, because you're pushing the latent representation further in the direction of niceness in corgis, which is quite nice. Be aware this isn't free. You can imagine if your classifier free guidance weight was like 100, you wouldn't get like a really, really super nice corgi. In actual fact, you'd be prompting your model to generate from like a point in the latent space which it has never generated from in training. So there's definitely a limit to classifier free guidance, and there's a whole load of people that do smart things about like how to improve classifier free guidance and whatnot. But this is sort of like basically how to do classifier free guidance in autoregressive generation. And the capstone project, which we can begin to attempt now here, but like you're going to need to go and take it home and look at, is the idea of like closing the loop here. So what we know is that our model is able to generate an image. We also know that our model is able to understand an image and to map it to like, does this image map the prompt or not? The way we do this in the code is we basically say kind of like, hi, like here is an image. Does it match this prompt? And the prompt might be like a red bicycle against a wall. And then we look into the logits and figure out the probability mass that it's putting on the token of yes or the token of no. So we're sort of grading the model's certainty over knowing what's in an image here. So we can see that we can make the model do some understanding and some generation. The capstone project is basically ideally for if I prompt a model and I use classifier free guidance to guide it more toward the prompt, as I do that, for greater guidance scales, if I were to then go back and take the outputted image from the model and feed it back into the understanding mode of the model and say, hey, does it match this prompt? Ideally, the log probs over the yes token should increase. If that happened, it would be kind of a neat example where it would be like, oh, great, okay, by shifting more in the latent space of the generation stage, I generate sort of more coherent images from the understanding side. So, okay, in the interest of time, that is the capstone project. Please go in and look at it yourselves. Be aware that, unfortunately, in general, when Janus does understanding tasks, it understands in text space still, right? Although it can do understanding and generation, internally it does go, and when it tries to understand an image, it maps it into some text representation. There is one big unified transformer, so if you wanted to sort of interleave some sort of multi-step generation and understanding, ideally the transformer is able to attend over the latent representations of the different encoders, but it's not perfect, and there's a whole lot of interesting stuff that still remains to be done here. What's important here is that the generation is autoregressive. It's not diffusion, but we can still do classifier free guidance. We saw classifier free guidance steer faithfulness, and you can kind of implement that yourselves as well. And then the kind of take-home task is the self-evaluation, where the idea is as you increase the guidance scale and you pass it back into the understanding of the model, does the model seem to agree with it a lot more? There is also a paper called Gen4U, Unifying Video Generation and Understanding via Diffusion, which Viorica is the last author of. So like it's a hot topic. You should look at it. This is a very different architecture than what we've looked at, but the kind of the overall topic is the kind of the same. And the conclusion, to wrap up, we don't need to do that. That's fine. We don't really need to do that. Yeah, okay. Like we still don't really know what the best tokenization format for images are. We still don't really know what the best way of supervising visual representation learning is. There's still a whole load of debate in this field. We've kind of generally settled on let's just use sort of a kind of an amalgamation of everything. And even Janus does that as well. there are also elements of extending what we've just looked at to video understanding and video generation. Obviously, this gets a whole lot more computationally complex. You should read a paper called Vivid, which is basically the vision transformer for video. There's a whole, there's a lot of research going into like how should we tokenize videos, and what does that look like? And clearly, we're still sort of like quite behind the curve on visual reasoning tasks. In the sense that which of these shapes can be folded into a cube? If we ask Gemini 2.5 Pro, clearly only A can be folded into a cube, but it seems to think that B can as well. So all that is to say that the space is still wide open. You need a lot of compute to compete, but there's a lot of interesting angles for research here. And with that, yeah, to summarize, congrats, you did self-attention, vision transformers. We've looked at a supervised loss manner of learning visual representations. We've looked at self-supervised loss. We've looked at contrastive loss, even though we kind of skipped through it a little bit. And now we've looked at sort of like unified generation understanding, which is where the field is going. And hopefully you'll be able to kind of like look through that take-home task later. But without further ado, it is 6:30. It is your first day here. Everyone's probably pretty knackered and has like flown in late yesterday. Thank you for bearing with me on the last session of the day and for working through everything. I hope it was reasonably useful. The collab is probably better laid out than the talk I just gave. So if you didn't like the talk, you can read the collab. And thank you very much.